Has anyone used Virtuoso so far? Okay, that's good. That's part of the story.
Okay.
All good?
I think so.
You think so? Okay. Okay, maybe before he introduces the workshop, there will be some introduction talks from Konstantinos on first, and then there will be some invited talks that a lot of his team will be delivering, and then after.
Can you hear me? Can you hear me, Harsh? Can people hear me on YouTube? Can people hear me on YouTube? Can people hear me on YouTube? Can people hear me on YouTube?
On YouTube, they cannot hear you on Zoom. I guess I get stopped.
No.
Okay.
Okay.
So yes, we can start after these interesting technical issues, which I have solved many times during honors lectures. So as Honor said, thank him for the nice introduction. And I'm gonna be talking about Virtuoso. Yeah, Virtuoso is my child, as he said. I worked on it for at least 3 years, since almost the beginning of my PhD. And we organized this workshop to bring together, I guess, a bunch of people who might be interested in it. Some people who have inspired me in working on visual memory, and then they are in the room. And some other people who I hope use it in the future. So we're going to be talking about infrastructure for evaluating novel hardware and operating systems interfaces. This is the first iteration of the workshop, and we hope to host more iterations of the workshop in the future in future conferences. Who am I? I don't need to tell you who am I because Honor did the greatest introduction. You can find more about me on my webpage. Regarding the schedule, so we're going to have 3 talks from 8:30 to 10:30 a.m. And then we're going to have a small break and have 2 more talks from 11 a.m. until 12. And then we're going to switch to the schedule of the tutorial and the live demo. So our focus in this workshop will be hardware and operating system cooperation. And what is a better example of hardware cooperation, hardware and operating system cooperation than virtual memory? And virtual memory is one of the first instances of hardware and operating system cooperation, one of the most successful ones, and one that still remains in most of our computing systems. And how does that work? So our applications use program addresses, virtual addresses, and when they want to access the physical memory, we need to take these addresses and then use the address translation hardware to be able to access the physical memory. Here, what do you want? Sorry again. So yes, virtual memory is examples of hardware and operating system co-design. What did we need to do? We needed to take program addresses from our applications, and through the virtual memory framework, what can we do? We have some sort of equipment down in the hardware, and we can access directly the physical memory. And who is managing memory to do all these things? It's the operating system. But if we want to be able to perform studies and research across the stack, across the operating system, application, and hardware level stack, then we need a simulation infrastructure. So I'm going to be talking today about the simulation infrastructure that we built called Virtuoso. It was published in ASPLOS 2025. And with this, I evaluated some of the works which are either published or under submission. And these were all about hardware and operating system synergistic schemes that accelerate address translation. So let's get to some basics first. So why do we need virtual memory? Virtual memory has several benefits. First, it provides the programmer transparent memory management. The application and the programmer do not need to know anything about physical addresses. Second, there is process isolation. Third, there is data sharing between processes. And the question is, how does virtual memory work? We have two applications, as you can see here, and these two applications use two different virtual address spaces. And there is a thing called virtual to physical address mapping that allows us to take one virtual address and be able to access the physical memory directly without involving the programmer at all. And most of you know this stuff, but the question is, who establishes this virtual to physical address mapping? And the answer is, when an address with its own virtual address space wants to map a page in the physical memory, then who does that? We have a fault in this scenario because we do not know the mapping between the virtual and the physical address, and the operating system takes over. And the operating system handles essentially the memory allocation, the physical memory allocation. And we have two distinct scenarios here. First, the application gets stalled, and then the operating system tries to find free space in the physical memory. This is the scenario, the case of a minor fault. In this case, we are fetching, in another case, we need to fetch data from the disk, especially in scenarios where we want to access a file back data. After we fetch the data from the disk, we need to be able to find the free space in the physical memory. And this is called a major page fault. The operating system, after it does all these things and finds a nice spot for our data inside the physical memory by bringing it from the disk or not, it needs to store and update information about the virtual to physical address mapping. How do we do that? We do that with a page table, which is stored somewhere in the physical memory. Again, this is all background, but I want to spend some time on that. I'm going to be quick though. So address translation, how does it happen at the hardware level? We ship the virtual address to the memory management unit that lives inside our core, which talks with the memory hierarchy to bring the page table and store it as best as possible. How does the memory management unit look like? There is an L1 ITLB and an L1 DTLB that store recently accessed translations. If we miss in those structures, then we access a unified L2 TLB that stores translations for both data and instructions. So if we miss also in the L2 TLB, we need to perform a page table walk. And the page table walk is a state machine that looks up the page table. And if we miss, if we need to perform the page table, and given that the fact that there is a radix-based page table with multiple levels, then we cache the intermediate levels in the page walk caches. And this is, I think, in most modern processors, this covers a lot of the page table walk overhead that exists. If not, if we don't find our data there, then we need to retrieve the data from the page table. And GPUs, CPUs, network interface cards, they all use concepts from virtual memory because and it has been a cornerstone basically of most modern computing systems. But it does not come for free. So it causes high performance overheads because of two reasons. First, it might cause high performance overhead because we need to spend cycles to allocate memory. And second, we need to spend cycles in performing address translation. Let's jump to the memory allocation overheads first. So we have a bunch of emerging workloads like function as a service, this short input, short output, large language model inference, which again can fall under the serverless paradigm. They're short running, they have a very high spawning throughput. And what's the problem with that? We're spending too much time on operating system memory allocation routines and a smaller amount of time on the execution. What does that mean? The time we spend in the operating system cannot be amortized due to the short execution of these functions. And I guess we will have a talk that tries to cover this a bit later today. So in this plot, we demonstrate the physical memory allocation overheads, and this is the fraction of the total execution time of these applications. These come from serverless and matrix operations and some short input, short output LLM inference, where we demonstrate that on average 32% of the execution time, and we measure this in a real system, is spent on physical memory allocation. When it comes to address translation overheads, we have another class of emerging workloads like sparse machine learning, bioinformatics, graph analytics, and databases, which are long-running and typically have irregular memory accesses. In this scenario, the problem is a bit different. The problem here is that we have lots of LTLB misses caused by irregular memory access patterns and the large data sets, lots of page table walks, and these high latency operations basically stall the data fetching. We need to pay a lot of cycles upfront before we are able to fetch our data. In this plot, we demonstrate the fraction of the total execution time of address translation in a real system in very large graph workloads and some other quantum simulation and HPCC workloads. And on average, 26% of the execution time measured in a real system is spent on address translation. And I think Dimitris is going to give us a bit more about the exact numbers here from production systems. So virtual memory causes high overheads, and these have diverse nature, and different workloads cause different types of overheads. So, and these overheads are expected to increase as we transition to much larger physical address spaces. So we have unified memory, like a GPU memory and a CPU memory, where we need to manage them very flexibly, being able to store data in the CPU memory while we cannot fit all our data in the GPU memory. We have direct storage access. In some scenarios, we are able to access a high-end SSD with a byte addressable interface. We also have memory disaggregation, where we have access, like CXL, we have access to both local and remote memory modules. And researchers try to save the day. How do they do that? They try to co-design the hardware and the OS to reduce the virtual memory overheads. So we have researchers who propose software-managed TLB subsystems. What does that mean? We mean that we back up our large hardware-based TLB hierarchy with a software-based TLB. There are multiple works across this domain, and another bunch of works propose leveraging virtual address to physical address contiguity. Many of these approaches follow this, and they do this by basically calculating the physical address using a direct offset without the need to perform costly page table walks. Another class of works try to accelerate memory allocation, like physical memory allocation, by delegating parts or the whole physical memory allocation down at the hardware level. And we're going to have one of our speakers who's going to discuss one of these today. Last, we have another type of works where they try to perform would use different types of mappings, like near memory address translation, mosaic pages, and utopia. This is one of our works. And in these scenarios, we try to restrict the mapping so that we reduce the size of the page table. There's much more. How can we rethink the page table design in order to be able to perform more fast page table walks? How can employ multiple page sizes? Most modern systems are using multiple page sizes in their systems, and a lot more. So there's a wide range of hardware operating system co-design techniques that aim to improve virtual memory. And basically, we brought the researchers today so that they can discuss these techniques with you. Thanks a lot. What's the issue?
We will have them send the emails that send them the Zoom link. You need to fix this.
What is the problem with that?
It needs to be hidden.
Hidden.
Yes, hide floating panel. But anyway, we stop share. We set up the next talk.
Hide floating panel.
We don't need to do this now. We set up the next talk.
No, but did they email the slide?
We will ask him.
Ask
I'll send the Zoom. Should we have the Zoom or should he have the slide?
He wanted to bring on with his own laptop.
He's in the thing by the unit. Okay, it's fine. It's fine. Like.
Laptop or do you wanna start? I'm sending you a Zoom link if you can. Yep. Yeah, I just sent it a new one. It's a new one. This is for the Zoom, the other words. Yep.
Recording in progress.
Speaker. Yes. The speaker is Yep. And then can you zoom into the connection in the arm? So
I need to open the mic.
yes, and there, can you click the arrow? There's the correct microphone. Perfect. Wireless.
This one? The wireless.
Oh,
Can you hear me?
Can you hear me? Good.
Is it good?
Good.
Can you hear me?
Yeah, I can see it on Zoom.
Okay. Then, just a second.
Okay.
In the slideshow.
Perfect.
And let me share the slide to Zoom.
Can you see everything perfect on Zoom? Yes, everything's perfect. Yeah, it looks good. Can you check Zoom? Can you check YouTube?
It's my
Select the other screen
It's good.
and click X.
Click X. Got it.
Perfect.
Yeah.
Thank you so much.
Hi, everyone. So the next speaker is Jinkyu Jeong. He's an associate professor in the Department of Computer Science at the Yonsei University. He has written one of the papers that inspired me, a case for hardware-based impact phasing, which I really like. He received his PhD degree from the Korea Advanced Institute of Science and Technology, and his advisor was Moving. And his bachelor's degree from the Yonsei University. He has lots of nice work in operating systems and memory management. And the stage is yours.
Yeah, thank you. Thank you for the introduction. Can you hear clearly? Is it good? Yeah. Before we get started, I'm happy to see this top tier conference being held in Seoul as a Korean. Actually, last week we had another top-tier conference, SSP, which was also held in Seoul, and I'm happy to see you guys come and have great conference here. Thank you.
If you want.
So, I'm here to present a case for hardware-based demand paging, which is about performing page fault handling in hardware instead of operating system. And actually, this is a 5-year-old research, but I gave this talk and give some more details of this one because I have heard that it will be used in the showcase of the Virtuoso framework. And if the Virtuoso is made in 5 years ago, then my life would be easier because I did a lot of trouble when building this system. So let me give you this talk. So actually, the slides have basic stuff of virtual memory and handling page faults, but actually Konstantinos gave a brief overview of virtual memory systems, so I will skip some basic ones. But the demand paging is the core of virtual memory, and it loads memory pages on demand. So the figure to the right is a typical figure process showing how to handle page faults in modern operating systems, and the figure is already you are familiar with this figure because this one is already shown in many operating system textbooks. And we also know the benefits of demand paging because we can use less memory, we can perform less I/O, and we can make process running faster, and we can host multiple processes. So let me show how the page fault is handled by the operating system. So when a process wants to access the virtual memory, so it will give the virtual address to the MMU of CPU. Then if the page table entry of the virtual address has present bit 0, then it means the page is not resident in memory. So we say that's a page miss. Then the CPU traps the operating system, and the OS page fault handler is invoked and handles the page fault. So it brings pages, it allocates pages, and if necessary, it performs disk I/O, so bring the data from disk to memory. Then after that, the OS kernel resumes the process. So this is a typical process of handling page fault. So this process is used to populate disk pages on memory, and it's also used to populate anonymous pages like a stack and heap pages on memory. And in rare case, when an invalid memory access occurs, then the page fault operation also occurs, then the OS tries to kill process if the memory access is invalid. So this page fault-based demand paging is a de facto standard way implementing demand paging on modern operating systems. But the problem was that this figure is actually also familiar with you guys. This graph shows the latency of computer components in computer systems. So it's well known that disk is much slower than memory and CPU. So there are several orders of magnitude. Disks are several orders of magnitude, and CPU or DRAM. But since the introduction of flash-based SSDs, you can see those in the figure here. So the latency of disk has been reduced a lot. And recently, we say the ultra-low latency SSDs have introduced. So their I/O latency is some tens of microseconds. It's way faster than typical previous generation flash-based SSDs. So this reduced the gap of between the disk and CPU. So because the device is getting faster, it's already known that the software overhead will become very high, gets higher. So this figure also shows the I/O latency handling, delivering disk I/O. So in this figure, you can actually this figure from Hot Chips 2013, and Intel has already estimated the bigger overhead of software parts with faster storage devices. So you can see here that with future memory, the software overhead, you can see the software overhead here in red, and it accounts for more than half of the total I/O latency. And the big up to the bottom is our measurement. So in our lab, we did measure the I/O latency of with these 4 different devices. And you can see here that here we have 2 ultra low latency SSDs. Here we have Samsung Z SSD and the Intel Optane SSD. And as you can see, the device time is shown in gray, and the user and the kernel part, which are the software parts, takes from 30 to 50% of the total I/O latency. Got it? So it means that the bottleneck is shifting from disk I/O time to the software. So this graph shows the breakdown of the latency handling a page fault. So when a page fault exception occurs, then the OS kernel does some operations like identifying page table entries causing the page fault, and allocate pages and pass through the I/O stack to access the disk. So after that, the disk will perform its I/O operation, reading data from flash media and bringing back to doing DMA to the main memory. After that, the interrupt will raise, then the OS kernel will perform the context switching and do the I/O compression operations, and it will update the page table entry and finally resume the application. So the gray part means the I/O latency, and the other part means there's overhead associated with disk I/O during page fault handling. So this part accounts for the 76% of the disk I/O time. It means the overhead is getting bigger and bigger. And the page fault handling also brings some hidden costs. And it's well known that frequent intervention of exception handling causes architectural resource pollution. When user instruction is executed by CPU, then the CPU components like predictors and data caches can have the user space data. But whenever exception occurs, then those components are polluted by the execution, some traces caused by the execution of OS kernel. And you resume the instruction, then the data cache and predictors will be filled with user space once, but I guess polluted again. So this results in the drop of IPC and increased caching and so forth. So the point is that the page fault handling overhead is getting higher because of the introduction of low latency SSDs. So when I was preparing a West Coast lecture, I read some part from a well-known OS textbook, why hardware doesn't handle page faults. And the author gave 2 reasons. First, the page faults to disks are too slow. So if CPU handles the page fault, then it gets long because of the long store the CPU is doing idle for a long time. But it's not true anymore. I mean, disk is getting faster. And the second reason is that the hardware, the CPU, would have to understand the swap space. It means when the CPU handles the page fault directly, then it needs to understand the layout of disk because it needs to locate the desired page from disk. So because the disk is getting faster, our trial was what happens if the CPU handles the page fault directly? So if so, because we've seen the 2 overhead, like the software overhead in page fault handling, then the architectural pollution, resource pollution during the exception handling. So if we do handle the page fault directly in CPU, then we may be able to eliminate the software overhead of demand paging, and we can also reduce the architectural resource pollution. So our proposal was hardware-based demand paging. So the CPU handles the page for2 directly. So the thing happens like this. The application accesses virtual memory, but if it's a page miss, then instead of issuing, making the page for the exception, the CPU issues the IO request to the disk directly. But to implement this one, we have several challenges. The first one is how the CPU knows the location of the page on disk. Actually, the data we want to access on disk is a file. It means the file is the disk layout is organized by file system, the operating system kernel. So it means the CPU, if the CPU doesn't get any help by the kernel, then it couldn't locate the desired page on the disk. So our solution is LBA augmented page table. So the page table is extended to be augmented with the logical block address. So the LBA means the location of the page on the disk. So by putting LBA on page table entry, whenever the CPU wants to locate the location of the page, then you can use this. The second challenge is how the CPU can handle the I/O protocol, the disk I/O protocol. To this end, we introduce a new component, the CPU, that's called the storage management unit. So it resembles, actually the internal details are totally different from MMU, but it performs the storage protocol related operation. The last one is that we are doing demand paging by CPU, and it's done instead of the operating system. It means one of the important role of the OS kernel is to manage the resource, manage the physical memory. But if the CPU performs this operation directly, then you also need to do some resource management rules. You need to take some resource management rules from the OS kernel. So for this, we put the hardware OS co-design to perform some part of the demand paging in CPU directory and some other parts in the OS kernel. So our hardware-based demand paging has two different parts. One is architectural extension. So we have LBA augmented page tables and storage management unit. And the other part, we extend the OS kernel to support the hardware-based demand paging. So it performs three operations. First, it provides three operations: fast file and map, and updating the OS metadata for hardware paging, and managing the free page queue. So let's take this in detail. The first one is LBA augmented page table. So the goal of this component is to make CPU understand the storage layout by putting LBA in the page table entry. So this figure shows the typical 4-level page table structure, and for each page table entry, when the present bit is set, then the entry contains the page frame number and the protection bits. When the present bit is 0, that means the page is not resident in memory, so the other part of the entry is ignored. So we know that. So we introduce an additional bit, which is called the LBA bit. So when the bit is set, that it's called the LBA augmented page table entry. So for PTs whose present bit is 0, we put another bit, LBA bit, and if this bit is set, then the first three parts specify a unique location on disk. So it will locate the page in disk. And you also put protection bits here. The reason is because the CPU handles the page fault operation directly. So after that, the page will be resident. So it will get accessed directly by MMU. So we also need to put the protection bit here, because after the page fault handling, the system needs to provide the right protection to the page. So we put protection bits here. So with the LBA augmented page table, when the application accesses a virtual memory and its page miss, then if the page table entry is LBA augmented 1, then the CPU performs IO directory and update the page table entry like this. Put the page frame number. So it means the hardware allocated a page and bring the page to this data from disk to the, and put the page frame number on the PTE. Also, it set the present bit to 1. It means now the MMU can use this one to translate the virtual address, to perform the virtual address translation. But at the time, this entry has some missing part. It means from the virtual address perspective, it's correct one, but from the OS perspective, the page is used but is not accounted in its resource management. For example, the OS hasn't done the resource accounting, and the OS kernel didn't perform any metadata updates. So this PTE is actually incomplete. So after that, the OS needs to do some more things to make it right one from the perspective of OS. So after that, the PT becomes the conventional PT like this one. So actually the LBA bit here is used to identify the PTs who are not done the OS related metadata update. So I will talk about this later, but the point is that the CPU performs the page fault operation, then after some time, the OS kernel do perform metadata updates lazily. With this LBA augmented page table, we introduced another unit in the CPU part, and that's called the storage management unit. So do I have 25 minutes?
Yeah, you have.
Okay, got it. Yeah. So the SMU here, this is an architectural component and the page missing hardware. So it has two components, internal components. One is page miss handler, and this handler handles each core's page miss status, and it allocates pages, and it issued disk IO to the neighboring component, NVMe host controller. And it also raises an exception if there is some problem like the free memory shortage. And the second component is NVMe host controller, and it handles the NVMe disk IO protocol. Here, the NVMe protocol. So let me tell you a little bit more about the page miss handler. So the SMU just show the components across cores in each chip. So it handles the page miss handling status. And that operation is actually very similar to the typical cache miss handling. So in the CPU cache, we have a register called miss status holding register. So we make another component that's called the page miss status holding register to and update the control the status miss handling. So each row in this register contains the page mishandling status. So for pending page misses, we have an entry in this register. So by using, we can query duplicated page misses in this component. So when a core causes a page fault, then it will send a request to the page miss handler. It first to look up the PMSHR. Then if there's then we PMSHR miss occurs, then the page Prefetcher, Prefetcher access the free page queue to allocate an entry. So you allocate a new entry like this, then it issues the IO request to the bottom part of the NVMe host controller. Whenever then it updates the page table entry, and then it removes the entry of the PMSHR, then it broadcasts the completion to the cores. And the next part is NVMe host controller, and of this component is a little bit more simple. So because the disk is actually shared between the OS kernel, the software, and also the hardware, the OS kernel is in charge of allocating an isolate NVMe command queues pairs, a pair of command queues, and the queue pair is dedicated to the CPU hardware. So the NVMe host, during the boot process, the OS kernel updates the NVMe queue descriptor register to assign a command queue to the NVMe host controller. After that, whenever the host controller receives IO request, then it puts the IO command to the memory. So actually, the way to handle this protocol by CPUs gets easier because of the introduction of memory protocol, because this protocol requires the access to memory, and it requires only a final updates on the PCI IO register. So this simplifies the operation of issuing IO commands to disks. So whenever host controller receives IO request, then it creates a new command and put that into the submission queue in memory. And when IO completion occurs, then it will get the IO completion message from the completion queue and pass the completion message to the upper part. And to identify whether command completion occurs, then we take a little bit a small technique that's snooping on memory, because to detect the completion of IO requests, one operation is using interrupt, but interrupt is not what we want to do. So we instead snoop on memory, a certain physical memory range which contains the completion queue. Then by doing so, we can avoid the high overhead of interrupt delivery. Oh, time is running. Yeah. So let me do 5 minutes. Okay. So the other part of the hardware-based demand paging is operating system support. So the first one is fast file mmap. So actually, the reason we introduced this fast file mmap is because our page fault handling process has some shortage. It means when the file is shared between multiple processes, then it will cause some complicated problem like page alias problem. So to avoid this, we introduced this interface. So when application or the kernel is known that this is safe to use the hardware-based demand paging, then the application can use this interface, mmap hardware DP, to declare this certain memory region is for hardware-based demand paging. So during the operation, the OS kernel populates the page table entries. If pages are found from the page cache, then it put the pages in the PDE. If the pages are not found from the page cache, then it consults the file system to get the LBA of each file page, then put the LBA in the page table entry. So by doing so, the CPU can know the location of pages on the page miss. So next part is updating the OS metadata for hardware paging, because after the SMU handled the page miss, still the page is not correct. Page table entry is not correct one, because the OS kernel doesn't know whether a page is used for assigned or allocated the page to a process. So this condition, LBA bit set and present bit set, indicates that the page is handled by hardware, but OS didn't catch up. So we introduced a background daemon called KPTD, which scans page table entries and identifies these such page table entries and to perform the OS metadata updates. And the last part is free page queue. And because free pages are managed by OS kernel, so the SMU also needs to know which pages are free and can be used during the page mishandling. So we make a shared queue between this SMU and the OS kernel. So OS refills free pages and the SMU consumes the pages. So this outlines the summary of the demand paging. The OS-based demand paging occurs like this. Whenever a page miss occurs, kernel part performs, which is shown in blue or light blue, and the IO operation, then OS metadata updates occurs, which is shown in red. But in our hardware-based paging, the file system part occurs at the very beginning of the operation. Then on every page miss, we do just IO and do usual instructions. Then the metadata management parts are done in background. So by doing so, let me briefly show the evaluation region. So let me skip this. So this part shows the page fault handling latency, single page fault handling latency, and as you can see, hardware-based demand paging has reduced the IO latency by 43%. And the next slide shows the evaluation results, the end-to-end application performance. So we tested several applications, synthetic benchmarks, and YCSB crowding benchmark workloads. So we achieved up to 27% in realistic workloads. And all of the downside of using hardware paging is that the CPU stores for a long time. So it means the pipelines are idle for a long time. So for that, if we can exploit the SMT feature, then we can increase the CPU utilization. So this graph shows that if we collocate IO threads with CPU intensive ones, then while the IO intensive ones are performing hardware paging, the CPU part can utilize the idle pipelines. So we achieve both the performance improvement on both sides. So the last one is actually I didn't show up this result and I made this public, but we prototyped our hardware paging using FPGA and we achieved similar performance improvement. So yeah, let me skip this slide because we have some Q&A time. So yeah, it's so done. Yeah, that's good. I hope to take questions.
Any questions?
Hello, my name is Sungho from DJs, and I have one question about LBA augmented page table. Since multi-level page table is used, page tables are not created for all virtual address. In that case, how we can determine the LBA of a VA that belongs to a page table which not has been created?
Okay, so the demand paging happens also on the page table. So if we perform ML operations, then the typical OS operations is that they don't populate the entire page table. But in our hardware-based demand paging, we do that. So we pre-populate all the page table entries. So that's why we have introduced the classified mmap. So for that reason, we populate page table entries. So it creates some space overlays, but that's not that big.
Thank you.
Any other questions? Yeah. You can take a minute.
Okay, thank you. My name is Wang. Okay. My question about the SMU. I think from my understanding, it's a hardware unit, right? So it is shared between multiple cores or it's private to each core?
So your question is what happens if multiple cores issue page miss on the same entry, right? Then how can you deliver the notification to multiple cores, right?
Sorry, my question is for SMU units. My question is it's shared between multiple cores, private for each core.
So your question is about how to deliver notifications to each core, right? So actually, I don't have an expertise in hardware side because this work is joint with the colleague in SNU. But we did the delivery of notification using this one broadcast. So whenever an entry of the PMSHR completes, then we deliver completion notification message onto the interconnection network. We do broadcast. So any cores who are interested in this mishandling can notify the completion of the page miss.
Sorry, so for each server, we have only one SMU, right?
I'm sorry.
We just need one this unit.
Yeah, so SMU is shared across course.
Okay, so maybe it will be the risk of bottleneck, I think.
But
Sure.
you know the every page operations to prepare.
Yeah.
So you-
This unity.
So you want to know whether the PMSHR becomes the bottleneck when it's shared between multiple cores, right?
Yes.
But the overhead, actually, the latency of handling a single page miss is in the scale of nanoseconds. So it may serialize the handling of page misses occurred on multiple cores simultaneously, but the serialized part is not that big. And it issue a request and handle the next one. So the bottleneck is not big.
Okay, so next question is about do you do some overhead analysis for this unit? For example, the area or the
In the paper, we have some analysis on the area overhead or something like that, but not that big because in the paper, we have some details of how many entries in PMSHR and PMSHR is actually CAM content reserve memory, but we had the analysis and please refer to the paper for that overhead analysis.
Thank you.
Thank you.
Thank you, Mickey. Yeah, I have one final question, please. So the first part is, how do you distinguish on the fly whether a page, the virtual address access basically, is backed by a file or not?
So that's another region we introduced the fast file mmap. So
I see.
yeah,
So that's why you need to repopulate the
yeah,
whole page table.
yeah,
So-
yeah.
But I guess you could do this in a different way, right? Like you could, for example, store information about the VMAs to figure out on the fly whether the page is file backed or not, instead of repopulating the whole page table. And the second question is, when you update the page table on the fly, do you have any synchronization primitives so that the page table does the OS, the software OS does not update the page
Yeah.
table on the fly? Like that's
Yeah.
quite hard because you need to somehow communicate all the logs
Yeah.
about the page table
That's right.
down
Yeah.
on the OS at the
Yeah,
hardware, right?
yeah. So during the talk, I gave one clue about that. The reason we introduced fast file mmap is because we want to avoid complex things.
Yeah.
By using the fast file mmap, it means the OS can notify whether this part is shared by multiple processes or not. So if the file mapped through the fast file mmap is used in another process, then the OS can do some other things to do synchronization like this. But if the file is not shared by multiple processes, then things
Then it
get
won't
fine.
happen. Yeah.
Yeah, that's right.
Okay, let's take the speaker.
Thank you.
Okay, how about now?
Next speaker is Dimitris. Dimitris is also the Carnegie Mellon University. Because I think so much very rebound, I would say. And it has also been a source of my creativity as like here. Start with a list of awards he has, and I will not stop. So I will give you stage and all these awards come because of your research.
Thank you for the very warm introduction. Happy to be here. So let's get started. I'm going to talk a little bit about the one abstraction to outlast them all. I think it's true, even if it actually we stop using virtual memory today. I think that's still going to be true. But let's get down to it, and I'm going to hopefully go over some high-level motivation of why this is important. So if we look into the power consumption of data centers today and how the trends have been evolving over the past 10 years, we're going to realize something very interesting. First is that servers are a major source of power consumption that is going up increasingly over the years. And the second part is that if I start plotting also GPU servers and AI, basically accelerated servers, things are getting even worse. Actually, in 2024, the growth of AI servers is 1.7x year over year, and things are getting much more, at least projected to get much more involved over the next few years. Just to get a sense, by 2028, what we're expected to see is that the power consumption of data centers is going to go and surpass actually that of Japan. We're closing actually the 1,000 terawatt hours, basically. So this is a very important problem. And architects and we in the community have actually quite a lot of capability to try to fix this. I'm going to show you here a quick breakdown between data centers and hyperscalers. You'll see that servers are really the bottleneck as far as power consumption goes. It accounts for about 75% in hyperscalers, close to 60% across all data centers. So clearly, we can optimize our servers to do a much better job, right? And with that short introduction of all of these problems, right, memory is about a third of the problem, and it's actually going to be close to half of the problem. So DRAM basically accounts for about a third of the server cost, monetary cost, but also that of power usage, right? And recent numbers have actually gone up quite a bit. We're close to 40% now and increasing. So here I'm showing a quick plot. On the y-axis, there is the infrastructure, the percentage of infrastructure, and you can see over generations of hardware, this is numbers from Meta, about 33% of the cost is really DRAM. There are a few alternatives, right? There is compressed DRAM and perhaps even SSDs. SSDs are becoming faster, as we were just talking about. So things are promising on that we can actually do quite a lot of things by using all of these resources together. And that's one of the works we did recently that is now in production in Meta across the entire fleet. It can help manage these resources like both DRAM, compressed DRAM, and SSDs. The result is offloading about 20 to 30% of the memory across many, many workloads to alternative memory tiers, right? And this is a huge capacity saving as well as potentially power saving, right? Things are going to become much more interesting with CXL. Now we have even more tiers, more options to offload, and we need really systems that are able to handle all of these different types of memory and how to integrate them into the system. So this is what we've been doing, but as you can see, as the infrastructure cost goes up, it means we have much more memory capacity, right? And as you can see, as memory capacity increases, right, we started with a few tens of gigabytes. We are now in the hundreds of gigabytes. Many production servers today are in the terabyte range of memory capacity, purely driven by AI workloads. There is going to be a problem. And obviously, this is a virtual memory talk. So lots of our problems, or the virtual memory wall, if you want, or the virtual memory bottleneck, is actually originating from the fact that we cannot really scale our TLBs anymore. So even if we aggressively keep pushing the number of entries per TLB, we still see that today, even state-of-the-art servers are bottlenecked at about 3,000 entries, which is clearly not enough to cover the memory capacity in servers, right? Architects have been working on this for quite some time. In a state-of-the-art system, we will see something like this. We have multiple TLBs now, a hierarchy of TLBs. We have a very large TLB of thousands of entries. We have MMU caches that cache translations from the radix page tables. So we try to cut the number of accesses we need to do to main memory. And also, we do have translation entries in the caches to accelerate the work. The thing is that if you just quickly do a simple analysis, you'll see that the TLB cycles have already surpassing that of the L2 caches, right? So it's really hard to scale the TLB for much more without paying an even higher latency. So the result of all of this is that despite this amount of work in architecture and in our community and in hardware, about 20% of the cycles are actually spent on page walks, and this is according to our study at Meta, and Google reported similar numbers in their infrastructure, right? So memory and virtual memory is becoming an increasingly important problem to work on, and we really need to find solutions, right? As we were just talking about this, CXL memory is going to increase capacity, so that is a major additional memory overhead that's going to come along our way, which is going to keep going like this, basically. We cannot really scale our TLBs. If I go and talk about VMs, forget about the 4 memory accesses per translation, we go to 24. This becomes even worse. We have to keep chasing points. And in confidential computing, there is even additional overhead through additional metadata structures we need to actually check in every access for a translation. Finally, we have already moved past 4 levels of page tables. We went to 5. So the actual page walk latency on the worst case can be very, very expensive, right? And lots of work has focused on one simple concept, and they've used it in different ways, and that is physical memory contiguity. So what is physical memory contiguity? It's basically the range of free space in memory that can be used for memory allocations, right? The larger the space, the better for us. So if this is the physical address space, and these are different pages, this, for example, is available contiguity, right? And we can create larger mappings. We can use this contiguity for many, many ways, right? And just to give you an example to highlight how we used contiguity in the past, actually more than 25 years now, is the following. Let's say that physical memory contiguity is a tree. We started with huge pages. This goes back, for example, to Talluri and Dave Patterson in '92. Lots of work on huge pages on how to use them, from simple techniques to even using machine learning to improve their usage. We use contiguity for range translations. So this is multi-gigabyte range translations, quite a lot of basically backing a lot of data with a single huge translation. Even more, some of the work also we did on hashed page tables, so alternative designs to reduce the amount of memory access needed per page walk, at least to break down the sequential part. And many other implicit use cases, right? I'm not going to go over all of these works, but as you can see, pretty much every single work on virtual memory is trying to use some form of physical memory contiguity to reduce the address translation cost. So the natural question is there physical memory contiguity in data centers, right? In a real production setup, can we actually find these large mappings, or are we doomed, right? So we went at Meta and we looked across a large portion of the servers across the fleet, and we found out that servers are highly fragmented, okay? This is very challenging because first, the surprising result that we saw is that a quarter of the servers don't have enough contiguity for even a single 2 megabyte page, right? So that idea of allocating huge pages kind of goes away. And there is no question about allocating 1 gigabyte pages, right? This is very difficult to do dynamically in production. The interesting fact is that this is from another paper on SDI, again at Meta. If you see here, this time scale shows the time it takes to activate different features. On the very far side, you'll see that it takes actual minutes to activate huge pages. So why is that? Servers are so fragmented that they have to be rebooted before a job can actually land on them, right? So this is very, very expensive and definitely not practical, right? So how do we fix all of this? Because if we don't, without physical memory contiguity, well, all of this work goes away, we cannot really use it, and the address translation overhead will remain very, very high, right? So part of our work has focused on exactly this problem. It's called contiguitas from ISCA 23. And the focus of it is, okay, what is the problem with contiguity? How do we find it? A big aspect of it is that unmovable pages that the OS cannot move around, and they are fixed at allocation time, and they can be basically I/O pages, either from networking, RDMA, GPUs, or accelerators. They actually block defragmentation from taking place, and you are stuck with these pages, and as a result, you cannot form continuity. So what we did is we actually went back to the OS, back to the basics. We redesigned the address space such that we can separate movable from unmovable allocations and maximize continuity as much as possible. We further went down to the hardware, and we added quite a lot of support for unmovable page migration. So of course, in hardware, we can do anything we want, and that's what we did. We can actually have a page that is pinned, move around, and leverage cache coherency mechanisms to do this as efficiently as possible without any overheads propagating up to the applications. The result of this is ample physical memory continuity. Even with the software alone, you can get quite a lot of physical memory continuity, close to 90% of total memory. And if you actually use this continuity, as we saw in production workloads at Meta, we saw that there are real performance gains of 2 to 18%. Right? If you think of millions of servers using these fixes, this is quite a lot of performance gains and power gains as well. Of course, the hardware can help even more. We had lots of discussions with different vendors, and I'm happy to announce that this is now in Linux. It's not the full version. We had to make some compromises, but quite a lot of these patches have landed. They are available as of 5 recent Linux kernel anyway. Have to check the version, but they're available, right? So you can go check them out and see some of these improvements even on your own setups. So okay, we got our physical memory continuity back. Lots of use cases. We can do quite a lot of things, right? And we can actually even think of new directions. So how does that look like? So going back to the root of all our problems so far is that we have radix page tables. We really don't like them. And we want to replace them, right? So what are the alternatives here? So one of the works I've been focused a lot in the past is about hash page tables. But unfortunately, if you quickly look at them, there are some major problems, right? So global hash page tables do not work efficiently. This is an old approach. Intel has deployed them. IBM has deployed them in real hardware. And the idea is that you have a virtual address from the application going to the hash table. You found your entry. But because of collisions, right? Collisions are a big problem here. And you actually have to sequentially perhaps walk entries in the page tables to find them, right? So collisions are a big problem. You need to invoke the OS to revoke them in many scenarios. That was happening in older systems. So if we were to take notes of what does not work in the setup is actually collisions, right? If I take this away and I keep thinking about hash tables, how about sharing pages, right? Or how about multiple page sizes, like 2 megabyte pages that now we can use? That would require having control over how virtual addresses map to the hash table, right? As you know, this is not possible to do. You have a hash function. You cannot control it. And as a result, the only solution to all of these problems is a new level of indirection. So slowly, step by step, we're going back to a design that has quite a lot of pointer chasing, right? So I'm going to keep writing them down. Page sharing, page sizes, all of them are problems. And if this looks like a dead end, it does. It didn't work. And both Intel and IBM switched to radix page tables. So this is how we started. This is how we got stuck with this problem. And this is a work we did. We kept continuing building on top of it, addressing different aspects over the years, from ASPLOS all the way to OSDI past summer. We introduced elastic cuckoo page tables. It's an idea that we actually can use a cuckoo page table design and make it elastic such that we can resize it dynamically. The main idea is that we no longer have sequential page walks. We don't do this pointer chasing process. We can fix the number of actions we need to do in parallel now, always, even if we are resizing the page table. And finally, we can use out-of-order processors to leverage performance and out-of-order memory accesses to hide the sequential page walks. So this is how they look. They have multiple ways. We spread the page tables across them, and we can access them in parallel, right? So lots of benefits. We got quite a bit of performance, and one of the key ideas here is that because we have to go across multiple page sizes, and we might require multiple accesses, one per page table of a given page size, we had the secondary structure that we were caching, similar to what page walk caches do, in order to reduce and prune basically the parallelism, right? Otherwise, we would actually hammer quite a lot on the memory subsystem for accesses. So we can remove some of them and end up with a simpler system. But if we go back to the basics and we try to understand the fundamental mechanics behind ECPT, we're going to see that there is a very simple trade-off. Radix has a sequential page walk, and we trade off that latency with bandwidth, and we do multiple memory accesses in parallel, right? And in some cases, we might have to do more because of multiple page sizes. But if we pause for a second and we think of what we want to achieve, our goal is, in a perfect world, to do translations or page walks with a single memory access, right? That is what we want to achieve. That's why everything is happening. So how do we get there? So this is a quick preview from our talk on Wednesday. And we are trying to transition now from hash tables, where you have a key virtual address, for example, you go to your hash function, and the goal of a hash function is to spread, right, your keys across your space and try to avoid these collisions in basically different positions. The problem is that even for a very low occupancy, like let's say 60%, you have more than 20% of your accesses being collisions, right? And that's why in our previous work, we went for a parallel design where you access all of these elements in parallel. An alternative way is called a learned index. It's a recent data structure. It came actually from databases. And the idea is that instead of having a hash function, we're going to actually learn now a function dynamically based on the key space. And the idea is that if the key space is regular, which means that it has a very nice pattern, for example, think of sequential keys, right, one after the other, then the collisions is very, very low. It's like 1%. And this is a great idea. It starts out of databases, lots of controversy if it works or if it doesn't work. And the reality is that database workloads, like key value stores and everything else you might think of, is not very regular, right? The keys can be all over the place. You have to support insertions. This becomes quickly problematic. So instead, we went back, and this is a bunch of workloads across many, many setups, and we looked into virtual memory and the virtual address space. And we quickly can realize that the virtual address space is very, very regular, right? This is private to its application, and it tends to grow, right, sequentially, one page after the other in sequence. Like when you're allocating memory, you're getting consecutive virtual memory pages, right? Again, we've been using huge pages. They require physical memory contiguity, but that doesn't mean that applications on the virtual address space are not contiguous, right? So the virtual address space is highly regular. As you can see here, the results show that you can map most of the address space perhaps with a single function, right? The result is that there is definitely a clear path of using learning indices and have low collisions, right? So how do we do that? So there are a lot of challenges that we figured out after this initial study, right? We can show that there is regularity, we can reduce the collisions, but can we use learning indices from databases for virtual memory? The first major problem we found is that actually the learning index itself is represented as a tree of multiple models. And as this structure reminds us of radix, it can grow both in depth and width. So it is very, very expensive to traverse, especially as it grows in size. So the first result that we found out is that learning indices from databases don't really fit virtual memory because they can be very, very large, megabytes in size, so we cannot cast them. They can grow uncontrollably, both in depth and width. It doesn't really fit what we want. So that was a major problem. Furthermore, we found out that previous approaches, they were not really supporting insertions, or they were getting very low accuracy, or they had to retrain quite often, and that was very costly. Right? When you are creating a new entry, you don't have to create and retrain your entire learning index structure to reduce the cost or actually maintain high accuracy. So that's another very important problem, which is insertions. And as you know, in page tables and virtual memory, you do add quite a lot of pages dynamically to your address space, and also you remove. A third problem is that we want to support multiple page sizes, right? We want to have 2 megabyte pages, maybe 1 gigabyte pages. And if we have to maintain a separate index for each one of them, this again becomes a problem of multiple memory accesses that we want to avoid. The problems don't stop. The other piece is that these structures are designed in databases. They're in high-level software, so they require large contiguous allocations. So again, problems. We cannot allocate our page tables to be very, very large, so we have to take into account available contiguity. Contiguity does fix that, but again, you don't want your subsystem, like the virtual memory subsystem, to rely on contiguity a lot. Finally, they require quite a lot of compute. They are not easy to compute. Some of these functions that they use are actually based on deep neural networks. They can be very expensive. You don't want to be computing a very complex function, even with floating point units, in the bottleneck to address translation, right, in your TLB. So that would be very expensive. So talking about dead ends, this definitely looks like one. Quite a lot of problems. The good news is that we did address all of them. This paper is going to appear on Wednesday. This is a learning index for virtual memory. It adapts dynamically to the application's virtual address space. High-level picture of how it looks like. Basically, you can take the address space of applications and use simple linear functions to map it. And we found out that you can actually do this quite efficiently and quite fast, and then get single access translation to your page tables. So they're small, about 200 bytes, very compact models, efficiently map new pages and support huge pages. Actually, they can support any page size you want without requiring multiple indices, and they do not require large contiguity. So we addressed all of these problems. We did have to do quite a bit of code design, so it kind of fits the theme of the workshop. But overall, we got major speedups, reduced the translation overhead, and also the page walk cache area itself in hardware. So we did the RTL synthesis, and we saw that LVM is actually much more efficient than Radix page tables themselves. And the final result is that we are within 1% of an ideal page table design that performs a single access all the time. If you want to hear out more, please come to our talk on session 9B on Wednesday. If you're still here, hopefully at 10 a.m., we're going to be happy to discuss more. So with that, I think I still have some time. Let's go over a few things that represent the core of virtual memory, and this is some of the concepts that I have covered over the years. There are three main concepts of virtual memory, some debate to that, but there is address translation, there is memory management, and there is security and isolation. And in my view, this is how I started back in 2017. That was the first paper I worked on as well, PageForge. It tries actually to perform deduplication, actually sharing of pages to reduce the memory pressure. That was the beginning of the journey. That led to security and isolation with Microscope, basically how to use virtual memory and exploit speculative execution to perform attacks, side channel attacks on hardware. And all of this work on memory management and virtual memory led to ECPT. Okay, there is a big problem in performance. Why don't address that? So ECPT came to be in that sequence. And then it kept building on top of this direction, right? Pageseer and Bubblefish actually use the memory management semantics to share translations and reduce and give hints to the memory subsystem to fetch pages ahead of time. We did defenses in silos, for example. We use memory management and virtual memory to isolate domains for Rowhammer. And then we kept building actually on ECPT, how it works in nested environments, how to make it memory efficient and not require lots of contiguity. We went back to memory management. We tried to actually fix now the problem of offloading pages. In Memento, we reduced the actual cost of allocating pages and managing the address space. And we did this in hardware. We went back to security, and we thought of, okay, how do we actually create domains to protect against Spectre attacks? The kernel. And we continue, of course, on the address translation path of improving the contiguity problems, how to actually use contiguity for translation to reduce the translation cost. And all of this work basically led to a paper on SDI past summer where we create OS abstractions for different page table designs. And finally, LVM, that is going to be in Micro today. So it's a long journey across three directions, going all over virtual memory and keep finding problems and trying to improve them. But I think that still we're not done. There's lots of problems, quite a lot of work to be done in this space. I think this is common. We've seen this a lot. It's memory. It's going to be memory. It will always be memory. There's going to be 6L interconnect, right? It's very important. We're going to have lots of problems there with additional capacity. We have lots of heterogeneous compute, GPUs, accelerators, processing in memory. All of this goes without saying. They're going to complicate memory management and address translation and also security. We have computational computing, additional costs. We have now cross-vendor computational computing. We have to think of GPUs and how all of them come together. The whole subsystem of protection relies on virtual memory, so it is at the center of it. And that is not done. We actually now move into heterogeneous memory itself. I'm not sure if you've seen the news of HBF coming out soon, apparently. So things are going to be very, very interesting. We'll have to work on these problems and try to address how do we move forward in the memory subsystem. Of course, there's lots of work. I'm not going to cover everything. If I just bring this up, basically, this is the work that my group has been doing at CMU for quite some time now. It goes all the way from the hardware to operating systems, and sometimes we touch applications. Some of them are in production at Meta. They have been upstreamed in Linux, and many of them are open source. So please feel free to check them out. How I'm doing on time? Great. So in the closing segment, I was talking a lot about the energy crisis of AI data centers. And I talked about the accelerated part. Now we have lots of GPUs. And this is the infra problem back in 2021 for me. I was working on this paper called RAS that does resource allocation at scale at Meta. And you see that on x-axis is different services. On the y-axis is failure domains. You want to see blue things. The more blue, the better. The idea is that a service can spread across different domains, right? And if it spreads, basically, if it goes down, you can actually reboot and start from somewhere else, perhaps, and all of these things. On the top side, on that service, you'll see that it's very red. This is what we don't want. And that service basically showed that GPU capacity is going to be a very important problem, because if you need GPU capacity and you don't have it, you are basically strangled in a few domains. So, whoever is reading that paper in 2021, they could have made an educated guess that GPU prices are going to go up. So read our papers, it's very important. So with that, I'm just going to go over a few things that we've been doing here. It's going to go dive back to memory management. GPU utilization is extremely low everywhere. At Meta, it's about 30% on device, 15% on streaming multiprocessors. This is also for Llama 3 training. It was about 40%. More details in our paper. Microsoft is at 52%, Alibaba at 10%, ByteDance at 26%. This is a real problem. We need to use this capacity efficiently. Otherwise, we're literally throwing away GPU capacity and burning money here. And energy. So this is a very important problem. We really need to figure out a way to solve it. And in my view, there is a bit of a retrospect here and quite a bit of a deja vu. So what is the role here of the operating system in the GPU era? This is a big question. How do we move forward? How do we build abstractions, long-lasting abstractions? And there is a relation basically to mainframes in the 50s and GPUs today. And that's the deja vu, actually. They're very expensive, they're very scarce, and they're single tenant, right? So we need to build abstractions, long-lasting abstractions, use efficiently, both in terms of compute and memory. So that's what we did, right? Operating systems can actually solve all of these problems. So a quick highlight from our work called Lithos, an operating system for GPUs. It's the first step towards that abstraction. It was presented last week at SOSP. It's fully transparent to the machine learning stack. It does require not any code modifications to PTX, frameworks, compiler changes, nothing like that. It performs TPC scheduling for the first time. We break down the abstraction of GPUs that are a single device. We manage now hardware at a very fine granularity, enabling stealing of resources between workloads. We perform many, many other features, like a kernel atomizer to support preemption, right sizing of TPCs, and also we provide transparent BVFS. The results are significant. We beat NVIDIA by 13x in terms of tail latencies, and compared to state-of-the-art solutions, two of them, by 3x on latencies and by 1.6x on throughput. And we can also save resources quite a lot with right sizing, basically defining the amount of capacity each kernel needs. We can reduce GPU capacity in general, and also reduce power usage by performing efficient DVFS. I'm not going to talk more about this, quite a lot of details in the paper. With that, I would like to thank my group. Some of the people are going to be here. Please talk to them. They've been doing this awesome work. And with that, I'm open to questions. Thank you, everyone. Questions? Yeah. So, 16.
you also have seen some system model processors is the one that it's the hardest one. People think slow eventually, trying to avoid it as much as possible. So, do you think it's one of the solutions that could reach the it's either in the applications or system. In order to achieve this co-design, like this contiguous reports, right? It's obvious that like offset-based cancellation can be very fast. But people are very against these approaches to specialize the operating system.
So this is a very good question. I've been thinking about it quite a lot. Actually, the moment we did the Elastic Loop page table work back in 2020, we went to Intel, we went to ARM, we presented the work. It's like, guys, this is great. You should do it. They said no. The reason is that they require lots of contiguity, right? And if you cannot allocate your page tables, what do? Radix page tables are very efficient. And that's what led to a lot of works after that to addressing this problem, right? A very real problem of contiguity. So contiguity has reduced this a lot. For example, LVM now does not require any contiguity. So I think that it's very important to understand what are the limitations from the hardware side. It's very difficult to make progress because you need to change the OS and you need to change the hardware. So sometimes, architects in one way, they want to be backwards compatible, legacy preserving, software is unaware of any changes, you just get some performance bump every few years. But the reality is that the only way to move forward is that we need to understand the software too. And some of the changes we're going to make, they will have to touch both. I think in my view, the way that things have worked so far out, for my research at least, is that you can do the best you can do in software, present the data to the hardware vendors, and say that, okay, this is the limit of software. You cannot do anything more than that. And maybe if we had this type of hardware support, things would be much easier. And then there is a back and forth. You take the hardware, you go back to the software, and you optimize that again. And I think this co-design is going to be required. Now, how do you convince the vendors? I think in some cases, it's important to think of ways that you can fix the system without really throwing away everything. But in some cases, maybe virtual memory is one of them. As the overheads keep going up, now we're at 20%. If we cross the terabyte scale capacity and we go to a few terabytes, I think it's going to go higher. I think the hardware vendors will have to reconsider, like if you think of I/O devices, that's a space where you can do quite a lot of progress because they don't have these legacy laggards, right? So new processor architectures, accelerators, I/O basically, all of these are promising because you don't need to support everything. You need to support a couple of use cases. So if we focus there, I think that we can easily convince at least that this is possible.
Any other question? So you unveiled surprisingly a lot of fragmentations in server workloads. And my question is, so it is difficult to keep contiguity. What is the limit of this contiguity scheme when it comes to performance for the server? Do we see some regularity in the virtual addresses, but is this enough? Or do we need something more of this contiguity schemes to completely activate the virtual address?
So there are a few interesting aspects. One is that with contiguous, we saw that the current situation is very difficult and very problematic. We do address quite a lot of it. I think there is a bit, way more ample contiguity now available, and especially with the patches upstreamed, I think this is going to get better. I think that we need solutions that are intermediate. They don't require multi-gigabyte contiguity. That's still a bit of a problem because of defragmentation itself. So promising research to be done there. But I think that if you have some elements of contiguity, I think that's doable now. So I can definitely hope to see solutions in that space.
Thank you.
Okay. What? This works. Let me share. We did it.
So our next speaker is Virtuoso. He's a researcher of the Huawei Zurich Research Center. He got his PhD from BSc in Barcelona. Classmates, basically. We're the same university. We got our degrees from the same university. And he has done some great work on the interactions of virtual memory and hardware prefetching and a lot more. Thanks. The stage is yours.
Thank you for the introduction. Hopefully you can hear me right. Okay. So first of all, I would like to thank Professor Mutlu and Konstantinos for inviting me to give this talk. And today I'll be talking about how to exploit interactions between virtual memory and hardware prefetching to boost our performance efficiency. A few words about me. As Konstantinos said, I did my diploma at NTUA in Athens, and then I moved to Barcelona for a PhD degree, and now I'm working on CPU microarchitecture for Huawei in Zurich. So these are the areas of research that I really like to do to work on. Hopefully, this will expand in the near future. But what I would like to point out is that all these works, you will see a cluster between virtual memory and hardware prefetching. And this is, sorry.
Can you share the correct screen?
What I'm sharing. Yeah. Can I share this? Yep. Good. It doesn't work. I see
Not
this.
yet, no. It's not the same screen yet. No. Yeah. Can I stop the screen sharing?
Stop sharing again. Wait. It needs special handling.
No problem. Doesn't work.
This? Yeah.
And now share the one you present. You know what to Zoom? Here, share. Can you do full screen? Is it possible to do entire screen?
The entire screen.
Yeah. That would be ideal. Just click entire screen here. Yeah, you click this. Just click. Yeah, exactly. And go back to slides and presenter.
I don't need presentation mode anyway.
Okay, and now you can click. Now it's fine.
Oh.
That's fine. Oh, that's fine for us.
Okay.
Yeah, perfect. Thank you so much.
Perfect.
And I will just do one more thing. So that it's okay. Thank you so much.
Okay. So after this small interruption, so these are the areas that I really like to do research on all these years. And what I want to point out is that there is a cluster between virtual memory and hardware prefetching, and this is where I will be focusing today to highlight that there are interactions between virtual memory and hardware speculation mechanisms that we can exploit and boost our performance efficiency. To do so, I'll be focusing on two key works, and I will provide a lot of information about them. And in the end, I'll talk about my vision about future microarchitectural designs. Before doing so, I will go briefly through the fundamentals, and I'll try to connect virtual memory with hardware prefetching. And I'll start with the memory wall. So everybody knows what is memory wall and refers to the discrepancy between CPU and main memory speeds. To reduce this processor memory performance gap, vendors what do is to employ hierarchies of cache memories. But guess what? It's not enough. They are limited in memory, in capacity. So they went through latency tolerance techniques. A very good example of a latency tolerance technique is hardware prefetching, which is the first building block of this presentation. So in a nutshell, a hardware prefetcher proactively fetches data blocks into the caches before they are explicitly requested by the core. And what I want to point out is that in the post-Moore era, where freelance due to frequency scaling is over, we can see that hardware prefetching, like advancements in hardware prefetching, dominate the IPC uplifts between processor generations. And I give a specific example in this slide from a leading CPU vendor, where it reports that 40% of the IPC uplifts between two processor generations are due to improvements in hardware prefetching. And this is huge. So the main takeaway of this slide is that we need innovation in hardware prefetching to keep pushing on performance efficiency. And this is a very good time to do research in this domain. The second building block of the presentation, virtual memory, I will briefly go through the fundamentals here because it was covered like multiple times during this session. So virtual memory doesn't come for free. Each memory access requires a translation from the virtual to the physical address space, which incurs additional references to the memory hierarchy, which makes the memory wall taller. So to reduce the address translation performance bottleneck, we employ hierarchies of translation look-aside buffers, or TLBs, which store the most recently used virtual to physical translations, translation caches that cache intermediate levels of the radix tree page table to accelerate page walks by reducing the number of references to the memory hierarchy, hardware page table walkers, multiple page sizes, many more. What I want to keep from this slide is that actually the memory wall the virtual memory makes the memory wall bottleneck, the memory wall even taller because of the additional references to the memory hierarchy, especially for translation-bound applications. Now let's take a look at contemporary microarchitectural designs. Of course, they are more complex from what I present in the slide, but what I want to point out is that as microarchitectures become more and more complex, a lot of information and a large amount of unexploited metadata flow around the microarchitecture and runtime levels that current designs do not fully exploit. And this is going to be the core objective of this presentation. So you can see these three works that I was involved in, and the main, they can be seen as examples of how to exploit specifically address translation metadata to improve cache prefetching and cache management. And for the sake of this presentation, I'll be focusing only on the first two to see how to exploit address translation metadata for improving hardware prefetching performance. So looking deeper in these two works, we will see that the first one, page size aware prefetching, what it's basically trying to do is to say modern OSs transparently support larger page sizes, and cache prefetchers placed alongside the lower level caches that operate with physical addresses, they don't have a notion of the page size information. So this work is making lower level cache prefetchers aware of the page size information, and it shows that it improves performance. The second work, which was a last year HPCA paper, exploits virtual index physically L1 caches to enable enable effective prefetching across page boundaries. And specifically, we saw that prefetching beyond page boundaries is sometimes beneficial for performance and sometimes it harms performance. And we propose a framework for designing effective page cross filters. But let's get started with the first work. As I said before, in most virtual memory implementations, the standard page size is 4 kilobytes, but modern OSs transparently support 2 megabyte large pages, which is the page size that we are focusing in this work. So what we observed is that lower level cache prefetchers operate with physical addresses, and they drive prefetching decisions assuming only 4 kilobyte pages. And more importantly, they don't permit prefetching beyond 4 kilobyte physical page boundaries because physical contiguity is not guaranteed. So doing so might open new side channels. The opportunity we observed is that if we limit our lower level spatial cache prefetchers to operate within 4 kilobyte physical page boundaries, this would result in suboptimal gains and would leave performance on the table when actually use 2 megabyte large pages, assuming that the prefetcher could be able to know this information. And finally, we observed that if we make these prefetchers to drive prefetching decisions, not only assuming 4 kilobyte pages, but also larger page sizes, this could actually give us the opportunity to identify more patterns. Long story short, this work, what it's trying to do is to make lower level cache prefetchers aware of the page size information and enable safe prefetching beyond 4 kilobyte physical page boundaries. I'll drive you through the findings of this work like very briefly. So what we did first is to measure, we got some applications from Spec and Gap, and we measured their memory mapped in 2 megabyte large pages. And what we find out is that most of them, they vastly use 2 megabyte large pages through their entire execution, which actually gives a hint that making lower level cache prefetchers aware of this page size information could boost their performance if we manage to efficiently exploit this information. The second thing we did is we went to a simulation infrastructure, and we used back in the day state-of-the-art spatial cache prefetcher, SPP, or signature path prefetcher. And we measured that 10% of its prefetchers are actually discarded due to the restriction of not crossing 4 kilobyte physical page boundaries when we actually knew that the block resides in a 2 megabyte large page. And this 10% is a very large number because if you think about how many prefetches are actually issued throughout the execution of a benchmark. The last thing that we identified is that if we integrate the notion of large pages in the design of a prefetcher, this might be useful or might harm performance. It will be useful because it will reduce the aliasing in the prediction structures of the prefetcher, and it will also give the opportunity to use more deltas for prefetching. But at the same time, it can be harmful when we have multiple small data structures with different memory access patterns residing in the same 2 megabyte large page. So to address our first finding and make the lower level cache prefetchers aware of the page size information, we propose the page size propagation module, or PPM, which basically operates as follows. After the L1D miss, we know the page size information, and we just propagate it through the L1D MSA chart to the lower level cache prefetcher. Now let's see how the prefetcher exploits this information. If the page size is 4 kilobytes, then the prefetcher simply stops prefetching at 4 kilobyte boundaries. And if the page size is 2 megabytes, then we give the opportunity to the prefetcher to cross 4 kilobyte physical page boundaries and up to 2 megabyte boundaries, but we don't force it to do so. We just give it the opportunity to do so, and if it has the confidence to cross the boundaries of 4 kilobytes, then it does. To address our last finding and integrate large pages in the design of a prefetcher, we employ a different version of the underlying prefetcher, which differs from the first one in only one aspect. It statically assumes larger page sizes for the prediction structures in order to drive prefetching decisions. Since this is sometimes useful, sometimes harmful for performance, we employ a selection logic based on set dwelling to dynamically switch between these two versions of the prefetcher. This selection logic it's like a small tweak over set dwelling, where we have leader sets for each competing prefetcher and follower sets that actually apply the dynamically best of these two prefetchers using a saturated counter. So to put everything together, the selection logic selects dynamically between the two versions of the prefetcher, and we use the page size information to make sure that no matter which prefetcher is actually enabled, we will enable prefetching only within the boundaries of the page where the currently accessed block resides. So regarding the evaluation, we considered 4 state-of-the-art L2 cache prefetchers: signature path prefetcher, VLDB, PPF, and BOP. And we evaluate 3 different versions of them over their original version that statically assumes 4 kilobyte pages. Their first version is the page size aware version that exploits the PPM module to make the lower level cache prefetcher aware of the page size information. The second one is their page size aware version that statically assumes 2 megabyte large pages to drive prefetching decisions. And finally, the version that relies on set dwelling to dynamically switch between the two versions of the prefetcher. Based on the results, you see that making a lower level cache prefetcher aware of the page size information, which is the blue bar in the slides, brings significant performance gains. But the version that statically assumes 2 megabyte large pages is not that good. It doesn't bring a lot of performance. And this is because it's suboptimal across different applications. But the version that uses set dwelling to dynamically switch between the two versions of the prefetcher manages to bring the best of both worlds and sometimes even more. And I would like to stress that these approaches are transparent to which lower level cache prefetcher we use. So in the original paper, there is additional evaluation that I'm not going to go through in this presentation. So in this work, what we show is that limiting our lower level spatial cache prefetchers to prefetch within 4 kilobyte physical page boundaries when actually 2 megabyte pages are used is suboptimal. And we propose a way to make them aware of the page size information and enable prefetching beyond 4 kilobyte physical page boundaries in a safe manner. And we also show that integrating the notion of 2 megabyte large pages in the design of a prefetcher may be beneficial sometimes, and we show how to make it work without harming performance. Now we go to the second work, which is entitled To Cross or Not to Cross Pages for Prefetching. In this work, what we observe is that hardware prefetchers that are placed alongside virtually indexed physically tagged L1 caches drive prefetching decisions with virtual addresses. So since they drive prefetching with virtual addresses, all these prefetch requests need to go through the TLB hierarchy before being issued. So for prefetches that hit in the TLB, the decision is very easy. We just issue the prefetch requests. But for those who are not TLB resident, then it's not that straightforward what to do. We can trigger a speculative page walk to fetch the translation to the TLB, but this would impact the TLB and the cache pollution if the page cross prefetch is inaccurate. But we can also go with the safest option, which is statically discarding page cross prefetch requests. But this would leave significant performance on the table when actually our prefetcher is able to accurately cross the boundaries, 4 kilobyte 4 kilobyte boundaries. So this work is actually motivated by a critical mismatch between academia and industry, where we see that in academia, most of the works try to propose more sophisticated prefetching algorithms that capture more and more in-page patterns than the state of the art, while industrial reports show that they are optimizing for both in-page and cross-page prefetch patterns. So this is the first work to bridge this gap, and we analyze the properties of page cross-prefetching across different state-of-the-art cache prefetchers in an academic environment. And we show that constantly permitting or discarding page cross-prefetch requests results in suboptimal gains. And we propose a solution that is able to optimize prefetching decisions across page boundaries. So first, I would like to highlight that static policies with respect to page cross-prefetching are suboptimal. To do so, I'm considering BERTI, which is the academic state-of-the-art spatial cache prefetcher, and I'm going to evaluate its version that statically permits page cross-prefetch requests over its version across a set of memory-intensive applications spanning various benchmark suites, over its version that statically discards page cross-prefetch requests. So what we see is that for some applications, constantly permitting page cross-prefetch requests brings performance, while for others harms performance. And our analysis reveals that this happens because a big fraction of the page cross-prefetch requests are actually inaccurate. And since this is a 2D speculation, since we trigger speculative page walks, this harms performance sometimes. The question we want to answer in this work is that, is there any way to dynamically identify the useless page cross-prefetch requests and filter them out? It turns out that it can be done, and it can be done using the MoCA framework that we're proposing, which is a framework for designing effective page cross filters based on hash perceptron prediction. In a nutshell, what happens is that the hardware prefetcher will trigger page cross prefetch requests, and they will need to pass the page cross filter in order to be issued, but sometimes the page cross filter will discard. So as I said, the MoCA framework is a framework for designing page cross filters based on hash perceptron prediction, and each page cross filter consists of different program and system features, as well as adaptive schemes that optimize decisions at runtime while using other structures that are necessary for correct updating the perceptron weights, I'm not going to go into the details of all these structures. You can find them in the paper, but we can also discuss afterwards. One thing to note is that we need 1 bit per L1D block to annotate whether has been fetched in cache by a page cross prefetch or not. So to showcase that if we use Mocha, we can design effective page cross filters, we consider 3 state-of-the-art L1D prefetchers, BERT, IPCP, and BOP. And we prototype a page cross filter for all of them using the set of program and system features that come with Mocha. We use IPC as optimization metric for the offline feature exploration, as typically done in hash perceptron predictors, but we can also use other metrics like coverage, accuracy, etc. So now I'm going to show you the results of using Dripper as a page cross filter as opposed to statically permitting or discarding page cross prefetch requests across the set of applications that I used before. Again, I'm going to focusing on BERT, which is the state-of-the-art spatial cache prefetcher. And the results show that Dripper is actually able to get the best out of page cross prefetching for the applications that enjoy benefits from it, while reducing the negative impact of page cross prefetching for the ones that BERT is not able to accurately cross pages for prefetching. We also show that Dripper is more effective than the state-of-the-art in-page hash perceptron prefetch filter, and we verify that this is the case across all 3 considered spatial cache prefetchers. Next, I'm going to consider different metrics to showcase why Dripper brings the benefits that I reported before. So first, the coverage, where we see that Dripper has more or less the same coverage as the statically permitting page cross scenario. And this is good news because Dripper is a filter. So managing to have the same coverage means that it's able to identify the useful page cross prefetch requests and issue them. Regarding the accuracy metric, we see that Dripper has significantly higher accuracy than both permit page cross and discard page cross scenarios. And this happens because it's able to identify the useless page cross prefetch requests and discard them. This has a positive impact on both TLB and cache MPKI rates because we are able to identify which are the useful page cross prefetch requests and discard them. Of course, there is additional evaluation in the paper, but I don't have the time to go through in this presentation. So the main conclusion behind this work is that prefetching beyond page boundaries for VIPT caches needs more attention since static policies with respect to it are suboptimal. Some applications enjoy benefits for crossing page boundaries for VIPT caches, some others not. And we propose one possible solution towards effective page cross filtering. And we prototype a page cross filter that we call Dripper and show that it provides consistent benefits across different state-of-the-art cache prefetchers and a diverse set of applications. Now I'm gonna go through briefly for like the last part of the presentation about the trends in microarchitectural designs, and I'll try to deliver my vision for or my perspective about future microarchitectural designs. So looking at current designs, we see that they are getting more and more complex. More and more features that are actually kind of really hard to be useful across all the emerging applications that we are targeting because they are increasingly diverse. So it's really unlikely that a feature will be useful for all applications. But what I want to highlight here is looking at the cartoon that I have in the slide, you will see that as we go to next generations, the IPC uplifts that we get through microarchitectural features is going down. And since we don't have many more traditional microarchitecture optimizations to improve performance efficiency, we need innovation. We need to think out of the box and come up with non-conventional approaches if we want to keep pushing for performance efficiency in next generation CPUs. And I think this is very challenging. And this is actually, I firmly believe that this is a good time to do microarchitectural research because of these challenges. And my perspective on this can be seen like based on this talk. What I showed is that it's possible to exploit metadata available at the microarchitecture and runtime levels to improve the microarchitectural decision making, and also design intelligent microarchitectural schemes like Dripper that can boost performance efficiency. So if you combine this with ideas that create synergies, for example, between different microarchitectural components where the output of one component can be input for another, also it's very important to be able to understand when a microarchitectural feature is not useful and disable it or transform it to do something else. Because, as I said, we are targeting a portfolio of completely diverse applications. And another idea is to exploit information from the upper level of the transformation hierarchy, like the OS. If you combine all these, you will end up with intelligent and adaptive microarchitectures, which is where it's going with microarchitectural designs in the future. And although I discussed about 2 works in this direction, there are additional works that highlight my vision towards intelligent and adaptive microarchitectures, and hopefully these will be expanded in the future. Hopefully I'm on time, so I would like to thank you for your attention.
Questions? Anyone?
Hi, great talk. So I'm curious, like, where do we think we're going to find room for microarchitectural innovation alone, or is it will have to be software plus microarchitecture?
Yeah, this is the last part, which is I just highlight that you can exploit information from the upper levels of the transformation hierarchy, like the OS, the software stuff. But I also think that there is room for innovation purely in microarchitecture by rethinking the microarchitectural designs and potentially breaking some of the assumptions that we currently have. And I think this is possible, and this is a potential way to go. But also, getting information from the upper levels of the transformation hierarchy, this is also a good direction.
Do you think vendors are open to co-design, or they prefer
Yeah, that's a very good question. Maybe, I don't know.
Thanks for the talk. I have two questions. One is, so you talked here about how we can leverage whatever the OS is doing. So the OS might create a 4 kilobyte or a 2 megabyte page or whatever it does, right? And then you try to leverage it by saying, let the prefetcher go loose beyond the page boundaries, etc. So one question is, this is can you do the reverse thing? Could you be like, okay, I will check what the prefetcher gains by potentially crossing the page boundary, and based on this, I will decide whether I will go for a 2 megabyte page or not, or whether it makes sense to take the pure microarchitectural decisions and telemetry basically in the first place, trying to find out what are the benefits, and then propagating this back to the operating system to make choices about the page size selection or any other page placement, let's say, technique.
In theory, this could be done, but I don't know if it would actually make more sense than what we are doing now, like propagating information from the upper levels to down to the microarchitecture, because then you would rely a lot on the underlying microarchitectural schemes that we are using, like the prefetchers, the replacement policies and stuff. So you might end up in a case where the prefetchers are not really working well, which might be the case in real-world applications. So you might end up propagating information back to the OS that are not really helpful, and you might end up harming more the performance that what would be your ideal upper bound on this direction.
I see. But you could at least, propagate whether this 2 megabyte page selection, for example, was useful for my prefetcher. This is something that you can inform the OS about, like in a learning type scenarios where this could be important.
Yeah, this in theory could be done. As I said, I have some concerns.
Is there some time?
Yeah.
Okay. Which one? Both. Okay. So thanks for the talk, Yorgos. I have a quick question and also maybe a comment for what was mentioned earlier about OS. We need to remember, and since this is a workshop about software hardware co-design, maybe it's not a very nice thing to say, but virtual memory in a sense is a liability, right? It's not something we want. The natural thing to do is have a flat physical memory everyone is comfortable with, and then we don't need to worry about crossing pages. It's done. It was added to solve things that you've mentioned earlier in your talk, right? So to do isolation, to increase the capacity, and then we had to abstract the way we think about memory in order to compensate for that. So what you're saying is that the hardware should help the software solve the problem that it created for the hardware, right? It's the inverse way of thinking. Instead, the software, if we want to do software hardware co-design, maybe the software should give us more hints on whether or not these 4K pages are actually a fragmentation of a much larger data set that it had to fragment for various reasons because it couldn't fit them together. So it could add hints and tell us, hey, this page, I want you to cross and prefetch through. So then, but then this requires a software hardware co-design scheme. So that's I think there is a lot of sense in adding these hints. It's about the trade-offs, of course, right? Do you want to add bits in the page map? Do you want to cache them?
Yeah.
Do you want to let the prefetcher see that? So, but there is a lot of, I think, potential here for further research. So this is very, I find this encouraging, I think.
Yeah, clearly there is potential, which is falls like into the last bullet. How can we do so? How to encode this information? How to pass them? These are open questions, and it really depends on the merit that you are getting out of it.
Let's thank the speaker again. We have a 5-minute break.
5. Okay.
Can you hear me?
I think they can hear.
Oye, you can hear me, right?
Yeah, now I can.
Oye. So, welcome back, everyone. So our next speaker is Jovan Stojkovic. He recently got his PhD from UIUC, working with Professor Josep Torrellas. He's currently a visiting researcher at Meta and an incoming faculty at UT Austin in 2026. And he has done very nice work into the realm of hardware, operating system, software, and many more things. He's one of the most productive architects I know. The stage is yours, Jovan.
Thank you very much. Thank you. Hello, everyone. I think that I can hear myself. Is it good now? Yeah. Is everything fine? Okay, and now I cannot hear. All right. Hello, everyone. I'm Jovan, and today I will talk about overview of my research on hardware and software design for cloud-native workloads. In recent years, we're witnessing a significant growth of cloud computing. As more and more users want to use cloud services, cloud providers not only need to increase their infrastructure by adding more and more servers, but they also need to find new ways and new computing abstractions to make the programming at this large scale more efficient. To that end, we have new computing paradigms, namely microservices and serverless computing or function as a service. With microservices, we take a large monolithic application and then decompose it into many small interdependent services. Each service implements its own separate functionality, and services communicate with each other to create the end-to-end application. With this approach, we have many benefits. The system is more scalable, design is simpler, and it's also easier to manage hardware at large data center scale. For these reasons, microservices are being widely used today. Large companies such as Uber, Netflix, Amazon, they all have their software infrastructures based on microservices. To take the step even further, cloud providers started offering serverless computing. The idea is keep the way of writing your applications as microservices, but on top of that, have another layer of abstraction to remove the resource provisioning burden away from the users. So the benefits, we still have this simple and modular programming inherited from microservices, but on top of that, we also have automatic resource scaling, meaning having more or less resources as we need it. And also we can charge the users with pay-as-you-go billing model. charge only for those resources that they actually use. For these reasons, large companies, large cloud providers such as Amazon AWS, Microsoft Azure, Google and IBM Cloud, they all have serverless offerings. In fact, the number of users using serverless computing is increasing a lot over the years. In fact, as you can see here, the AWS, Amazon AWS, more than 70% of their customers are using serverless computing. This means that cloud-native paradigms such as microservices and serverless computing are becoming more and more important. However, in my research, I recognize that there is a big mismatch between how we build processors today and what are the needs of cloud-native workloads. First, we keep building our processors to be large and larger cores, beefier cores. But in cloud-native environments, we have a lot but small-sized services. Intuitively, we had a large monolithic application and then slice it into many small microservices, but we keep running both the monolithic application and all of these small services on same hardware infrastructures. In fact, those small services probably do not even need the large caches, branch predictors, prefetchers, and many other sophisticated structures that consume area, consume power, but are not really bringing lots of benefits on the performance. And in addition to being small in size, these services typically have low instruction level parallelism, making it very difficult for them to extract all these optimizations on single thread performance. The main reason for low instruction level parallelism is something called data center tax. In order to execute these services in data centers, not only we need to execute the main application logic, but we also need to execute many auxiliary or helper functions to make the system run. For example, we need to go to the networking stack, we need to encrypt and decrypt messages, go to the RPC stack, serialize and deserialize messages, compress and decompress, and finally load balance across servers and even within server across different cores. As you can see here for DeathStar Bench, which are open source microservices, these services spend most of their time, 80% of their time, on data center tax operations. So ideally, we would like to offload these operations away from the CPU, let the CPU run efficiently the application logic, and potentially execute those operations on some domain-specific accelerators. Second, as we're building larger and larger cores and servers and put more cores on those servers, one of the main challenges is how to keep all these cores in our server coherent with each other. But in cloud-native environments, there is really not a lot of writable data sharing. As I said earlier, services communicate with each other using a remote procedure call. So software is using a remote procedure call for communication across services within one application. There is no use or there is no heavy use of shared memory. So this means that if we put all the cores in our server cache coherent, it is hard to justify the complexity and cost of such servers. On the other hand, we cannot fully abandon coherence and say that every core is for itself and then we only use message passing. The reason is some services need multi-threading, some services migrate threads across cores for load balance, and also we might have some level of data sharing. So instead of doing one of these two extremes, either full cache coherent or no cache coherence at all, we can go somewhere in the middle. We can take the large server, slice the monolithic coherence into many small independent domains, keep the coherence within domain, and use message passing across domain as it's already done in software layers. We have been building and optimizing processors for long-running predictable applications, such as HPC or similar. But in cloud-native workloads, we have short-running services, remember, microservices and serverless functions, and there's lots of idle time within the execution of those services, causing frequent context switching. So those services are dominated by idle time. And for that, there are two reasons. One, they often go to the remote storage to get the data from because they're implemented as stateless services. Or two, they communicate with each other, so caller service calls the callee and waits for the response. In both cases, either a service is waiting for the storage or for the callee service in an application. So we have an invocation, it has lots of idle time while it is executing the RPC request. In order to efficiently use our cores in a server, we need to frequently context switch. So we start running a service, it goes to the storage, we remove it from the core, and then start running another ready-to-run request. This request can be either from the same service or even worse, from some other service in our server. This frequent context switching causes lots of pollution in stateful hardware structures. Structures such as caches, TLBs, branch units, and others. In this example here, we have a blue thread running on a core. It brings its own data to the private local L2 cache, but then at some point it gets context switched out because it is issuing some remote procedure call. So we start running another ready-to-run request, for example, a red thread, which brings its own data. Then grid thread brings its own data, and so on and so forth. So when a blue thread returns and continues the execution on a given core, it will see highly polluted L2 cache, causing many misses and very low performance. So in order to improve the efficiency in this environment, we need to preserve the microarchitectural state of these services across many and frequent context switches. And finally, it is important to notice that conventional servers and conventional workloads are built to be optimized for average performance. But in cloud environments, we care not only about the average performance, but also we care a lot about tail latency. We want even the slowest request the tail of the response time distribution, to be completed within very strict deadlines. So what causes this high tail latency in conventional systems? Well, whenever there is contention in the system, it will cause high tail latency. For example, when we have queuing and scheduling, context switching, or even on-package network within a server. Typically, in these microservice environments or cloud-native environments, requests are coming in bursts. Here, I show the utilization of 3 large services from Microsoft production over 1 working day. And you can see that we have periods of load, and then sudden load spikes. So suddenly, many requests are coming in parallel for execution on this service. If we have a number of cores in our server and many requests coming in parallel, we can execute only as many requests as there are cores, while the other requests need to be queued. So how we design the queuing system will significantly impact the performance or tail latency of our services. And in fact, if we measure this overhead of scheduling done conventional systems in software, we can see that the overheads of scheduling increase the tail latency by about 10 times. This gives an idea that we can go much better and improve the efficiency of our system if we design a specialized hardware for scheduling and for queuing of these requests. I already mentioned that the context switching has this side effect of polluting the stateful hardware structures. But even the latencies or overheads of context switching can directly impact the tail latency of our cloud-native services. Here, I show on x-axis different context switch overheads, the simulated ones, and on y-axis how these overheads impact the tail latency for different system loads, from 5 to 50,000 requests per second. And to put this into context, this is where conventional Linux-based systems are. This is where more optimized state-of-the-art software schedulers, such as Shinjuku or ZigOS, are. And you can see that even with these optimized software schedulers, we get more than 10 times increase in tail latency just due to the high context switch overheads. Ideally, we want to be somewhere here, somewhere where the overhead of context switching is low enough that it doesn't impact the tail latency of our services, even at high system loads. So to do that, we would need to go away from the software solutions and offload this support for context switching in our hardware. And finally, as I said, these services frequently communicate with each other using network messages. So there's lots of traffic on the on-package network. While majority of these messages will be fast, some of those that are at the tail of their distribution will incur multi-hop routes, meaning long latencies, or they will face contention in links, meaning not enough bandwidth. And you can see here that the contention on the on-package network can significantly hurt the tail latency of our microservices. So for example, if we have high load, 50,000 requests per second, we use conventional 2D mesh topology, there is almost 15 times higher tail latency compared to an ideal system where cores can directly communicate with each other with zero overhead. So this means that we really need to design a high bandwidth and low latency on-package network for these cloud-native environments. So overall, we can see that when running cloud-native workloads on conventional hardware and conventional software systems, we end up having lots of inefficiencies in performance, energy, and resource utilization. So the goal of my research is to design new hardware platforms and new software stacks, and ideally co-design them tightly together to get orders of magnitude better efficiency in cloud-native workloads. Specifically, I design hardware and software schemes to improve performance, resource efficiency, and energy efficiency in cloud and data center workloads. Today, I will focus on these two examples of work, but of course, I will be happy to discuss any other at any other time. So if we take all the motivation and characterization that I discussed earlier, how should we design processors to improve the efficiencies of cloud-native workloads? Remember, here we have small-sized services that are invoked in bursts, so many requests coming in parallel. This means that instead of having a server with few large beefy cores that are optimized for single thread performance, we can use the same area and same power budget of our server, have many small cores, and execute many of these requests in parallel without losing the performance. However, when we have many cores in our system, for example, 1,000 cores, it is difficult to keep them all cache coherent. Fortunately, the communication in this environment is not done via shared memory, but using network messages or remote procedure calls, RPCs. So this means we take a large server with 1,000 small cores, but we don't connect all of these cores in a monolithic cache coherence. Instead, we group a few cores together in a village, keep the coherence within the village, and then let villages within the server communicate with each other using network messages as it's already done in software. And finally, we need to focus on optimizing not only the average performance, but also the tail latency of these workloads. To do that, we need to find and optimize away the main source of contention that increase the tail latency of cloud workloads. As I said earlier, those are scheduling, context switching, and on-package network. So I use those insights to design MicroManyCore, a processor architecture that is optimized for cloud-native services. Basic unit of a MicroManyCore is a hardware cache-coherent village. Within a village, we have a few simple cores, so each of them has its own L1 cache and then shared L2 cache. Cores within a village are coherent with each other, so they communicate using shared memory. We can migrate threads across cores for load balance, but then cores within one village can communicate with cores from another village only using network messages. So to facilitate that, every village in a MicroManyCore needs to have its network interface and DMA engine, both for local communication, meaning other villages in a server, or remote communication, meaning some other remote servers. And finally, every village in a MicroManyCore has a hardware request queue, which is a structure that allows us to do scheduling and context switching purely in hardware without involving any software or operating system invocations. So how does this hardware for scheduling and context switching work? When a new request for a microservice arrives in the village of our server, the network interface deposits this request in a hardware request queue. In this queue, we keep the status of the request to be waiting. So this request is waiting for one of the cores to become available. When one of the cores becomes idle, it starts spinning on a work flag. It means it checks in the queue, is there any request that is ready for execution, meaning being in status waiting? If so, the core executes a dequeue instruction, takes the request to run, and mark it as currently running. Once the request is completed, core issues a complete instruction, marking this request as finished, which will signal the network interface to take the request from the queue and then send back to the requester. So as you can see, the cores take the request from the queue and they deposit them back in the queue without involving any software or operating system for scheduling. As I mentioned earlier, during the execution of a single request, there is often time blocking event. So this means this request got blocked because it either goes to the storage or it calls some other services. In order to efficiently use our resources, we need to context switch and let this core run some other ready-to-run request. So in order to get this context switching fast, we also want to avoid operating systems and any software overheads for context switching. To do that, in micro-menu core, cores will save and restore the context of those requests purely in hardware. So core detects that a currently running request got blocked. It will mark it as blocked in the queue, and it will save the context of this request, meaning special purpose and general purpose registers, in a specialized request context memory. Then the core starts running something else, and in the meantime, the request gets unblocked. So now it is waiting for execution. When some of those cores again becomes idle, it will see there is a request in the queue. This request is waiting, meaning ready for run, but this request has already some state saved in the context memory. Then the core will read the state from this request from the memory in its own registers, and only then it will start running the request. As you can see, we use the same structure, this request queue, the hardware request queue, to do both scheduling and context switching purely in hardware without involving operating system, without involving any of these software overheads. And we further extended this idea of in-hardware scheduling for microservices to allow these services to be co-located together in the same server and then move the cores fast across different VMs. I will not go into details, but the main idea is that we need to detect when there is a request assigned for a given service that is not used, let another service use this core, but then have our hardware be conscious about lending or stealing the cores, so that when the request for a given service comes, we can fastly move the core back to the original virtual machine or original service. So now we designed these villages that are optimized for scheduling and context switching, and there are many of them, so we can execute many requests in parallel. But we now need to connect all of these villages together in a high bandwidth and low latency on-package network. To do that, in micro-menu core, we use a leaf spine topology. In leaf spine, we take a few villages, group them into clusters, and all clusters that are in the leaves of our topology are connected to all clusters that are in the spine of our topology. So this means we have many redundant and low hop count paths between any clusters of cores. Even if you have multiple messages going from the same source to the same destination, those messages can use different links and different paths, meaning lots of bandwidth. So in this way, we designed a server with many small cores because microservices are becoming simpler. Those cores are organized into coherence villages because the software is using remote procedure calls and not shared memory. And then we optimize some of the techniques such as scheduling and context switching away from the software in our hardware. And to take the step even further, I will briefly discuss how should we go even further and then design the microarchitecture of each of these individual cores. I mentioned earlier that one of the biggest challenges when it comes from microarchitecture in the cloud-native workloads is this preserving the state of services despite having frequent and many context switches. To do that, we designed Mosaic, which is a system that relies on fine-grained in-hardware partitioning of large stateful structures such as caches, TLBs, or branch prediction units. So in Mosaic, we take the large structures, we partition them into physical chunks, and then we take a few chunks that are not necessarily contiguous and assign those chunks to a given function as a tile. So every function has its own tile, which is a composition of a few different, not necessarily contiguous chunks. Then, when a function is running on a core, it can only use parts of the structures that are assigned to this function, and when we context switch, another function will start running on the core and use only parts of the structures assigned to it without touching the data from other functions or other services. In this way, we can have high performance because we skip the state of each of those individual functions in their own tiles. So we minimize the interference. And importantly, we can even assign all of these chunks as a single tile and then keep running traditional monolithic workloads without slowing them down. So in this way, we maintain the generality of our processor. Furthermore, we can not only improve the performance or efficiency of our microarchitectural structures, but we can also improve the power efficiency in these servers by using the partitioning technique. If we know that only part of the structure is going to be used while a given service is running on a core, we can only keep that part of the structure at high voltage, meaning good performance, and then put all the other parts of the structure at low voltage, which will effectively save the power of our server. So we will have 2 voltage rails, one for high, one for low, and then for every chunk, we will multiplex these 2 rails depending if this chunk is currently used by the running function or not. If it is used, use high voltage and good performance. If not, low voltage and save power. When we take all of these techniques and other techniques that we worked on, both on the hardware and software side, we can get orders of magnitude more efficient cloud-native workloads. For example, if we take Micro Many-Core Server and maybe optimize it with some domain-specific accelerators for different data center tax operations, as I mentioned earlier, and on top of that, we add software techniques for workflow, scheduling, and resource management, we can get 3 orders of magnitude more speed up or lower tail latency compared to state-of-the-art baselines. So using optimized hardware, using optimized software, we can get orders of magnitude better efficiency. And same thing goes for throughput. If we take Mosaic as our microarchitecture design and optimize it further with hard harvest, which I briefly mentioned, meaning fastly moving cores across services, and then using a software technique to overclock those cores only when needed, we can get throughput that is 15 times higher than state-of-the-art baselines. So overall, in this talk, I want to emphasize that cloud-native workloads are beneficial and they're becoming more and more important, but their current execution is really inefficient from the performance, resource utilization, and energy efficiency sides. I proposed new hardware and new software stacks to make a step towards cloud-native architectures. But what is even more exciting is that there is so many opportunities to further rethink how we build hardware and software abstractions for the emerging cloud workloads. With that, thank you for your attention, and I will be happy to take any questions you might have.
Any questions? Any questions, everyone? I have some questions, Jovan.
Yes, sure.
First, yeah, this approach is like, especially the micro mini core, it's like, you know, it's very intrusive to the conventional, let's say, multi-core architecture. So, and as you suggested as well, as you showed basically, like scheduling is one of the key things when it comes to this sort of microservices, function as a service paradigms, right? So my question is, what would be, let's say, a set of not so intrusive primitives that you could employ from the operating system side? For example, what could the operating system side give us hints or to the microarchitecture in order to enable the optimizations that we discussed now? For example, could I inform the current hardware architecture about the prefetching that it needs to do based on the scheduling decisions I will take? Or how can I adapt my scheduling decisions to enable better prefetching, locality in the TLBs, etc.?
Yeah, so I mean, those are great questions, and those are very open questions. So I mean, I like them. So you're right that some of the designs that I presented are more intrusive and more radical designs, like micro mini core. I think that focusing on scheduling and context switching would be a good start. So we don't need maybe to have 1,000 core machine with cache coherence villages, but we could have some optimized hardware for scheduling and for context switching. For example, using the Intel dynamic load balancer would be one of the ways. How should we design our software systems to efficiently use those new accelerators that are already present in today's servers? As I said, like the DLB is one example. You mentioned that we could use operating system to give hints for hardware or vice versa. I again agree with that. And there are many hints that you can give, either from for example, looking at how is hardware changing, or maybe what are the system calls that you're using, and then you can adjust many of the policies, including the policies on prefetching, including maybe on using different types of branch predictors or different replacement policies, or so on and so forth, depending on what you're currently running. So that is something that we're looking at actually at the moment, looking at how can we further incorporate some hints from the operating system or from the hardware counters, and then design more informed policies across microarchitectural features.
Okay, cool. Thanks. And the second question is with respect to GPUs. So, like you talked about serverless, right? So one of the recent works is trying to basically offload LLM inference, for example, and put it into the serverless function as a service paradigm. In this scenario, the GPU is one of the components, basically, where context switching hurts a lot. Like, if I want to temporally or spatially, basically temporally share the GPU, context switching is performance. So I guess, what do you think about like these sort of approaches that you design in your thesis and research when it comes to this sort of like huge register files and the sort of massive parallelism offered by the modern GPUs, for example?
Yeah, that is awesome question. That is awesome question, awesome research direction, I would say, about looking at context switching across models, maybe context switching across users on a GPU, and then like allowing them either to temper or spatially share, or both, so that we can get better efficiency. I think Dimitris was mentioning earlier that the GPUs are highly underutilized in across different industries. So yes, I think that if we take a look into, for example, maybe optimizing the context switching with some pipelining, or maybe predicting ahead of time how we should prefetch some data to the GPU from the CPU, or maybe even like using the newer generation of GPU servers that have GPU plus CPU that are cache coherent, and you have like unified virtual address space. You have lots of opportunity there, for example, to have better scheduling and better context switching policies. So I think that's the impact of optimizing scheduling and context switching in these workloads, where you have large data that you need to move around from CPU and GPU, either to design it new software techniques, as I said, maybe prefetching, or maybe new hardware features like CPU GPU coherence or something similar. I think that would get even higher benefits and even larger speedups than doing for conventional general purpose compute.
Cool. Thanks a lot. Let's thank the
Thank
speaker
you.
again. Is he there? He's you. Yeah, tell him to search. Can you hear me? The screen now.
Can you hear me?
Yeah, perfect.
All right, can you see my screen and everything works okay? It's sound? Is it too loud, too quiet? Okay, perfect.
Give us 1 minute or so. Ratsata, can you hear us? Can you hear us? No.
Yeah, can you hear me? Hello.
Can we hear him well? Can you try touching a bit?
Hello, can you hear me? Is it okay?
Yeah. Yes,
All right.
you can start.
Okay.
So
All right,
let me
so today I'll talk. Well, I can
let me
start, right?
No, let me introduce you first.
Yes.
So our next speaker is Ratsata. He received his PhD from Honor. We worked with the same lab for a long time, and he's currently at Mango Boost, where he's doing product planning. And he also was one of the people who made me dive into the world of virtual memory with his works. We have had lots of brainstorming together, and we have collaborated in some projects. Yeah, and I consider him one of my early career mentors, basically. Ratsata, the stage is yours.
All right, thank you so much for your kind words, and thanks for reminding me I tricked you into working on virtual memory. So today I'll talk about virtual memory design, but focusing on the throughput processor or the GPU, if you will, right? Company disclaimer, and one more disclaimer. It is especially more important disclaimer. All the work I'm going to talk about is actually everything is done prior to joining Mango Boost, so it means that anything before 2024. If you ask the question why is these papers like quite old, yeah, because um basically that those are still the time I was still active and publishing things in academia. All right, so if you look at modern day workloads, as you can see here already, joke on things being old, right? TensorFlow is actually getting replaced by PyTorch more and more nowadays. But if you look at modern day workload, right, you are having basically multiple types of workload that would run on a GPU, right? Things from AI, like IoT running on the edge, and now they are like basically putting AI into basically almost every edge devices, from your refrigerators to like your phone, right? You have things like federated training down here, where basically Google would collect your data and train locally on your devices, and they just submit the weight to the server and do aggregation inside the server and send it back so that your autocorrect is smarter and smarter every day, right? And on the right side, again, it's a little bit older, but these are like basically COVID mutation that we will still have to track, right? Because it's still going on. And so that we can actually build a next generation of vaccine, right? So these are the things where, if you look at it, right, it demands new hardware. And especially for AI, right? If you look at how it start in, let's say, like 2000s, 2010s, right? Into the part where GPT kind of flooded the market in 2003, then everyone followed that in 2024, and now a lot of new models are looking totally different in 2025, right? The hardware is going to be different. And so this means that you need a good system design, and then you need basically a hardware that can handle a lot of different types of workload, right? So one of the solution that I look into is actually how can we actually improve the memory management, specifically things like unified memory and virtual memory, so that you don't just get programmability, but also without the loss of performance, if you will, right? And why this emerging demands are important. So the typical assumption, right? I have a GPU, I buy a fancy new GPU, I want high throughput, and that's true already. And then application typically are really highly tuned for performance. But then you have things like LLMs, especially 2025 LLMs, where the model is much bigger. The other thing is much bigger is context length, and that actually exploit this thing called KV cache, which basically is a huge demand for your HBM and your memory, right? So your working set size is much, much, much bigger, even when you compare late 2024 to now. It's actually way bigger. And compute, right now, right, it's not only limited to just CPUs or GPUs. Why? People don't look at serving just a single model. Sometimes you look at serving agentic workload where you have one small model doing certain things that are fine-tuned, that they're really, really good at. Then they send the data to another agent, which is another LM models, right? So these are typically run on different GPUs. Sometimes they run on the accelerators that are neither the CPU or the GPU, but in the same system, they have to share data. So how do we actually control that? Now, what I'm going to cover in this talk, again, obviously, I'll talk about the virtual memory design or unified memory design for GPU, and then on another work that focus on processing and memory, right? So let's dive into the first type of work. And again, I because of the time, right, I might go a little bit high level. So if you have any follow-up questions, feel free to ask me or just shoot me an email. That's fine. And I will be happy to answer any of your questions, right? So one of the first issue with much larger working set size is oversubscription, right? I mean, one of the things that are being pitched to handle oversubscription is unified memory, right? But the problem with unified memory is you have a large pool of DRAM in the CPU. These can be like in modern system, this is like 2 TB of DRAM, right? And then you have a GPU with a limited HBM, and you need a lot of memory. So what did you do, right? One way you handle this is basically to do explicit memory transfer between CPU and GPU. Another thing is you can use unified memory. The thing about unified memory is when you have this automatic data movement, right? And you have to page data around, that can be slow. And these degrade GPU performance. And in some cases, when I run like experiment locally to test unified memory performance, someone crashed my system, right? And that is bad. It's bad not in just a lab setup where I run something and it crashed, or I need to rerun that. But imagine, right? You build a startup, you have to deploy your AI workload. GPU crash. That's not acceptable, right? So this basically becomes one of the major hurdle of basically adopting unified memory. Now, what are the current approach to handle memory over subscription, right? So obviously, one thing you can do is to kind of try to like bring in the request from CPU or somewhere, right? These days, it might not be a CPU alone. It can be CXL memory attached to a network fabric, right? You bring it into the GPU at a time, while you're evicting whatever is in there in the GPU memory that are stale, right? You can do like duplication, but that's also demand more memory on a GPU, which is not really solving the problem, right? So the downside is these are manual in many cases. You need to manually move the data. On top of that, right? You kind of need to know the working set at runtime, right? And then if you have virtualization going on in any method, right? You don't know what the other VMs are using, right? So you want a better way to handle this. And then when you have a multi GPU, things get way more complicated here, right? You can imagine this is our slide, so I'm using an older model like VGG16 or like PageRank or another workload, WCC, right? But you can imagine agentic AI where I can run Llama 3.145 billion, which is huge on a subset of GPU, and then I have another Llama 3.18 billion, which is much smaller on a different GPU, right? The smaller model usually demand a lot less HBM. So what it means is the model have that are smaller basically have a lot lower memory usage. And in many cases, you can actually do multiple tricks to get more parallelism out of a small model. But another option is I can also yield this extra HBM, right, for a bigger model. So that way, the oversubscribed memory can leverage this much faster HBM that are connected using NVLink as I show here, right? Because GPU typically is now connected with high-speed NVLink. By high speed, these are typically 900 gigabyte per second, comparing to the PCIe switch, which is basically in many cases 400 to 800 gigabit, right? So those are much slower. So if you can leverage the high bandwidth NVLink, then you have another HBM pool that you can access. And why is that much better? Basically, if you have to oversubscribe and go to the host, like this, and let's say we use it as a swap memory, the performance degradation is really high. It can be 2 to 6-fold longer to actually complete the application, basically end-to-end request latencies. And this is even with only 40% oversubscription, right? So our solution, that basically called harvesting memory or hierarchical UVM, right? We want to utilize the neighbor GPU memory and basically we want to be able to steal a small fraction of oversubscribed memory into a different GPU. And one of the problems that you see when you see this, one thing is, well, it's a network memory. It's a remote HBM. So definitely there's a Newman latency go into play here, right? So there has to be many elements that have to be designed and work together to make sure that these doesn't degrade in this case page rank, right? Because if you just spill any pages to a different GPU, that's bad as well. So our design goal is basically there are three things, right? We want to be the high eviction latency, high the fetch latency, and also make sure this application transparent, right? So on top of just make sure that this actually improve performance. So our design is shown here, right? The first thing is we want to preemptively evict the unused page ahead of time, but we actually utilize a neighbor GPU by using them as a victim cache. So this way, basically, anything that gets spilled over from my own GPU 0 here, right, is likely to be less frequently accessed because these are victim cache. So you first evict them here, then you evict them to the host memory. So that way you have these hierarchies of paging, right, where you go to first to the faster HBM and then to the slower PCIe connected DDR5. Now, the second thing is you can also fetch. But again, these are network, right? Basically, everything connected through either the high bandwidth NVLink or even the PCIe, which is not that high bandwidth, but it's still having quite a lot of bandwidth as well, right? So you can hide the fetch latency by using multipathing, because in this case, I show you 2 GPUs, right? But in modern system, a server has 8 GPUs. All of them actually are connected with NVLink. And in the middle is the NV switch. So you can actually fetch from multiple links from different GPUs together to actually get much higher bandwidth as well. So that allows you to hide fetch latency. And the third thing is we have this hierarchical design where the victim cache on a remote GPU becomes actually a pool of memory where you can quickly fetch data back to another GPU. This allow you to leverage the extra NV links that you might have not used, right? And this can be pretty useful for storing KV cache and use it as an intermediate layer between your host GPU and the much slower the CPU's DRAM, right? So because those are PCIe connected. And in our design, we make sure that this is basically all modified in a UVM driver. So if you just use CUDA malloc manage and use the unified memory like normally, you basically get 3x performance improvement on average without actually having to fix the software because that's big, right? If you program in GPU before, right, you will know that fixing that GPU application, like kernel code is really headache. It's a lot of headache, right? You don't want to do that. Now, this is the first work I'm talking about, which has to do with oversubscription, right? Basically, how unified memory can help programmability, but can hurt performance, and we can actually address it a bit. The second thing is, with the much larger working set size, right? You would imagine that, hey, I can maybe use huge page. And personally, I published paper on how we can have basically huge page functioning on GPU virtual memory, right? It's called Mosaic, and that was work back in 2017, 2018. One of the things we saw is even with huge page, right? You basically are pinned to either a small or large page, basically two different granularity. In many cases, can be like 4 kilobytes and 2 megabytes. In a GPU world, these days it can be like basically 64 kilobytes, right? Page. Now, I'll show you the problem of fidelity loss. And what it means is, if I use huge page, I have a much larger TLB reach, and that's good for performance. In theory, in practice, right, you have problems where you can run into things like fragmentation. In this case, this from a paper from OSCI 2016, right? You on x-axis is time, y-axis is fragmentation index. Basically, how fragmented is your memory? The more fragmented they are actually unused DRAM that should have been used by the system, but you cannot use it because it's fragmented everywhere, and the huge page is too big to fit, right? So if you use huge page, you see the fragmentation index go up to 1, which is really bad. The second thing is this another paper from HotOS 2019, right? You have dirty data amplification because huge page, when you tag things as dirty, right? The whole huge page is dirty, but in fact, in many cases, not the entire 2 megabytes is dirty. In many cases, only like maybe 16 or 64 kilobytes, right? So that's also another bad thing. Because if you tag the whole huge page as dirty, when you replace the page, those are also the whole 2 megabytes is replaced, even though you can only you might only have to replace 16 or 64 kilobytes. The third thing is unfair. Let's say you run 3 VMs, and this again is paper from OSCI 16, right? You run 3 virtual machine, my bad. You run 3 virtual machines, and the y-axis is the promotion. The higher is better. Basically, I get more promotion. I get more huge page. Then on the x-axis is time, and you can see the unfairness here, where VM3 basically got all the promotion and consume all the huge page. VM2 actually never get any huge page, right? And all these problems stem from the fact that when you promote to a 2 megabyte, you lose fidelity. What it means is, well, now I'm based in Chicago, so I'll use this example, right? This picture shows a Willis Tower in Chicago, and it's a giant skyscraper, right? So imagine if you use a small page. What it really means is, let's say I need to clean the windows. So not the, well, with this skyscraper, it's a hard job for sure, right? But imagine each of the window is your DRAM. There's a lot of windows there, right? If something is dirty, right, and you need to go clean it, small page means that I know exactly that pane, that window, that one single pane, that a small page. I know that window is dirty, so I can go and clean it right away. Now, if I use huge page, what's gonna happen is I have no way to tell that that part is dirty because my tag only tell me the whole side of the building is dirty. The whole 2 MB is dirty. I don't even though it's only one window pane is dirty. My job now is I have to clean the whole side, right? And this is a big problem as shown earlier. So to dive a little bit deeper, right, you have things like metadata bits where if you look at 2 MB page table entry, right? These are typical things like you have the PFN, all right, and then the metadata, right? And these are used to replace pages and figure out where if the page has been accessed or if the page is dirty or if the page is there, right? The problem is this is coupled to the page size, which what it means is if I use huge page, my metadata is tagged to that one big 2 MB. And with this, right, on this plot, this violin plot, we run many applications. And the shape of this plot, the bigger, the wider they are, means that I have things that I touch or things that are dirty on that application, but only on that fraction of the page. So as you can see here, right, many of these applications, I touch it only once on a few 4 KB page, fraction of my huge page. But then if I use 2 MB, right, the whole thing gets replaced, even though things I touch is only like at the beginning or at the end. For example, in this case, that I draw a circle around, right? Only small fraction are actually hot, right? But if I use huge page metadata, right, basically the whole thing is marked as hot. So our goal is to decouple this and make sure we have a finer grained way to tag sub pages, if you will, when you have a huge page or when you have a page promotion, right? And we want to make sure this applicable to anything like CPU and GPU. So our approach called Prism basically achieve this goal by first, we use this thing called metadata registry and the extension to the page table. Both of these are designed so that you can actually stick with the traditional page table structure, right? So for a quick overview, so if you have a virtual address here, right, you start with CR3 register, use the top index to the level 4, then level 3, right? And in here, in the level 2, level 2 is where typically when you have the huge page, like 2 MB granularity, right? So what we propose is to add this extension the same size as the typical level 2 page table entries, right? But we double the size. The reason we do that is when we double the size, right, we can actually store in this table, there will be this metadata registry bit that actually store the individual subpage access and dirty bits. And as you can see here, there are 32 bit each for the access bit and the dirty bits. It allows us to actually tag each individual 4 KB get granularity on whether that 4 KB is accessed or not, right? And with this extension, right, you can access your correct MRE. Let's say your page table entry is here. You then can just shift it by 2 to make sure you can access the correct entry in the MRE as well. So it's really simple. Now, in the 2 MB page table entry, right, in this case, these unused portion between bit 11 to bit 20, right, these are stored. We now use it store first of all just 1 bit if we have the MRE. If we have an MRE, we know that we can go to here to get the access and the dirty bits. And then 6 more bits. These will tell you the granularity of the access and the dirty bits. Because sometimes you don't want to track everything as 4 KB granularity. Sometimes 64 is enough, right? So the MRE bits has the 3 bits encoding, right? From the most fine grain, the 4 KB, to the least fine grain. With this, we can actually pick the granularity that we want. It can be 4 KB, 16 KB, 64 KB, or something bigger. Now, these have to do with page table. The other structure that we haven't talked about is a TLB, right? And the thing with the TLB is used as a cache to store your translation data. And if you have to do the page table walk, right, MIE provide that information. If you don't have to do a page table walk, you don't have your MRE. So what we do is we actually have to extend the L1 and L2 TLB with the MRE. So that way, anything that has to do with the large page, the 2 megabyte, will have the MRE structure attached to the TLB. And if you have a TLB hit, you basically just kind of check the access and dirty bits. Then you set it accordingly, right? Now, when you have a TLB miss, you then use the MRE store inside the TLB to update, basically, to update the page table MREs, right? So that way you know what's the update access and the dirty bits. And for the interfacing with software, basically we can modify the system call mmd config to actually have the the MRE bits and actually to configure the address space with these additional information. For performance wise, right? Basically, we want to showcase that it not only work on a CPU but also work on a GPU, and we want to link to many of the studies that I've done so far on like virtual memory design for GPU. So we actually extend our Mosaic simulator. Basically, these would model the GPU virtual address, GPU address translation, and also a huge page on a GPU. Right, we extend that to model the GTX 750 Ti and run multiple GPU workloads and at varying granularity, right? So the ideal case, right? Demand paging performance, right? You want to basically demand page as small as possible. So 4 kilobytes is the ideal performance, if you will, right? There's a lot of downside with translation, but these are not factored into the plot, right? We want to read the, we want to actually perform close to this red line as possible. But if you look at this plot, right, the blue bar is the baseline where you have a huge page. And as you can see here, there's a handful of application where your performance dropped by like 20% or even 80%, right? So that's a really, really bad. With Prism, you can actually use the MRE in the finest granularity here, right? For example, in the 32-bit granularity to track pages at the, I think, 16 kilobyte ranges. That way, you don't have to evict the entire 2 megabytes, and you can actually show in the paper that it's effective at handling fine-grained metadata, even though the 2 megabyte huge page doesn't have it. Now, the last thing I want to wrap up today, and I know for the interest of time, I want to kind of wrap this up quickly, is what if you have more than one type of accelerators, right? So in this case, it's in this case, let's say you have a PIM, right? Near data accelerators, which can come from in the form of GPU, FPGA, or ASIC. That like basically is accelerator that attached to the memory that can sit next to a GPU, or it can sit next to a CPU. In this case, we assume it sits next to the CPU on the HBM die, where you have this NDA on it, right? The problem is when you have the HBM, right? Typically your compute is at the bottom. These are typically the logic, and because the HBM has multiple volts, right? There will be multiple PIM cores on the PIM stack. Now, with this, right, what it means is the host CPU will see this PIM core, if you will, right? And with this means if I have a host CPU that want to access the data in HBM, right? This is in the memory bank. The host CPU can write to it. But again, at the same time, the PIM core, which is at this vault logic here, can also touch the memory banks. The problem with that is the host has its own MMU. PIM core does not even have MMU. So what do we do here? Because they touch the same memory. It's the same physical address, right? So this means that if you have PIM and you want to make sure it functions with the host, right? You want to make sure that you also you need virtual memory, right? But the problem is if you apply virtual memory to this kind of system, right? you ended up with a lot of sequential access. How does virtual memory work? When you do page walk, right? Let's say S5 has to do the page walk. It sometimes sends the page walk requests all over the place because they are sitting at a different channel, right? So that in this case, you do 4-level page table walk, 1 to S2, then S3, then S11, S14, and those are so. Now, what we propose in this paper called VPIM is that we first want to leverage a cuckoo hash table to actually do the page walk in parallel. And then we want to further optimize by asking, can we avoid even the first access, right? So let me go quickly go over the idea. Basically, what cuckoo hash table, which is a previously proposed idea, do is when I want to do translation, I have a cuckoo hash table where my translated address can be at some of these locations. So what I do is I leverage the parallelism within the the HBM structure, because HBM structure has a really one of the benefit of this is it has high bandwidth. So I can go to S0, S3, S11, S14 at the same time, right? If one of those locations has my address, I can go get them in one single memory access. And this is actually good, right? The problem is, can we do better? Because the problem is, PIM doesn't have even a SRAM TOP, right? If I need to go to if I need to use virtual address, I cannot even rely on SRAM TOP. It's not there. I need to go to DRAM. And can I avoid that one single DRAM access? Because it's long. It's actually double the memory access length. Because memory access, well, it's one DRAM access. Now you have two DRAM accesses, right? So what we do is, well, what if we dedicate some of this PIM core to do pre-translation? And to do that, right, we give the option to basically in this case, let's say you have a code where you have a parallel for loop, right? These are things that you would run on a PIM core. But the code for the main core is in the parallel for loop here at the top. We have a pre-translated core that almost like a run-ahead core, if you will, right? That go and look at what is my next physical address that I want. Well, now that I have a list of virtual addresses, I pre-translate that, put them in the MMU right away. So I pre-translate ahead of the fetch. So you basically avoid that first DRAM access. Now, in terms of performance, right? You can see that on the y-axis is a slowdown relative to total time. So you want it to be basically you want the bar to be as high as possible, right? With our design VPIM, we are able to improve performance by 4.4x compared to a traditional page table structure like LaTeX page table. And I believe the number is about 2 times faster than a traditional cuckoo hash page table because we do pre-translation. And we have more results in the paper, again, because I'm basically covering 3 different ideas with like 25 minutes. Again, to summarize, right, takeaway is if you want to manage accelerator memory, right, you want to look into things that matter for performance, things like paging between different accelerators, GPU to GPU, or paging between CPU to GPU. Granularity also matters, right? When you page things, you might want to page things at a bigger block or at a smaller block. But to do that, you need a way to track what you want to page in and out. And then multiple types of compute can further complicate the virtual memory design. For example, I have CPU, I have PIM, I have inference accelerator, I have a GPU. How do they talk to each other, right? With the same virtual address, that can be complicated. And possible solution that what I show here, for example, are things where we can hide eviction and fetch latency and use victim cache to leverage actually neighbor GPU memory as your, I guess, your second hierarchy in the memory hierarchy when you want to access a GPU, right? You also can add more metadata information inside the page table structure, right? So that you know what exactly are the hot pages, what exactly are the dirty pages. And also, you can also leverage parallelisms to actually pre-translate page walk And with the ML10 trend, right? This is basically the last key takeaway that's not actually covered in the talk. But you have new workload where you're looking at a lot of KV cache demand, a lot of basically heterogeneous model, things like mixture of expert, or even when you have small model and large model working together in an agentic workload, right? Your address space will grow significantly across the many GPU servers, right? This is basically why you see a lot of new GPU, I guess, rack, right? That would are now connected in NVLink, for example, right? This is really a scale up solution in a different scale, if you will. And then accelerator types might not be the same. I mean, you saw this already with the NVIDIA announcement where you have the pre-fill accelerators, the GPU that are tuned for compute, and then the decode accelerators in the same rack, right? Where it's tuned for memory, right? And there's so many open-end research questions. Actually, I would say thanks to how fast the ML, I guess AI ML area have moved, right? It shifts the bottleneck quite a bit. So this is another thing I want to talk today. And that's it for today's talk. If you have any questions, feel free to email me. I'll be happy to answer any questions. And thank you so much. And let me know if you have any questions today.
Any questions? Let me see if the
Yes. It is later. Okay, so you talked about fragmentation, internal and external fragmentation, and specifically when it comes to metadata. And essentially, you increase the granularity in which the metadata are stored in the page table, right? I'm curious, what would be your opinion about essentially using more page sizes, extending essentially the available page sizes, and sort of tackling this problem this way? Did you study this? Would this be a solution? Would this have any negatives in your opinion?
So let me iterate the question so I understand that correctly, right? So your question is, what if I use a bigger page size? Is that the case?
More variety in page sizes, multiple
Oh,
page
more
sizes,
variety in page size. Yes.
Mainly smaller than 2 megabytes.
That is a great idea, actually. So I agree that that can help fix the problem. I think the devil is in the detail, though. It's like if you want to enable more page sizes, what is the best approach that will not? So one of the things that when we start talking to system people is that it's going to be also pushback on, okay, we have now 10 choices of page sizes. Now I need to change the kernel to adapt to that, right? So basically, how to make sure that also is done in a performant way, right? So it's fast, still fast, and also in a way that it can be integrated to the rest of the stack. But yes, that can totally be a possible solution.
Okay, thank you.
Hi, Osata. So one more question from me. So regarding the GPU unified memory part of your talk, so as you discussed, right, like when we do demand paging and we want to fetch pages from the CPU to the GPU, we potentially need to pay a high cost because we fill up the page fault buffer. We're waiting then for the CPU to handle the transactions through the PCIe. And my question is the following there. So all of these models you described, like that use KV caches, etc., they tend to sparsify, right? Like from the algorithmics point of view, people using sparse attention right now to reduce, for example, the size of the matrices. They try to selectively drop some parts of the KV cache. So my question is the following there. Would we be able to afford doing this sort of migrations and the demand paging at singularities than what we're doing right with modern GPUs? Because I might move 64 kilobytes of data from my CPU, but if it's like I'm not going to use this piece of data, then it's pointless, right? So could I save if somehow the CUDA runtime or the GPU runtime was able to give me the possibility of transferring less, basically? And how would that impact the translation subsystem?
Yeah, so actually that's a great question. So one trend I see from like the ML system folks or like this KV cache pooling and KV cache manager, right? Where well what you said, right? If I don't have enough room for the KV cache, I might have dropped it, right? Or because the thing is if I put KV cache in the CPU, it might be too slow, right? So there are trend in the system side of things where they are trying to look into are there can we leverage the KV cache available anywhere else? Uh, and sorry, the echo of the spotlight, so it suddenly become my face on the screen. But yeah, so these can actually change how KV cache behave, right? And with that, you can pool the memory resources, right, into a bigger pool, but then you make sure that you manage as if you're prefetching the KV cache that's likely to be used into the GPU memory faster. Does that answer your question?
Yeah. It does.
And again, the thing, right, is it is I my belief is that it's not just a software solution that has to be moving. Hardware have to also assist that as well, right? Because again, PCA is too slow, right? So you might want to actually get faster. You also might want to be more proactive in can there be a way to prefetch those KV cache uh, uh, that are assisted by hardware. These are things that are open, to be honest, right? And I think with again with the trend this year, I was very specifically talk about papers that have been published in the ML community this year. There's also many focus on how to deal with like this large demand from KV cache because once long context comes into play, I mean the memory footprint grows significantly. And by long context, basically, I'm talking about like a Meta Llama 4 where it support like a 1 million context link.
Yeah. There's the problem where the fetching data from the
Yeah.
CPU becomes much larger, right?
Yes.
Okay, cool. Let's thank the speaker again.
All right. Thank you so much.
We conclude this part of the workshop. So we're gonna have 1 hour and no, it's like we're gonna start around 1:15. I'm gonna add it in a slide so that people can see it. And we're gonna start the tutorial part. So I would like people who would like to participate actively in the tutorial. I will give you some instructions so that we can give you access to some virtual machines so that you don't need to install anything on your computers and you can do everything with virtual machines. You just say it's there and then you can use it seamlessly, basically. We'll give you the instructions during the break. Thanks.
I will put a slide that says I will put a slide. You want your computer to right? Yeah, we can see it. That's better now. Yeah, you know, it's like outside. The real player has things. Test, can you hear me? Fine, perfect. Thanks. Okay, take it out. Give it here first. It's open. Cool. Let's connect.
Hi again, everyone. So this is the second part of the workshop/tutorial. This is the tutorial part. So we're gonna first give a brief introduction to the tool that we're gonna use at the demo later. And Konstantinos Zouras is gonna give the introduction to Virtuoso and its technical details and what we achieved. Konstantinos is a master student at ETH Zurich. He is a research assistant working with Professor Mutlu. We have been working together for more than 3 years on the simulator. He's probably the most major contributor, and I think it was a good experience overall, and we made the steps together in this direction. The stage is yours.
Thank you, Konstantinos. I hope everyone can hear me. Nope. Can you hear me? Perfect. So we will get into Virtuoso, but first, everyone that wants to follow the tutorial, you can send us an email in this email address. Generally, take a picture if you want to follow the tutorial, so that we can provide access to a VM. So please send us our name and affiliation, and we can begin the process because it's going to take some time. You can start from now until the end of my talk, so that we can have everything ready. And if you want, you can also work locally. Perfect. So we talked about a lot of stuff. We talked about overheads of virtual memory, overheads of others translation, memory management in general. And we want to essentially see this topic from a different perspective. How to effectively evaluate these virtual memory techniques, which is very crucial. And there's a big sort of opportunity here because there are challenges in this evaluation, specifically of virtual memory and of OS hardware code design. There are many system components that play a part when it comes to this code design. We can have the hardware MEMU, the system components, memory management at the software level, and all of these sort of have an interplay with each other. And this makes the simulation very, very difficult. One example of this is, for example, between the page table and the allocation policy that the OS uses. So the size of the page table essentially depends on the number of large pages that the OS has provided. Let's get a little bit more detailed on that. So if the OS has low fragmentation, it can provide plenty of large pages, for example, 2 megabyte pages in this case, and the page table is relatively short, so it has fewer entries, and and it uses less memory essentially. But if the OS cannot provide, let's say we have high fragmentation, can provide only or not provide that many 2 megabyte pages, we are forced to use 4 kilobyte pages. This makes the page table larger. And this can have interference in many places. For example, it can have interference in the cache hierarchy, and it can change how essentially our workload behaves. And another example is the page table and the memory interference. Essentially, we can have an application which has its page table entries in memory, and we have another application that has its data in memory. And these page table entries and data coexist in the same DRAM bank. If this happens and we want to access the page table and program data at the same time, and the two applications are running together, what we'll see is that we will be bringing, for example, the program data into the raw buffer, and then we want the page table data. And that results in a conflict. Essentially, this is really difficult to simulate and express this interplay through our simulations. Perfect. So again, we can have conflicts, and this can affect the latency of our execution. So these are the main challenges in evaluation. The fact that we have so much interplay, and the fact that the interplay is critical when it comes to evaluating current and new virtual memory techniques. So researchers have architectural simulators at their disposal. Let's look at how the architectural simulators are categorized. There are two main classes of simulators. The first class is emulation-based simulators, and the second is full system. Emulation-based simulators, such as Ramulator, Sniper, ChampSim, ZSim, all have high simulation speed with a focus on modeling microarchitectural features. The negatives? They have limited support for OS primitives, and they analytically estimate, for example, the virtual memory overheads. On the other hand, full system simulators like Gem5 Full System, QFlex, PTL Sim, etc., enable the execution of a full-blown OS on top of the hardware simulator. Of course, this comes with lower simulation speed, and of course, it's harder to develop. So anyone who has worked, for example, with Gem5 will know that it's very hard to implement new features, especially when it comes to software and hardware cooperation, because of the very high compile times or booting times, etc. So these are the two main classes of simulators, and we can plot them in this graph and say that the emulation-based are fast, but not as accurate, and the full system are more accurate, but have lower speed. And essentially, there is a dichotomy between these two categories of simulators. So what is our goal? Our goal is to bridge this gap, essentially. We want a simulation tool that is both fast and accurate at the same time. And bridging, and this is our goal, and this is our proposal, Virtuoso, enabling fast and accurate virtual memory research with an imitation-based operating system simulation methodology, which was published in ASPLOS 2025. And what is Virtuoso? Virtuoso is a new simulation framework that enables fast and accurate prototyping and evaluation of the software and hardware components of virtual memory. So essentially, Virtuoso uses a lightweight user space kernel written in a high-level programming language, specific C++, and only chooses OS modules related to the desired research topic that each researcher wants to touch. For example, let's say we have these are all the sort of things that an actual kernel can do: monitoring, interrupts, thread scheduling, boot, and specifically to memory allocation and virtual memory research, transparent huge pages, swapping, and virtual memory area handling. So from all of these features that we could have from our OS, we are only picking the ones that are relevant to our topic. So we can combine them, and we can use this lightweight user space kernel to have essentially faster simulation. We're going to see how exactly. So there are three goals that we have with this tool. First, rapid development and prototyping. We want this to be fast, as we said, for full system simulators. This is likely not the case. We want high simulation speed by executing only the desired OS kernel functionality. We saw that we're picking the functionality that is relevant to our research topic. And we want accurate evaluation by integrating Virtuoso with an architectural simulation, which means that we can provide all these features and we combine with a core model, an MU model that is already existent and provided by architectural simulators. So essentially how this imitation-based simulation works. So we have our lightweight user space kernel, which is written in this case in C++, and we have our simulator. What we use in our case, and the integration with Sniper, we're using binary instrumentation using PIN, Intel PIN, and we take our lightweight kernel and we're running it, and we have a stream of instructions. So we take this stream of instructions and we're feeding it into the core model of our simulation. So let's say we have a page fault. We're taking all the instructions of the page fault and we're feeding it into the core model of our simulator. These are getting processed and processed and processed. And essentially, we're imitating the OS level overhead of this interaction. And in order to have the functional outcome of the page fault, for example, as well, we have a communication channel where we enable emulation of the kernel models. And we essentially return the answer of each of the OS functions that we are invoking. So let's see an example workflow. So let's say we have page fault handler and we're using transparent huge pages and a body allocator. So we have an example user space kernel here, which will be our page fault, and we have a workload. The workload essentially communicates the memory accesses to the core model of the simulator. The core model sends a translation request to the MMU model of the simulator. And then this MMU model has a communication channel where it communicates all the events that are happening, which, for example, is a page fault, and communicates it to the user space kernel. This user space kernel runs a coroutine, a page fault handler in this specific situation, and it uses binary instrumentation to send the instructions into the core model. And it also sends the event, the page fault outcome, to the MMU model. So essentially, we are clicking our user space kernel with an existing architectural simulator. So the Mimic OS is what we call essentially our framework and the OS part of our proposal, which includes body allocator, radix-based page tables, huge TLBFS, transparent huge paging, swash space, and page cache. And you can find more of these details and more of what Mimic OS can offer in the paper. Also, we offer a toolset which encompasses both hardware and software components of multiple state-of-the-art VM techniques, and you can see many of them here. For example, page size prediction, page tables, etc. And we essentially have packaged everything so people can use it and can essentially help in virtual memory results. So you can find, again, more of this information in the paper. So what we have also done is we wanted to prove that we can port this Mimic OS, this lightweight user kernel, and we can port it in different simulators. So we decided to integrate Virtuoso with 5 diverse architectural simulators. For example, Gem5 syscall emulation, RAM emulator, Sniper, ChumpSim, and MQSim. All are specialized for different applications and fit different workloads better. And we showed that we can have our Mimic OS integrate with every one of them. Also, in order to show how accurate exactly is Virtuoso, we decided to validate against a real system. So we integrated Virtuoso with Sniper, and we compared it against a Linux kernel with a high-end server-grade CPU. And these are the results. So we have the baseline Sniper, we have Virtuoso with Sniper, which is the integration, and the Gem5 full system. Essentially, these numbers and this IPC modeling accuracy is found by running on a real system, which has been configured in the same configuration as the simulated system, and we try to match the conditions as well, for example, fragmentation, etc., in order to have the best result possible. So Virtuoso integrated with Sniper provides 21% better IPC modeling compared to the baseline Sniper, and it's also 9% different from the Gem5 full system, which is the most accurate that we could find when it comes to simulation, the closest one to the real system. And it is interesting to see also the simulation speed, because it's the other part of the trade-off, where we can see Gem5 specifically in the full system, which is very, very slow when it comes to performance. And we can see our integration and the integration with other simulators that on average have 20% overhead when it comes to simulation speed. So yes. Exactly. So, Virtuoso's versatility. We showcase Virtuoso's versatility by evaluating multiple different use cases and demonstrate new insights on state-of-the-art VM techniques. We have 5 use cases in the paper, but for this talk, just to keep it short, we will evaluate 2 of them, how we evaluate different page table designs and evaluating physical memory allocation policies. Yes. So first, we're going to start with evaluating different page table designs. So we used RSR baseline, radix-based page table, and we evaluated elastic cuckoo hashing, which was presented as well. And we essentially defined fragmentation as the number of available 2 megabyte pages compared to the total number of 2 megabyte pages that can be found in the system. And we're using these workloads from GraphBig, XSBench, and HPCC. So what do we notice? We notice that when the fragmentation level becomes lower and lower, the page table work latency reduction of elastic cuckoo hashing compared to radix increases, which means it gets faster and faster and faster the more contiguity it can find in the system, the less fragmentation essentially it can find in the system. And we can also see the negative, essentially, of elastic cuckoo hashing that we could pinpoint, which was that elastic cuckoo hashing leads to an average 52% increase in DRAM row buffer conflicts. Doesn't necessarily mean total end-to-end latency increase, but the row buffer conflicts increased by 52% when we're using elastic cuckoo hashing. The other example use case is evaluating the physical memory allocation policies. So we used a baseline of an allocator with a buddy system, and we used Utopia, which essentially we are managing memory in a hash-based manner. We're using restrictive mappings in order to have a better allocation policy. And our workloads are short input and short output LLM inference. And we can see that Utopia, which restricts the visual to physical mapping, speeds up memory allocation up to 2.17% for these workloads that were evaluated. So more details about this can be found in the paper, and you can see this detailed description of the Mimic OS. You can see how we integrated it exactly, and many other stuff that you can see in the paper. And also, the entirety of Virtuoso is open source. You can access it right now from this GitHub link, and we hope to update it and keep it in a state-of-the-art manner with new techniques constantly. And we have, of course, a website and documentation, just make it easier for people to develop with Virtuoso. And with that, we can go on to the tutorial. If there are any questions, we can have them now for the theoretical part, essentially, of Virtuoso, and we can move on to more practical. Please. Yep.
Thanks. So you were saying you run everything, and whenever you hit some OS code like page unfold, you spin to translate that and move that over to, or feed that to the simulator.
Yes, so we are essentially stopping our main execution. We are recording the page fault or whatever this code is. It could be networking, it could be whatever. And we're injecting this instruction into our instruction stream.
Do you pick the addresses original, or do you fiddle with the addresses too?
So essentially, we're returning the information of the page fault. So the simulator, because this has to happen on the simulator side, can actually translate all these addresses, and we can implement virtual translation using our Mimic OS coroutine. So if we have a channel that returns the address.
Or then from the host runs it?
Yes. No, the Mimic OS simulates the page fault, right? So it's a lightweight user space kernel. We simulate this page fault, and we have a result, the address. And we feed this back into the simulator.
Do you change the addresses that run, that the OS basically uses? Do you change them when you feed them to the simulator or not?
No.
No? Okay.
Yeah.
So how is it different than full systems? Because it's a mini OS.
It's a mini OS. We choose what we're running. And also, essentially, we don't have the full flexibility. We don't have the full functionality of the OS. Even when it comes to page fault, a lot of things that we may not want to simulate. So we have a lightweight version of the page fault routine that we have written just for research purposes. And we can have a good understanding of what is happening and what are the performance overheads of the page fault latency. Yes.
I can add up something. So one more benefit, which has to do with scaling experiments as well as the memory requirements, right? Because the full system, when you use a 70 gigabyte data set, it requires a 70 gigabyte large memory to be able to fit stuff. Right now, we do not store actual values. We do not need to store them because, okay, we don't do fault injection potentially, right? Where we want to have the actual values. Scaling experiments as well. Like, for example, we could run in our cluster 2,000 experiments at the same time, right? And with Gen 5, we could run 150, something like that. That's one. And second, I think there are two ways to approach what you discussed, whether we change the addresses or not, right? So the user space OS could either use translation or not. So when let's say we record the trace, right? Like in SAMSIM or whichever simulator, this trace has virtual addresses. So in SAMSIM, for example, there's no translation. So you're using the virtual addresses to access the caches. In a relator, the same, for example, you would use again physical addresses in a random manner. You have a linear mapping, right? Which is not representative of what would happen in reality. So what we do is like we feed these physical addresses based on what the user space OS has decided from an emulated memory. So essentially emulate the memory. So you can define the physical addresses that your simulator is going to use.
So you have your own page map.
Yes, you have all of this. Yeah. So the only thing you cannot change easily is
So when you want to simulate your user space application, this is in the virtual address space. Between this virtual address space addresses accessed by Mimic OS, we basically add one more bit so that there is no aliasing between the physical addresses of which are emulated and the addresses of the user space. Because otherwise it becomes very tricky to do. Like having actual physical addresses requires basically running experiments in a server with where you have pseudo accesses and all that. We didn't find a way, but even I do not have access to that in our lab.
Okay. And the other thing you mentioned, so you have or you may have conflicts, right, between user data and
Yes.
translations because they use the same methods.
Yes.
Is this something observed with those simulations also?
Yes, and as we saw with Elastic Cuckoo hashing, it was an interesting observation. It was improving performance, but we saw specifically for the DRAM model, we had a lot of more conflicts basically than a normal scheme. So it was an interesting observation to see that these conflicts do exist, and page table data and actual data create basically the fact that we have page table data in our system creates more conflicts. So yes, the fact that we simulated this page table created more interference with the actual data. Yeah, it was an interesting observation.
Thanks.
Thank you for your questions.
Yeah, I think this is one of the topics which is not very well studied, I guess. Interactions of the page table with the DRAM, basically. And like also the mapping, the physical mapping, which means that how do I place my page table so that I minimize conflicts or I minimize interference with other piece of data? I don't think there's too much work on this research-wise, and I think it's a good area for someone to.
What about devices, by the way? Do you emulate? Do you emulate devices as well?
Well, yeah, we're building a NIC right now. So we're trying to emulate the NIC, the IOMMU and the NIC. But the TCP/IP stack is killing me a bit. So.
Yeah. But the methodology is there. Everything would be implemented.
But at this point, you already emulate. I mean, the I/O, the disk, these things are emulated.
We have the disk. We have everything when it comes to address translation and virtual memory, and we're trying to create as well NICs, etc.
Ours is going to show a demo with this.
Yes. Thank you for your questions.
Everyone?
You go around the room, take the mic.
Okay, perfect. Then we can move on with the tutorial.
Guys, how many people want to follow the tutorial?
So it's a different room, right?
It's a different room. No,
Maybe I'm wrong.
No, it's this.
This would be a painting.
Thank you.
We are moving on.
Thank you. Appreciate it. We can. If you put the presentations. Of course, I will send you the can I have. Sure, I will send you.
Yeah.
Yeah.
You remember?
Of course.
So we always lots of problems.
Thank you for your argument. You see, this is balance.
Yeah, you click the mouse.
No, it's the other room. Same story. This one academy.
So
that's 1912.
You want to? No. I don't know. I don't know how to. It's tired. We want to do it basically for the purpose of recording it, so we have that.
If you want to sell this, say so.
You can give me Lotte. Yes, I have a second. I can't prepare. But I would suggest that it's painful if you don't want that. You're specifically. It's painful in the sense of like I need to go through code. So.
But now it's just for.
That's not for you, it's not. Not for you.
Thanks. Das ist ein Ding. Die wollen sich dann. Ja, es kommt welche, was sie drin haben. No, 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 the Thailand.
Yeah, it's too cold.
This freaked me out.
What?
She's from BTH also. She has the same bag. What's her name?
Konstantinos, the exact same name.
No, it's so I have the same bag, so it's just. This is mine, this is yours.
This is mine.
Yours? Is it yours?
Mine.
Again, the same. Okay.
Keep an eye.
Where did you get this one?
I got it.
I think mine.
I got it.
Yeah, that's exactly. So that's their brand probably.
And actually, I got it for this trip specifically.
Nice having you guys here. Yeah, thanks.
Thank you for the question.
I should ask it. I just want to talk to you guys, but multi-threaded simulations. So it kind of reminds us. It reminds me of it. We used to have it. You remember McCarthy? But it wasn't as yeah, you didn't like that. But it actually has a potential. It's kind of like a mini OS as well. The mini it's an internal tool. It's also continuous. But it used to be called McCarthy. Now they switched because they have WindRiver instead. We got the Simix based solution. So it's very slow. I know, but they discarded the old solution. But they used to have a mini OS. A bunch of people worked on it, and they enabled a lot of flows, and it was still doing some kind of mini hosting, semi-hosting for regular workloads, but some of the code, especially. So the thing is, it wasn't meant for page faults and things like that. It could support them, but we didn't bother with all the other code. We didn't care about it. What we did want is to have a mechanism to do simulation for multi-threading, so that you can run p-threads. So you could write a piece of code, run it natively on a core, a user space emulation, but the p-threads would allow you to do data sharing and everything. This was
that the primitives continue to go. Yeah.
That was a framework for evaluating all sorts of really cool, features for data sharing.
What kept it back was the downside? Clear downside.
The need to support use.
I think it might be with the data sharing, right? I think the infrastructure is very hard to maintain in general. For Virtuoso, it's the same.
It is.
Like making it like the more things you add, the more you complicate stuff.
Yeah. No, but that was very.
The downside was functional. But for performance, it was not really doing the real.
Because we didn't care about the performance of the OS code, which you do, right? You want to evaluate OS flow, right? They only cared about the user space performance, but we had realistic data sharing. So we needed a pthread framework, but you don't really have code, right? You just need to do all sorts of semaphores.
That was slower than anything.
Yeah, but it could be a nice capability.
Like right now, I'm working on project. Not like simulation, but like I need multi-threading.
Right.
And the way I do this with pthread, basically when I want to have multiple, so basically each core has its own handler essentially. And whenever a core needs to perform page faults,
it talks with a different module essentially, and this module communicate together as a shared, as one application with multiple threads.
Right.
So it's not the most representative, probably.
No, but you needed to.
But I needed to do it somehow.
But
right?
there's pthreads code, POSIX code, or something
Yeah.
that you had to emulate it to not emulate, to actually implement.
I do it with many tricks, like magic instructions, which are propagated with simulator to explain to the simulator.
It's barrier calls and stuff.
Yeah,
and all this. Yeah, so that's not. Oh, now I remember. The main motivation for that was because at the time Intel started working on transactional memory. And that was the reason we needed multiple thread, but we needed it for microarchitectural implementation.
We see.
So you needed to do transactional memory, HLE, Lotte.
Oh, yeah.
Remember Ravi?
Yeah.
He's still with me. So we did move to. No, it was. Oh, no, that was ages before. Yeah, but no, when they did the transactional memory for Haswell, which failed, and then they shut it off, and then they did it again on Skylake, and then it failed, and they shut it off. Then they did it again. And then they eventually got the message, and nobody did it, but it was, so they had the two transactional memory, HLE, and another HLE plus. One was architectural, and one was micro. You can just align the lots, and one was replacing them with QX. So that's a large flow.
So basically, they wanted to intercept all the libraries with what you like. They wanted to have a binary, and then they write the interceptor that bypasses what the pthread would do and does whatever you want to do, which is very hard to do.
No, so it was, yeah. It was for that, and one additional reason was for right. So the comms guys, they have a bunch of flows of IP security, and these flows are multi-threaded, but they wanted to help software for them, and they run it on the simulator on the CA one. So yeah. Then also. Anyway, great. So yeah, this is my question. I just need to keep this. All right. Thanks.
Thank you.
Nice meeting you.
That's part of the if that is big.
That's a few. You want to test it a bit? I need someone to basically work with Constantina together. You won't really do it? Yeah. Both of you. What? We have nothing else to do, basically. Yes, guys, like let's record it for our purpose. Yes, we do a good job now. Come on. Like we only spent some days, weeks, and months working on it. Just a few days. Stuff. Like maybe we lost one. I'm just sleepless. Like maybe one line. Maybe one line. Kind special. This is on YouTube, by the way. The way you're sitting right now, and the way you just spoke. It's on YouTube. What's it? This is gonna be. Yes, you are. Yes, my listening. He's chilling and singing. But is there any microphone? No. Yeah. Good. Like this is gonna be in your defense. Whatever you do here.
No one knows what's happening behind here, so you can look at different.
Exactly.
Oh, you want something?
We could act up like a storm here. Is you here? Stop. Okay. Okay. Hi, everyone. Welcome back. So we're going to the second part of our talk and tutorial, which is basically the part where we dive into the details of Virtuoso. So let me share my slide deck. Yeah, sure. Can everyone at the back hear me? Can you hear me at the back? Okay, okay. Have you all sent us the email for okay, okay. We need to first set up our VM. So I'm gonna share with you right now all the SSH keys and the instructions. Okay.
Your email, you're sharing your email. You don't use my chat. I should share it.
I'm not sharing.
We can see the screen. The screen.
That's fine.
Keep sending me.
Some fighters like
Oh yeah, I guess you have all received the credentials. Yes, so the first thing you need to try to do is connect to the provided machine using the SSH key and the command. So in the commands, you can find the exact IP and the exact key needed to connect. And I would suggest that you do two things. First, try to connect via terminal. And the second thing you should try to do is try to connect via VS Code. Basically install the remote SSH plugin in VS Code and then add it as an SSH configuration. Let's take 2-3 minutes to figure out this. Is there any issue with connecting? Okay, sure. Just try first from the terminal, just to make sure that the firewall is okay. Through the remote SSH. Oh, VS Code works as well. Okay, terminal. Terminal is fine as well. So sure, because anyways, I'm gonna be showing you the solutions, everyone. So you do not need to actively code something. So yeah, so for this part of the tutorial, we're gonna have 3 hands-on presenters. I'm gonna present, I think, 2 parts. Then Konstantinos Harsh, who is a master student at ETH Zurich. He's our supporting cast and a DRAM expert. That's how I would proclaim him. He's interested in configurable systems, hardware, software, co-design, and memory system. Currently writing his first paper. He's a research assistant of the Safari Research Group, and he's going to help us with the emulator part of the tutorial. And then we have Konstantinos, who also gave the talk on Virtuoso. He's a master student at ETH Zurich. He's a research assistant with Safari. He's a longtime friend and collaborator. He has interest in coherence, microarchitecture, hardware, software co-design, and processing and memory. And we're gonna do 2 things. We're gonna have a set of slides for introduction to each part of the demo, and we're gonna use Markdown and VS Code terminal from the implementation. From your side, you do not need to implement actively because this will take lots of time, and we're not gonna go for blind coding or shadow coding. I'm gonna be discussing the solutions of each exercise with you, basically. So we're gonna have 5 parts in the tutorial. And the first part is the simplest one. So we'll have a hello world from Virtuoso and Sniper and emulator. So in part 1, we're gonna discuss how we can leverage Virtuoso for implementing new address translation techniques. In part 2, we're gonna discuss how we can leverage Virtuoso to devise fast physical memory allocations. And in part 3, we're gonna show how we can leverage Virtuoso to enable swap space support in emulator. And in the last part, we're going to discuss some future features and advanced use cases. So let's jump to part 0, the hello world part from Virtuoso in Sniper and emulator. So how do things work? So we have a user space kernel, and we find out that the Sniper simulator already had a very good infrastructure when it comes to coherence, interconnects, the cache hierarchy, the core models. And what we did essentially is we introduced in Sniper the user space kernel with all the modules and the MMU. So we built a detailed virtual memory subsystem on top of a detailed multi-core model, and this gave us higher IPC accuracy as we discussed before. How did we achieve this? So the user space kernel, as Konstantinos described before, when the workload performs a memory access, it sends the memory address to the core model. The core model performs the translation request, and the MMU model needs to decide, oh, is there a physical mapping for this specific virtual address? No.
So it's a page fault. Send a message to the user space kernel. The page fault handler wakes up. We binary instrument, and then we ship back the instructions to the core model so that we are able to track the latency as well as the outcome of the page faults. How did we do this in Emulator 2.0? We are using again the user space kernel. We enhanced our emulator with an MMU, and on top of an existing cache and detailed main memory model, we have a detailed virtual memory subsystem, which, as Harsh will show later, unlocks very interesting studies. Yeah, so the first thing you should do is to log in through terminal and basically clone the following repo. Let me know once you're done. So let's give 2 minutes to that. Yes, I agree. Yes, the coherence is a very big part of Snipe. Yeah, it was very well modeled. Yeah, let me check. One moment. Also, if anyone on YouTube has questions, you should raise them up so that we can help if you're doing it also on the fly. Unfortunately, we cannot provide VMs to YouTube people because basically we do not know you. We don't have the affiliation so that we can track you in case something goes off.
But locally should be fine anyway.
Yes, local should be fine. I think if you simply clone and then install the dependencies as I will show you, it's going to be perfectly fine. So once you clone the repo, you should basically git checkout to the part 1.0 and part 1.1. And after you do this, I suggest you make this clean. Make this clean essentially freshes up and cleans up all the auxiliary files and the downloaded files of the simulator. And with make, you can then build the simulator. I suggest you use the ones for using VMs. Yeah, the ones you're using VMs should basically use 2 cores. Yeah, correct.
Yeah, we're gonna stay here for 1 minute and then we're gonna continue. Let me know once the process starts compiling because it will take around 10 minutes to compile in the two-core VM. Only the first time. When you compile the next time, it won't take this much. This is only for the VM because for the other one I have tested. Oh, you need a key as well? You need a key? Okay. Yeah, more than 30 VMs is quite expensive, so I would suggest that you work in pairs in case you... Yeah, you can work in pairs if you want. yeah, building sniper and a 2-core machine will take some time. No, it might get stuck in the beginning. Oh, you just cleaned? Okay, yeah. Cool. After this is done, then we're gonna do our warm-up, basically. Yeah, the cat is warming up, basically. So while it's compiling for most of you, so I'm gonna give the intro to the page size prediction. This will be our warm-up. So let me walk you through that, and please make the session interactive, which means that you can ask questions. So the first thing we need to do is to understand the MMU design of Virtuoso. And I'm going to give you a walkthrough of how we designed the MMU inside Sniper. Yeah, I will share my Visual Studio Code. So. Let me get my mouse. So the file structure in Sniper looks like this, and there are two key things in this directory, right? The first key thing is the core. So in the core, you can find all the structures that exist in the core, which means we can figure out things about the memory subsystem, the caches, DRAM directory schemes, a DRAM, how we architect the MMUs, and most of Virtuoso's implementations lie underneath a parametric DRAM directory. MSI, this means that basically we're using a DRAM-based directory. And we placed everything here. All our translation components are under translation components, which means the TLBs, the page size predictors, and many more things. So let me give you an overview of a baseline MMU that resembles what could be there in a modern core. So this is the baseline MMU code. I'm going to try to walk you through along with the markdown file. So let's see what the MMU has to begin with. Like what does the constructor of the MMU look like? So the constructor of the MMU looks in the following way. So the first thing we have, and I generally use this as a practice in most of the classes that we introduce in Virtuoso, is logging. And I suggest to everyone who wants to do like this sort of fine-grained debugging and understand how when things work and when things do not work, is to log everything you're doing. When you log everything you're doing, it's much easier to debug, basically. So for every component, we create something we call a log file. And basically, we can figure out later debugging statistics about how the MMU performed, what are the physical addresses, what are the latencies, and understand what's going on. Then we have two components which are the key parts of the MMU. We have the page table walker, and we have the TLB subsystem. So let's see the TLB subsystem first and how we initialize it. So the TLB subsystem is basically initialized using a TLB hierarchy, and right now we need two new variables. Oh, what's the issue? Okay, so we need two new variables to represent the page size prediction parameters. I'm going to talk about this later after I introduce page size prediction. What's the problem? Oh yeah, sure. So after we instantiate the TLB subsystem, then we need to instantiate the page table walker. And for the page table walker, we need some information. We want the page table type and the page table name. So how do we read parameters from the configuration of Sniper? Sniper follows a specific format when it comes to configurations, and we can read it using this exact command. So basically, what are we saying here? We want to retrieve the simulation object, we want to retrieve the configuration object, we're going to retrieve the string that matches this specific page table type, this specific string. And To give you a rough idea of what this would do, it would basically, when we provide the config to Sniper, what happens is that it's gonna, well, let's say we provide the 4-level radix configuration, then what's gonna happen is the following. It's gonna come here, it's gonna read these parameters like perf model, macOS host, page table type radix, and this way you will be able to figure out what is the type of your page table, what's the type of your, the name of your page table. And given this, you can add your new parameter here, which doesn't affect anything, and call it value, right? So next time you wanna be able to read this value, is this basically. You would come here in line 73, and I would say, okay, I want to read my new parameter. Let's call it string parameter. Yeah. Yeah, we have a new parameter here. We define it, and the new parameter, let's call it new parameter. So when we read basically this new parameter, then we would get back the word value, as you can see here, right? Yeah, this is one way to do it. This is Sniper specific. This is not Virtuoso specific. This can only be used, it can be used in many other simulators, but like for now, we're talking about the way to read the configuration in Sniper, not in Virtuoso. So then what we need to do is we need to activate the page walk caches. So we activate the page walk caches, we instantiate them, and let me close this so that you can see better, basically. We're instantiating the page table walk caches. We use 3 of them for the first 3 levels of the page table, and we defined the latencies for each one of these 2. And then the most important part is the page table walkers. So the page table walkers here, why do we instantiate them as MSHRs? Because essentially we need to model the contention of the page table walkers. What does that mean? If we are full in terms of L2TLB misses, for example, then we need to overflow in the MSHRs, and that's not possible, so which means we need to wait. And we want to model this contention in the MSHRs, and that's something that we take into account in our simulator. So we finished up initializing all these, and then a very important part, again, of your debugging strategy would be registering statistics. So this is one way that Sniper, again, uses to register statistics. For example, here I'm saying, oh, please register these statistics for me. This is the name of the module I'm using. This is the core that owns this module. This is the name of the statistics, and this is the name of the statistic, and this is the variable that you should be tracking. So every time the number of translation changes, we have a reference to the number of translations. So we would be able to print out these statistics at the end of the simulation and figure out, oh, this is the number of translations I did. This is the latency of my page table walks. This is the total translation latency. And this can be very helpful when it comes to debugging again. So we're done then with initializing the MMU, and yeah, done.
What's the difference between the name and
the name between?
The name and the next thing?
The name is the name of the component. So in this scenario, the name is MMU, and and then the third one is the name of the statistic you want to keep track of. Okay, let's see what's next. So we instantiated this, and then we need to see how we perform others translation. This is the second part of the MMU. So as we discussed here, this function is called by the memory manager and offloads the translation to the MMU. So imagine in Sniper there is a concept, an abstract concept called the memory manager, which essentially is the module responsible for handling all the memory accesses. And we have this function, the perform others translation function in our basic MMU, that has one job. It needs to give us back the physical address. So it gives us back the physical address, and internally it handles any sort of timings that it wants to handle. So how does it do that? the first thing we need to do is access the TLB subsystem. So the TLB subsystem is part of the MMU and is responsible for storing the recent translations to speed up translation. And how do we do this? We perform a lookup in the TLB hierarchy to find the translation of the virtual address. The way we do this is by iterating throughout the TLB hierarchy at each level and at every TLB at each level to figure out which component might have the final translation. So let's see how this works. So the moment you receive the perform address translation request, the first thing you need to do is instantiate all the variables you need to have in order to track whether there is a miss, there is a hit, and all of these things. So how does that work right now? So we have a multi-level hierarchy TLB, 2 levels in our scenario, and at each level, we might have more than one TLBs. For example, we might have one TLB, 2 TLBs at the first level, one that stores 4 kilobyte pages, another TLB at the second level, one that stores 2 megabyte pages. And when we're missing these two, we access the unified L2 TLB, which supports, for example, 2 page sizes, both 4 kilobytes and 2 megabyte pages. So the first thing we check is whether the TLB stores instructions or not. If it stores instructions, then we cannot send it to the data TLB, the request, we need to send it to the instruction TLB. So if it stores instructions, and the request is an instruction, so the demand is for an instruction, then we do the lookup and we retrieve the TLB block info. The TLB block info essentially is the variable that tells us, will we have a hit in the TLB or will we have a miss in the TLB? So if the TLB block info is different than null, this means that the TLB returned something back and said, okay, I found something in your TLB, and I'm going to tell you right now, I know the page size, I know the final translation, I know the level that you hit, I know the TLB in the level that you hit. If this is not an instruction and it's data, again, we do the same procedure, but we first check if the TLB is able to store data or not. Again, same thing, we track the TLB block info to figure out whether there is a hit or a miss. If there is a hit in the TLB, then we break immediately. And we break immediately and we figure out in which TLB we hit on. So we initialize the charged TLB latency. Imagine the charged TLB latency as the total latency we would charge for accessing the TLBs. And as I write here as a comment, like we perform the TLB lookup, and we now need to decide what latency to charge better based on whether we had a TLB hit or a TLB miss. If it is an L2 TLB hit, you need to change the code below to take into account the page size prediction and the page size used in the TLB hit, and we will discuss this later. So if we had a TLB hit, the first thing we need to do is retrieve the physical page number and the page size. So how do we do this? So we figure out first what is the hit level. What is the hit level means that if we hit in the first level of the TLB, then we would charge the latency of the TLB that we hit at. For example, even though we might have 2 TLBs and the second one might have a large access latency, it doesn't really matter because the one we care about, because the access is performed in parallel, the one we care about is the one you hit. So this is the one that's going to deliver the final translation. Of course, we might spend energy, and this is something we take into account in our experiments.
So would you be able to charge different latencies for TLBs at the same level? For example, the L1 DTLB, L1 ITLB?
The I and the DTLB are not accessed in parallel because you cannot have a request which is both for data and for instructions, right? That's not possible.
But then in that case, you mean that they're tightly designed. You couldn't come up with a system where if you want to charge different latencies for L1I, L1D, you couldn't with the simulator.
We could.
As from a modeling point of view, basically.
From a modeling point of view, you can technically do anything you want, right? It's a matter of whether what you do makes sense at the low level or not architecturally. It's not only a matter of whether I can code it in C++, right? So how does that work? We find out the hit level and we find out the maximum latency for each TLB at that level. And are we in the hit case? Yeah, we're in the hit case. So if we, let's say, hit at the L2 TLB, then we need to find the maximum latency that we had at the previous level, which means level equals 0. And the level equals 0, we have two TLBs, the L1 for 4 kilobyte data and the L1 for 2 megabyte data. And in this scenario, we would have the maximum latency between these two TLBs because this would be done in parallel. So we charge this latency and then we find out that, okay, we hit at the next level. So if we hit at the next level, we need to iterate right now through all the TLBs in the next level to figure out to which one we hit at. So we figured out which one we hit at by keeping track of the hit TLB in that level. So we charge the TLB latency based on the one we hit at. And at the end of the day, what we do is we take into account all these latencies and we increase the elapsed time. How do we do this? In Sniper, that's very tricky. You need to be very careful in how you do this. So essentially, we need to progress the clock to the time that the TLB latency has been served. So why do we progress the clock here? Because let's take a scenario where you have a TLB miss, right? And you need to pinpoint the exact time your page table walk started. You need to progress the time after the TLB miss has happened and you have served the miss. You have basically figured out there is a miss, so that you know that the page table will start at T1 instead of T0, which is before the TLB access. So if there was no hit, the only difference is that we don't have a hit level here because we missed in everything. So what do? We need to take the maximum latency across all levels, and we accumulate these at the end. These are not the most interesting part of the virtual memory subsystem because, as we discussed before, and everyone before in their presentations, they demonstrated that we don't hit a lot in the TLBs. So basically, we are experiencing lots of TLB misses, which trigger page table walks. So let's see the scenario where we have a TLB miss. So if we have a TLB miss, we trigger the page table walk. What do we do first? We need to find out when was the page table walk triggered, which is using again by taking a snapshot of the elapsed time. And the first thing we need to ask is, do we have a slot to start the page table walkers? Because we discussed before, there's a concept of MSHRs and a contention for the page table walkers. So we call this function to figure out the following. So the system has n walkers, let's say, that can be used to perform the page table walks in parallel. But we need to find if there is any delay in case all the n MSHRs of the page table walkers are taken over. So if this is the case, then we need to adjust the delay because the page table walk would start with a delay, right? Then the next thing we need to do is we need to figure out the pointer to our page table. You can think of this as an equivalent of the CR3 register. I write it here, so okay. So we're starting the page table walk at this point in time. And then we have this function called perform page table walk. And I will not go into the details of this function right now, but you can think of it in the following way. This function will tell us two things. It will tell us, is there a page fault? If there is no page fault, then what is the result of the page table walk? Which means what is the physical address and what is the page size? So we need these two information to figure out what is the final physical address. The second most important thing after we do the page table walk is what is the latency of the page table walk. So we need to keep track of the total walk latency. And in this scenario, we take it as a member of the page table walk result derived from the perform PTW class function. So the interesting part is we cause a page fault. If we cause the page fault, then we need to find out what is the page fault latency. And here there are multiple ways in Virtuoso doing that. One way, which is the most straightforward, is you set a static page table walk latency of 2000 cycles, and then you basically don't want to do that because the latency is very volatile, and you cannot basically do experiments which are very accurate with this metric. But after you charge the page fault latency, you want to restart the page table walk. Why do you want to restart it? Because the page fault essentially will have filled up, will fill up your PTEs with the final translation after the page fault, which means the virtual to physical mapping is already established, and then you need to restart your page table walk so that you can finally find the virtual to physical mapping. So once we find once we restart the page table walk, there is no way here at this point that this will fail. There is no way, I write as a comment, there is no way that this will lead to a page fault. Why it cannot lead to a page fault? Because we have already serviced the page fault. Is there any question on YouTube, maybe? Okay, sure. Anyone else?
So when you're doing,
How's the compilation going?
It's done.
Oh, it's done. It's working, right? It's working. I mean, it has compiled. Yes, that's very detailed. It's a very detailed question right now. So this has to do with how Sniper, this is very specific to Sniper, basically. Sniper is an event-driven simulator, and we want to keep track. We want to play basically with the time of the user thread, which is the application thread. There are different threads, like the network thread, which is not a user thread. It's a thread that works asynchronously or with different, let's say, interacts with different components, it's shared among different cores, and it doesn't respect the timings of a single core, right? So in this scenario, we wouldn't use a user thread, we would use a simulation thread. But I don't want to go into these details because that's too much, I guess. So the interesting part is here, like we restarted the walk, we figured out the new latency of the walk, we figured out the new page size and the new physical page number. And after we do all these, we basically need to handle the case again of the page fault. If we had a page fault, then what is the problem with the page fault? As I discussed in my slides before, the application stalls when you have a page fault. It stops, you context switch, you bring the OS into the game, it performs operations, and after it performs some operations, you basically are able to stop the core, you take the translation over after you restart only. So how do we do this? We basically issue some sort of memory barrier. This memory barrier essentially tells us, okay, you're going to stop for 2000 cycles, and you cannot issue any instructions in parallel with this specific instruction, which means it's called a serializing instruction. It's like a memory fence, basically. And after that, we set the elapsed time to the final time. And the final time is the time it takes to start, the time where we start the page table, the delay we caused because of the contention, the total walk latency, and the total fall latency. Those is the total time we spent in, this is the final timestamp at which we will have the translation ready. So does anyone know what is the step, like after we perform the page table walk, what is the next thing we need to do? Like we figured out the virtual to physical mapping. Then what should we do next? No, but let's say we updated the page table, that's done. Exactly. So the first thing you need to do after you do this is refill the TLBs. And this is the piece of code here that refills the TLBs. Essentially, we're iterating over all TLB levels. Some of the TLBs might allocate on a miss. Some other TLBs might not allocate on a miss, which means it has an exclusive versus inclusive behavior. And we are able basically to refill the entry inside the TLBs. I won't go into much details. This is something that's purely functional. There's no timings correlated to that. It's only a matter of propagating the evictions and the insertions that will be correctly. And last but not least, what we need to do is we need to return the physical address. That's the key part. We return the physical address, then the memory manager takes over and satisfies the memory request using the new physical address. It doesn't use the virtual address provided by the program. Are there any questions regarding the MMU? I don't want to go into more details because I guess we spent some time on that. Okay. So let's see right now what is page size prediction and why do we going to use page size prediction. So as we discussed before, the TLB subsystem has multiple TSBs. Some support 4 kilobyte pages, some that support 2 megabyte pages. And the question is, so before we access the TLB, how do we know the page size? So for example, to access the TLB, we need to figure out an index. and the index is calculated based on the page offset. But the page offset is different for each one of the TLBs. If one supports 4 kilobytes and another one supports 2 megabytes, then the offset is different. And if the same TLB supports both 4 kilobytes and 2 megabytes, we need to be changing offsets in order to calculate the indices. An example is the following. So let's say the page size is 4 kilobytes. If the page size is 4 kilobytes, we need to access, even if the page size is 4 kilobytes, we need to access the DTLB, both the 4 kilobyte one and the 2 megabyte one. Why? Because we do not know a priori what is the page size. We would need to figure out on the fly that, okay, there's a hit in the L1 DTLB, and you did a mistake for not for accessing the L1 DTLB with a 2 megabyte translation. So we do two parallel accesses, we pay for them, which means we pay for energy, and potentially we might pay for some latency in some specific cases, especially when it comes to the mispath. And yeah, we didn't access in this scenario the L2 TLB. Second scenario, the page size is 2 megabytes. Again, the same thing. So we need to access both the TLBs because we do not know a priori that the size was 2 megabytes, and we cannot avoid the access to the 4 kilobyte one. So again, we perform two parallel accesses. And an interesting scenario here is like the page size is 4 kilobytes. We miss in both TLBs, the L1s, but we have an L2 TLB hit. So we miss there by two parallel accesses. We have the L2 TLB, and we hit with the first try. So how many do we have? We had two parallel accesses plus one L2 TLB access for the 4 kilobyte size. The worst case scenario is this. The page size is 2 megabytes, but we have a TLB hit, which means we have two parallel accesses plus two accesses in the L2 TLB, one for 4 kilobyte, assuming a 4 kilobyte page size, and one assuming a 2 megabyte page size. So we have two parallel accesses in the beginning plus two L2 TLB accesses. So basically we perform, instead of accessing, for example, two TLBs, one at the L1 level, one at the L2, we accessed 4 TLBs. Essentially, we accessed 4 TLBs throughout the translation path. So the idea here is the following, it's extremely simple. Let's predict the page size. So when we find out there's a miss, let's say that we don't want to change the L1 DTLB that stores 4 kilobyte and 2 megabyte translations, right? Because they're on the critical path and it's very hard changing them. So we miss in both these structures. And we have a page size predictor that tells us the following information. So the page size predictor will tell us, is the page probably a 2 megabyte one or a 4 kilobyte one? Let me predict first. So in this scenario, for example, the page size predictor could say, assume that the page is 2 megabytes, because I have allocated in the past most pages as 2 megabyte pages. This way, how many accesses would you do to the L2 TLB? 1, because the final translation would be at the 2 megabyte granularity. This way you would have a lower TLB hit latency and reduction in energy. And the way we would simulate that is with a sniper space kernel. So to simplify the experiments a bit here is that we don't want to use a user space kernel that we discussed before. We want to embed our kernel in Sniper so that we simplify a bit the tutorial part. And let's head to the demo time. Is everyone ready for demo? Okay. Let's try some simple stuff first before we jump into the demo. Can you try to run the example that we have? So there's a file, I think, called runexample.sh. I just want to make sure that everyone has this ready so that I can proceed. Yeah, I will come over. Yeah, in the VM. So in the VM, you cannot run with pin because it's a VM. So we were going to use traces, which is a bit easier, basically. I'm muted? No, I'm not. Yeah, I'm not muted. So in the VM, it's better to use traces. Just, I'm sharing my screen, right? No.
You are sharing screen. You are sharing.
I am sharing, right? Okay, so here, we're using right now an executable binary. So instead of using a binary, we want to use a trace. So there's a script called download traces. I would suggest you run this script so that we download some traces so we can play with. I'm going to show you how you can change the script to run traces. So the general way of running Sniper is the following. Sniper requires a configuration file. It requires an output directory, a stop condition. In this scenario, we stop based on the instruction count. And it also needs either a workload, which is in a binary format, or a trace. And the trace is, imagine it as a pre-recorded version of a binary being executed in a system. And how do we do this? /run sniper -c, the config file, -d, the output. We generate the statistics. We stop after 10 million instructions. Here, no, 1 million instructions. We'll run for 5 in this case. And we're going to run with traces. So we're going to use this workload. And we pick the rnd.shift because it runs fast and we can run quickly, basically.
Taking some time to download.
Is it slow?
Can it be an executable?
It cannot be every executable. That's not a limitation only on our side, so it depends on the simulator. For example, in Gem 5, it could be any executable. In Sniper, it cannot be any executable because Sniper relies on a specific type of format and like trace pin essentially to be able to take the commands. And this does not help with running every application. For example, it's very hard running Go applications or running this sort of coroutine-based applications like C++ fibers, let's say. It's around 6 gigabytes of traces, right? Okay, sure.
Open again the screen that shows the changes in the script.
Yeah, sure. Yeah. So here, instead of using the binary, you're using the trace. So you're going to point to the trace. So what you're downloading right now is downloading a bunch of traces. And what you need to do is point to this specific trace. It's going to put it under traces. And then instead of running here with a workload, the binary, you specify that I'm going to use traces into my simulation. I'm going to also make, but I have 256 cores compared to you. So it's going to compile in 1 minute instead of the amount of time it took to you. Yeah, sure. This one, right. Were you able to run it now? Okay, cool. So you should see then something like yeah, I would see the same thing, I guess. Yeah, I see the same thing. So we were able to run our first example. And yeah, I'm going to walk you through how we do the page size prediction. So imagine that the page size predictor is basically a history. We use a history-based approach. You use a two-level adaptive history component with both global and local history. And for the history, we use a DQ. It's a queue basically that stores the pages of the last 4 translations. And it stores 12 for the 4 kilobyte and 21 for the 2 megabyte pages. And this history is basically used to form an index. And we used another table. We use basically 16 of these 16 tables. Using the global history, we point to the corresponding table, and each one of these has 32 entries. And we use the address, the virtual address, in order to figure out the index inside the table. So how does this work? So the predictor takes a virtual address as input. Let me walk you through the predictor so that we open it up. It's under common core, memory subsystem, translation parametric DRAM directory, translation components, and page size predictor. So let me close these. Okay, our predictor needs to predict the page size, right? So how do we predict the page size? So we form first the history index, and for the history index, we basically get these 4 bits. Essentially, these 4 bits create an index, which we will use for the next. And let me show you how we do this. So we take the table index. The table index, how do we calculate it? It's the bits 16 to 12 from the virtual address, because it's a 32 entry table. So we need this amount of bits, we need 5 bits. And for the final prediction, what do we access? We access the tables at the history index using the 4 global history bits, and the table index, which is formed based on the virtual address. So we choose the table based on the global bits, and then we use the address to figure out to which entry inside its table we're going to. And then we figure out that, okay, we need to answer the question, is our prediction does it predict a 4 kilobyte page or a 2 megabyte page? And how does that impact things in any scenario, right? So yeah, when we update, how do we update the predictor? The thing we want basically is to change the history index, because the history index right now changes because the last 4 translations we did might have a different result. We need to basically push a new result into our global history index. And essentially, that's the key difference here. Let me show you though how right now we integrate this into the MMU. So in the MMU, so the memory management unit uses again the TLB hierarchy to perform others translation, right? So when we have another perform others translation thing, the MMU first checks the L1 TLBs. And if there is a miss in the L1 TLB, the MMU needs to check the L2 TLB. But the MMU calls TLB subsystem predict size to get a prediction for the page size before accessing the L2 TLB. And what do we do in this scenario? Let's see. Predict. Okay, so if the page size prediction is enabled, then we need to find out the predicted page size. So we give to the TLB subsystem the address, and it gives us back a number, 12 or 21, right? And after it gives us back the number 12 or 21, we can figure out, in case there is a miss to the TLBs, to the first level of TLBs, how many accesses we need to do essentially to the L2 TLB. So in case hit in the L2 TLB, then we would come to this piece of code and we would be like, okay, so we didn't hit at the 0 level, where it's the L1 TLBs, but we hit at the first level, which is the L2 TLB. So here we have a corner case. So if the TLB hit level is not 1, this means we don't have an L2 TLB. Let's say we have an L3 TLB or something like that. Then we're charging the latency normally as we described before, which means that we're simply, this is our hit TLB, this latency. But with page size prediction, that's not what we do. If we are at the second level, hit level equals 1, and the page size prediction is enabled, and we figure out that we predicted successfully the page size, then we charge the latency based on the L2 TLB correct prediction latency, which is lower than the latency of accessing and missing in the L2 TLB, or performing 2 accesses to retrieve the page table size, based on the page table size. However, if our prediction is not successful, then we need to pay the price of our misprediction, which means that we need to pay the whole path of accessing the L2 TLB. We need to access for both 4 kilobyte pages and 2 megabyte pages. Is that clear, everyone, until now? Okay. Anyone else? Yes. So the misprediction latency, that's a good question. So the misprediction latency is something that in general the simulator designer should take care of. So here you need to understand conceptually at an architectural level, what is the difference between performing one access to the L2 TLB in terms of lookup latency, and what does it mean for the L2 TLB to be accessed 2 times? So we change the configuration of the simulator, as I will show you now, to integrate this information, this piece of information. So let me go to the configuration. So we have a configuration here with a page size prediction, and we are basically including this MMU configuration. And in this MMU configuration, which is the base one, we basically added 2 new configurations. The one is the misprediction latency, which says, okay, if you mispredicted, then you need to pay the price of the full L2 TLB latency. Yeah? Can you repeat? Sorry. Oh, sorry. Yeah. So when you need to pay the price of the full misprediction latency, you need to pay the full price of accessing the L2 TLB. And in another scenario, you have a correct prediction latency, which means that you access the L2TLB only a single time, which results in almost half the latency of accessing the TLB. Yeah, sure.
The way you design this, the page size prediction as a module is tightly coupled with the TLB subsystem.
Yeah.
But you may want to use the page size prediction as a utility for some other parts of the virtual memory system.
Yeah.
Is this solution supposed to be coupled tightly with TLB subsystem, or is this a modeling specificity? Like one could
So the way this is, so basically the page size predictor as a class, it simply gives you an API. The TLB subsystem uses the API, but it's not integral to the whole system, which means that someone could simply take from here the page size predictor, which we implemented as a factory essentially, and being able to implement their own page size predictor.
essentially that is member in some other class.
Exactly. So you want to use it at the OS level or some other class, then you could pick it up and use it the same way you would use it in the L2 TLB. So here we chose to couple it with the TLB subsystem though. Okay, so what is the difference here? Again, when we have a prediction success, we charge the L2 TLB latency, given that we have a correct prediction, much lower than the TLB miss latency when we have a wrong prediction. We pay 4 cycles essentially here. And if we do not predict correctly, we'd pay 10 cycles. So now let's see how this works in action. So we have prepared a script for you. You can check it. It's called run part 1.0. Can you open it up? Sure.
We need to rename the trace.
I know, I'm using the same trace. We're using traces for the. Yeah, no, you don't need to, I think, because for this specific like run, I'm using traces. I do not use executables. So the file is run part 1.0.sh, and I will explain what we do in this file. Did you open it up, guys?
Yes.
Okay, sure. So we created a new configuration file first. The new configuration file is called Virtuoso page size prediction. And we're using a specific trace here, and we want to find out, let's try to find out how our technique works, right? So we have 2 runs that we're going to do, just for the sake of simplicity and for speed in the workshop. We're going to do 2 runs. In the first run, we're going to turn off transparent huge pages, okay? And in the second run, we're going to turn on transparent huge pages. And what are we going to see? We're going to see basically how our predictor works. That's what we want to see, basically. And let's run together, basically, this one.
Is it important for us to understand what it means when you say transparent huge pages for the rest of this exercise?
I will go into part 1.1 much deeper into the transparent huge pages. For now, you can think of transparent huge pages as the way to activate 2 megabyte pages in the system or not. So I want to see basically the following. I want to see, in the case of having only 4 kilobyte pages, of course, my predictor can figure things out, right? But the question is what will happen when I install 2 megabyte pages in the system.
So in essence, transparent huge pages provides you both.
Yeah, exactly. Transparent huge pages can give me both 2 megabyte or 4 kilobyte pages. Okay, so we're running the examples. Yeah, you can think of the simulator simulating, let's say, 100 million instructions for an hour around for the most demanding workload. So if you want to simulate with your workload, 1 billion instructions will take around 10 hours. Of course, that's not ideal, but that's why we're working on it, so that you can basically do it faster. Yeah, a bit better than M5, which would take 1 week. So, yeah.
There's a big difference between the race that you said and actually running the executable.
Yeah, of course. Yeah. So when you're running, so this heavily depends on the software engineering part of the story. What do I mean by that? Usually Sniper and many of the simulators, basically Ramulator and SamSim, for example, use trace-based simulation, right? So what does that mean? It means that I'm feeding some instructions or some memory addresses inside the simulator, but this means that it's much faster, right? I don't need to produce any instruction. I don't need to execute any binary. However, the problem is the following. I cannot capture some effects with dynamic, which have to do with dynamic behavior, right? In this in these simulators. And yes, in Sniper, you can do both. You can use both traces and the execution driven. As you correctly say, the execution driven is more expensive in terms of execution time, but I commend the authors of Sniper because they have done a very good job in how they programmed the parallel model of consuming and producing the instructions. So basically, you have two entities in Sniper, one that produces the instruction stream and another one that consumes the instruction stream, basically. And they are, let's say, they're running as asynchronously as possible so that you can minimize the effects of execution-driven latency. Yeah, so we have our results. So let's analyze a bit now. Did they finish? Perfect. Okay, how do we read results? That's a very important part of simulation. And I typically, one thing that impresses me in people who are very good in research is the way they're basically reading results. And some of you might know my best buddy at lab, Rahul Bera, who is the best result reader. He's not here, but he recently took his PhD and we're very happy to have him still with us. Okay, let's see our results. So Sniper, we make Sniper output all the results in the sim.stats file. In the sim.stats, we basically have a list of all the results, right? And I'm basically putting them side to side. So on the left, you can see the results when we have transparent huge pages disabled, and on the right, you can see the results when we have transparent huge pages enabled. Yeah. Yeah, sure. So the other output files are, for example, the whole database with the statistics. So Sniper creates an SQLite 3 database which has all the statistics. It has a sim.out which has a summary of the statistics, which is, in my opinion, is not very useful because you need to dive deeper into all these stats on your own and all these metrics. Then it has simulation configuration information, which means that you can figure out what configuration you use to run your simulation. And then if you want to enable logging, as I described before, then you would see all your logs inside these folders. We also output a heartbeat so that we can see that our simulation progresses and it doesn't stall. This is very useful, especially when you run long-running experiments for billions of instructions, and simulations take a lot of time, basically. So again, let's see the stats here. Let's go to the stat called, let's see how, no, sorry. Yeah. So let's see our predictors here. Our predictors, of course, are working very well, right? So our predictor can easily find out if the page is basically a 4 kilobyte page or 2 megabyte page. Why is that? The reason this happens is because if we have lots of 2 megabyte pages, then Linux, and as we configure it here, will start giving you lots of 2 megabyte pages. So you'll have a very small number of 2 megabyte pages. And you will probably hit a lot in the L1 DTLB that has many 2 megabyte pages. An example here, if we see the hit ratio in the L1 2TLB, let me go here. So let's see the following. So in the first scenario, when we have transparent huge pages disabled, then, sorry, give me a second. Okay. So yes, as you see here in the L1 DTLB that stores 2 MB translations, we have 1.2 million accesses and we have 200,000 misses, around 80%, I would say, or a bit higher hit rate. However, in the case where you're using 4 kilobyte pages only, we have again 1.2 million accesses, but we have 560 565,000 misses in the L1 DTLB for 4 kilobyte pages. And how would this help essentially? This would help us in the following way. So if I wanted to prioritize, if I know that most of my accesses are at 2 megabyte granularity, then I can do two things. First, which I would do not explore here, I can disable accessing the L1 DTLB for 4 kilobyte pages. That's one way. Or I could make the access serial to the 2 megabyte one. Then another thing I could do is basically I could change the probing order in the L2 TLB. I could first access using the 2 megabyte prediction and then switch back to the 4 kilobyte one. And this would help me basically get back both energy and hit latency. Any questions? Okay.
Essentially, in this case, in the case that you prescribed, 4 kilobyte access is more expensive if you were to serialize. So with more fragmentation, I mean, more memory pressure, it would become more expensive to access memory.
Sure, yes, that's true. Yeah. Were you able to run it? Everything worked? Okay, sure. Great. So this was part 1.0. You basically run these two traces. We check the results. You were basically able to predict the page size. I mean, this was a simplistic example, but you get an idea of what can happen with 2 megabyte paging. And yeah, we're gonna move to the next part. Konstantinos is gonna talk about transparent huge pages and the new policy, basically, that we can employ there. Let's take a 5-minute break and then we continue.
Can you hear me? Perfect. So we are going to start. Can you see my screen? No, I haven't seen. Perfect. So this is the second part of the Virtuoso tutorial, and we are going to essentially implement an intelligent page size selector via hardware feedback. So let's see a little bit what we're going to do. Then we're going to explain how Konstantinos did maybe in a little bit less detail how the allocator works in Virtuoso. And then we are going to implement, I have comments and stuff, we're going to comment, we're going to see how to implement this mechanism. So first of all, let's talk about transparent huge pages. So Linux with its allocation policy is very aggressive. When a 2 megabyte page is free, Linux without any policy allocates immediately this 2 megabyte region. So is this always the best decision? FreeBSD, for example, and multiple other research proposals take a different approach. So, for example, the part of the virtual address space is mapped to a 4 kilobyte region, and this 4 kilobyte region is in a 2 megabyte region. So this 2 megabyte page region is first reserved. So we are not allocating the specific 2 megabyte region, but we're reserving it. If we continue and continue to allocate, we decide to promote. So if we, for example, have X number of out of the 512 4 kilobyte pages allocated, then we promote to a 2 megabyte page. But this is a very naive mechanism. The question is, can we do better? So in this specific example, we are using utilization as an indicator of whether or not to promote. What about the temporal locality exceeded by the data in the 2 megabyte region? Should we sacrifice the whole page if the access frequency is low and reuse distance is high? Also, what could be a good indicator for the benefits? Could it be the TLB MPKI? Could it be the translation cost that we pay? So in this specific tutorial, we're going to choose one of these and we're going to implement this in Virtuoso. Specifically, we are going to calculate the translation cost for the 4 kilobyte pages inside the 2 megabyte region. And we're going to use this as a feature, as an indicator, essentially, to promote this specific 2 megabyte region into a 2 megabyte page. So after taking this out of the way, we can go on to the demo. Are there any questions? Perfect. By the way, if anyone wants to follow, we say again, there are VMs available. If you want to follow. No, it's on.
Sure.
Cool.
That's perfect.
Let's see. Perfect. So we don't need to download anything more. We have everything from the previous part. You cannot see it.
I think it's stuck. On the meeting, it's fine.
On the meeting, it's fine. Yes. Here, I'm not sure.
It's duplicated screen. I saw duplicated the screen.
What can you see now? Okay, cool. It's not duplicated. Okay. We'll fix this. So you can see this on the, okay.
On the meeting, I can.
Okay. Mm-hmm. Perfect. So what we're going to do is, first of all, we're going to explain how the allocator in Virtuoso works, and then we're going to work from there. So in Virtuoso, we have implemented many allocators, including the reserved THP. So let's see some very important, we can also put this here. So this is for the implementation. Okay. So let's see the main sort of functions that we need in order to understand the allocator in Virtuoso. So first of all, the main function essentially that is called is the allocate function. So in the MMU, when we in the page table, when we want to have a new page for our data, we need to use this allocate function, which essentially takes the size that we want to allocate, the address, the virtual address that we want to allocate, the core ID and the page table location, and we're using this to, and the reservation THP essentially returns the physical page as well as the page size for that specific allocation. So of course we have, if in case it is a page table allocation, we have a different way to allocate. So in this specific case, we're using body allocator, but this can be anything. And the important stuff for this specific mechanism that we're going to show is line 431. Essentially, we're checking whether or not this allocation can happen in a 2 megabyte page or in a 4 kilobyte page. If we have a valid answer, if we got a valid answer, we either we have a reserve or we use an existing 2 megabyte region. So we checked and we saw that we are using a 2 megabyte region, or we just reserved this page. So in this specific case, we just return the 2 megabyte page that we reserved. Otherwise, we are in 4 kilobyte mode, then we return the 4 kilobyte page with the appropriate size. So in case we cannot allocate with our reserved THP, we are falling back to our body allocator essentially as a fallback. Let's see the check for 2 megabyte allocation. So we're checking whether or not we can allocate with 2 megabytes. Let's check this function. So right here, we are keeping essentially a map of all 2 megabyte regions in the system, physical memory regions. And we are calculating, first of all, we're calculating which region matches our address. We have a specific address, we shift by 21, which are the bits for the 2 megabyte VPN. And essentially, we are trying to find in this map whether or not we have something that exists. So if we don't find it in our map, we start reserving it. So we got the body allocator and we reserve a 2 megabyte page. We're not allocating yet, we're just reserving. And until it fills up, or we use our new metric that we can just implement, essentially we have reserved it, but not allocated yet. If we couldn't reserve a 2 megabyte page, of course, we return -1. Otherwise, we successfully reserve a 2 megabyte chunk. So, if the region had already been promoted, we shouldn't have had the page fault. So this is an assert condition. And in this case, we essentially see whether or not we can promote a specific region, whether or not there are enough 4 kilobyte pages or our other features in order to promote this 2 megabyte region into a 2 megabyte allocated page. So essentially, the default mode is to use essentially utilization. So we count the number of 4 kilobyte pages that are set inside the 2 megabyte region. And if it exceeds a specific number, which is right here, the threshold for promotion, we essentially claim that we're ready to promote, and we're promoting this region from a 4 kilobyte, from a 2 megabyte reserved region with a few 4 kilobyte pages allocated inside it to a 2 megabyte allocated page. Are there any questions on that? Because this is the main function we're going to use to implement our mechanism. No? Perfect. Okay, so slowly we're going to start building up our mechanism. We're going to start implementing stuff on top of this allocator. So let's see the relevant code pieces. Okay. So the first code piece that we need to implement, and the main code piece that we need to implement, we have created this template function, is the metadata update. So we introduce a new function called metadata update. This function essentially is used to count every time we are accessing a specific 4 kilobyte page. We want to log the latency that it takes to access this specific page, and we want to accumulate these latencies. So we implement this metadata update function. This metadata update function belongs to the reservation THP class, and it's going to be called by outside. Specifically, it's going to be called by the MMU. And this function, we take an address, and we take the latency page, the translation latency, essentially. The first thing we need to do is calculate the region that this 4 kilobyte page is in. This region is allocated already because we have translated. So this has been already allocated, and we're going to find it for sure. So first of all, we'll comment this. And we're going to go into our map, and we're going to log this latency, this 4 kilobyte latency. And we're going to, as I said, we're going to accumulate. So we want to accumulate all latencies and check if we're above a specific threshold to promote the specific 2 megabyte region. Yes.
How would you do this in real hardware? Because like you cannot easily keep the latency.
Yes, as we say here as a note, essentially we would quantize this value. So we would essentially keep it, depending on the hardware availability that we have, we could quantize it to 8 bits, 16 bits, 32 bits, depending on what we want. And essentially we can set a threshold. So the granularity at which we keep, of course, gives us more flexibility, but of course incurs hardware overhead. So the more bits we keep, the more accurate we can be.
Did you keep it in like inside the base table or in a separate hardware module or in a separate software structure?
So in this specific case, you can do it in the software. So you don't necessarily need to keep a hardware structure for it. But still, the bits that you're going to use are going to determine the memory overhead of this specific structure, and are going to be and you should try to minimize. But this is just for simplicity, we have not quantized, but you could possibly quantize.
Thanks.
Perfect. So this metadata update, we essentially want, first of all, to use it to essentially log these latencies. So we're going to go in the MMU. The MMU was shown by Konstantinos in the previous segment of our tutorial. And we're going to go at the final part of the MMU where we were charging the latencies. So at some point after we allocate on our TLBs, we have these two latencies here, the total walk latency, that means the amount of time that it took to perform the page table walk, and the charged TLB latency, the amount it took to access the TLBs. So what we're going to do is we're going to access, using this sim get mimic.s get memory allocator, we have built sort of pointer in order to be able to access mimic.s from everywhere in our script. And we're going to call the metadata update function from the memory allocator that we have set. And we're going to pass the entire translation latency, both the TLB and the page table walk latency, in order to log it and accumulate in the accumulator that we implemented before. So but we also, so when we demote and when we promote a specific page, we also want to reset this counter. So this will be done in the reserve THP file again. So here is the place where we essentially promote this page to the 2 megabyte page. We need to reset this metadata counter, so we are going to use again the same function, but with subsecond times 0, which essentially is the 0 time for sniper. Perfect. And now the final part. Is here we need to essentially create, we need to check the threshold. So first of all, we need to get the time for the specific latency. This is inside the check 2 megabyte allocation function that we saw before. And where we had for the utilization before only as a metric, how many 4 kilobyte pages inside the 2 megabyte region, we're going to also add the latency 4 kilobytes. So we're going to take this from our map that we have already saved it and accumulated it. And then essentially we need to implement. For now, the implementation of how the utilization is used is this. So we set it to promote true only if the utilization is above a specific threshold. And we're using this to essentially promote and to log stats and in the future promote as well. So what we're going to add is we're going to add this piece of code. Let me comment that. And essentially, we have two configuration values that we have implemented in the specific scenario. The enable latency aware promotion. So if this is false, we're going to fall back to our baseline promotion strategy, which is essentially using only the utilization. And we have the promotion threshold for latency 4 kilobytes. So essentially, we're taking the accumulated value that we have and we're comparing it against a threshold. If we're above this threshold, we are going to promote, we're going to set the rate to promote true, and we're going to promote. We're going to use a combination of the utilization and the latency 4 kilobyte in order to have the most accurate metric that we have for the specific scenario. So we can see again how these were set. So we can have it here. So in the beginning, when we're initiating the allocator, we're doing what Konstantinos showed in the previous part of the tutorial. Essentially, we're taking a configuration value, and we are going to take this configuration value and this configuration value, and we're going to put them in variables that we're going to use in our simulation. And I will show later the config as well. And this is it. And this is exactly this is the only thing we need to do in order to implement a latency-aware allocator in Virtuoso. Are there any questions for the code part? I'm going to show the configuration afterwards. No questions, suppose.
So could it also be that you use like an and clause, which means that like you would promote only if the utilization is above a level and the latency is above a level. So basically to trade off between like, okay, I will only promote as long as I will promote and waste capacity if the translation latency is high.
Yes, essentially it's a trade-off between fragmentation. Basically, you're tuning how aggressive you want to be.
Yeah.
And the features are generally tuning how aggressive or not aggressive you want to be. The choice essentially set how smart the mechanism is, and whether or not you're going to use or an and is going to tune how aggressive you are. And the more aggressive you are with your promotions, the more internal fragmentation you have. The more pessimistic you are with your promotions, the more external fragmentation you're going to have. So it's a trade-off between external and internal fragmentation, depending on your workload characteristics or depending on your analysis, and generally it's a choice. Okay. So we're going to show the configuration value, the configuration file, sorry. Perfect. So this right here is the configuration file. And from the allocator, specifically visual memory allocation and reserve thp.cfg, we have here. We have included these two this attribute and this attribute here, which essentially are the ones that are controlling our new promotion mechanism. This can be set at whatever value. Now, your task is to simply run the run part 1.1, which is running two things. First of all, it's running the traditional promotion using only the utilization. And the second run is running the new promotion with the new feature with a threshold of 0 for this specific case, but we can change the threshold. Let's make the threshold slightly higher. Oh, the threshold for promotion latency is 1,000. I'm sorry, it's right here. Let's put it here. Perfect. Okay, so we can run it and we can see the results. We can do this as well. Part 1.1. There's nothing you need to modify. You can run it.
We modify the text.
No, there's nothing you need to modify. It's ready.
Okay.
Just run the script again.
Yes. Essentially, we encoded just to show what are the changes and how we can implement something new. When we're done. So you had the question?
Yes, may have missed this. But you described that you promote based on the latency of page. What is this latency? Where is it coming from? Just from like the TLB latency and the page walk latency?
Yes. So
Now, if that's the case, then this really depends on the DRAM model as well, right?
I agree, yes.
The exact latency that you charge.
Yes.
Which means that the way we're modeling right now, as far as I understand, you have a static latency for the DRAM.
We have a DRAM model in
We have the
Virtuoso.
DRAM model.
Yes.
Okay.
Yes.
That's
But generally, the threshold, we have set it after some profiling, of course. So we have seen these values and we have set to a specific value. For this example, we have preset it, but someone can, it's up to the designer to set the correct value. Yeah. Okay, so we have run it and everyone has finished. So we can go and see the results. So I want to compare specifically one stat. So let's go to results. Here for the original promotion strategy, and here for the new proposed promotion strategy. Let's put them side by side. Perfect. So the metric that essentially is going to show us that it works and we have a different behavior in this specific scenario. There could be many metrics, but one good metric is the total number of pages that have been allocated. So in this specific scenario, in the baseline, essentially, the total allocations are 1,274. And we should see less total allocations in the modified scenario. Shouldn't see more, we should see less. We see less allocations in the modified scenario. So what we can do, so we should have had more. So let's debug a little bit.
I think you have more because the number of promoted pages.
You're not wrong. Yes, the number of promoted pages are doubled. We have the same reserved regions. Yes, you're right.
I think the total in this scenario is the whole kilobyte page.
Yes, you're right. Yes, and we can see here that the promotions caused by latency are 6 in this specific scenario, and the promotions caused by utilizations are 0. So essentially, by introducing the latency metric, we have more promotions caused by latency. Essentially, the utilization metric is not used because first we reach the latency metric and then we promote. Do you see the same results? You can check.
Yeah.
Yep. Perfect. And that wraps up the second part of the tutorial, and we can move on to part 2. Should we have a 5-minute break? Yes.
Yeah, sure.
Can you guys hear me from Zoom? YouTube?
Yeah.
Yes? YouTube? Yes? Hello? Okay. So I'm gonna go into the hardest part of today's session, which is how we can delegate physical memory allocation to hardware. This is related to one of the talks happened today. So we discussed before the memory allocation overhead. So we have a bunch of emerging workloads, function as a survey, short input, short output, large language model inference, which are short running, they have a high spawning throughput, and the latency of the OS memory allocation routines cannot be amortized due to short execution. So how does memory allocation work? When I want to map a page from the virtual address space and we want to find its position in the physical memory, then we need to map it somehow. And the process of mapping it is called fault. So when the virtual address is not mapped to the physical memory, the OS takes over the fault. And the operating system handles essentially the physical memory allocation. The application gets stalled, the operating system finds free physical space and physical memory for the page. This is called a minor page fault. If we need to access the data as well from the disk, then we call this a major page fault. And we also have, because of this process, frequent context switches. What does that mean? We have the page table walker who faults frequently. We have lots of context switches, and the operating system handler is called multiple times, stalling our process. So if there are other instructions which are ready to be executed in the pipeline, they could not be executed and they would face bubbles because of the context switch and the OS handler taking over the compute resources. So essentially, context switching in this context kills the instruction level parallelism that could be exposed by our application. This leads to high latency memory allocation. And in this plot, we show the breakdown in terms of execution time that the minor page fault take compared to the address translation for a bunch of workloads which are short running. And we see that more than 30% of average execution time is spent on allocating memory. We also waste energy for allocation. Why? Because the OS handler needs to execute the operating system instructions in the power-hungry out-of-order core. And the first thing we're going to do is evaluate these overheads in Virtuoso. So I would suggest first to the audience to git checkout to part 1.2 and then build again the simulator. Are you doing it? Okay, sure. Okay. Yeah, I'm gonna wait a bit. You can stash the changes, right? You can stash and then basically check out to another branch. Okay, did you check out to part 1.2 or? Okay, sure. Now you need to make this clean and then make again the simulator, build it from scratch with -J2 in your scenario because you're using the VM. You need to go inside Virtuoso, Simulator, Sniper, and then there's a make. So let me give you the path actually, so that I can show it also. So let's see, I show you my screen. Okay.
inside simulator, sniper. Sniper. And then my mic minus J2. Okay, sure. So while it's compiling for you guys, I'm gonna give a short intro onto how basically we can use the MimicOS for on runtime to discover the overheads of the software-based page faults. So basically, what is MimicOS? Let's recap again. It's a minimal user space operating system that runs alongside a sniper-like or a shift-like or a trace-based simulator. And for now, for this tutorial, we configure it only to handle page faults and allocate physical memory frames on demand for a single process. So it basically takes as input an initialization file. This contains init parameters for the physical memory allocator. It boots a traced user application, so you can boot both executables and traced applications. It receives allocation requests from the simulator, typically on page faults, and it allocates frames either for data or for page tables and sends the messages via a message protocol to the simulator. So as you can see, this is the constructor of MimicOS, where we simply read the parameters for the physical memory allocator which we create. And where do we get these values from? We have specified an init file which describes what is the allocator we're using, how big is your memory, what's the target fragmentation, and such stuff. So basically, for example, we can show what's the fragmentation type, the threshold for promotion, the target fragmentation, and much more. And the question is right now, how do we boot? So the way to boot is by instantiating the allocator and then fragmenting the memory. So we want to fragment the memory to be able to emulate scenarios where memory is fragmented, same way we did before for our experiments. One of the key things that we did during the boot process is the start application process. So in start applications, we're essentially trying to do two things. First, we execute a magic instruction. The magic instruction is the simroy start. And as you can see here, the simroy start is an instruction, most commonly in x86, it's the exchange instruction, which is a special one. The simulator treats it as a special instruction that gives a specific signal. In this scenario, the signal is that you should start performing detailed simulation after the simroy start has been executed. And then after we start the detailed simulation, then we want to send another signal to the simulator, the sim start process magic instruction. And the sim start process basically takes as input a path, which is a path to the trace that the user wants to execute, which is our workload. So essentially, we're giving a message to the simulator saying, okay, this is where you should start performing a detailed simulation, and this is the trace that you should use to perform this simulation. Yeah, sure.
This is an instruction to the simulator or the underlying hardware that returned the instruction?
This is an instruction basically to the simulator. Okay. So you're essentially executing a normal instruction, but which has no effect on the architectural state, which means I'm doing an exchange of an R1 register with another R1 register. This doesn't affect the architectural state, but the contents of the R1 show you what is the shadow message, the secret message you want to pass to the simulator, which is, for example, if you use opcodes and you store in R1 the byte, let's say an 8-byte number, you can say, okay, you treat 0 as a simroy start, treat 1 as a sim start process. And the simulator understands what message you want to convey every single time. How is the compilation going?
No.
It's not done.
Okay. Yeah.
No.
Oh, yeah, sure. Yeah, and the main loop for the simulator is the following. So the simulator for the Mimic OS is the following. After we boot the application, we have only one job to do. So we context switch immediately back to our process. What does that mean? We haven't received a page fault yet, so there's no point in handling a message. So before we boot, after we boot our application, we immediately give over control back to our application. We basically yield the core to the application using a magic instruction called the context switch. So in this context, in this specific instruction here, we do not charge a latency. And maybe in some cases, this specific instruction, the sim context switch, you want to charge a specific latency for the context switch in the simulator. For this tutorial's purposes, we don't do that. We just simplify the magic instruction. In a functional manner, we simply send a message to the simulator that, okay, you should continue running your application. And how does this mini OS look like? So it needs to receive a message. So this is a magic instruction again, which is a blocking instruction. And what does that mean? We need to block until we receive a message. So the simulator receives this instruction and blocks essentially until it finds a page fault. So it will not process any other instructions from the Mimic OS or instrument any other instructions from the Mimic OS until it finds a page fault. And once it finds a page fault and we return from the sim receive message, then we will simply execute. We will first allocate the data frames, the data frames using the physical memory allocator that lives inside Mimic OS, and then we will allocate the page type and send the response back to the simulator. And how do we send the response back? Again, our communication so that we are fast, no need for shared memory, no need for any expensive synchronization. We have magic instructions. How does that work? We send the result back using a magic instruction, the pointers to our messages. So as I said before, we have an exchange instruction. We can use the R1 register, and inside the R1 register exchange with itself, we can add the pointer to the structure that we wanna copy at the simulator side. Which part could be a problem? In what aspect? Oh yeah, sure. So this is for single core, right? If I wanted to support multi-core, okay, let me say it another way. So here I'm spawning one Mimic OS thread, which will handle all allocations in the system. If I wanted to spawn multiple Mimic OS threads that each one can run in its own core, then I would basically need to synchronize on top of some of these operations so that there would be no correctness issues, basically. Yeah, so here you can see the whole flow. The application sends a signal to the simulator. Oh, I have a page fault at this virtual address. So the simulator says, oh, I will call Mimic OS. Mimic OS calls up the allocator. And then Mimic OS finally sends a message to the simulator saying, oh, take your data back. And then the simulator says, okay, you can continue. I will model your instructions. You can continue giving me data, basically. So I'm gonna go right now into the technical part. Oh, sure, yeah. Yeah, let's wait a bit. It's fine. It's taking a bit of time. So the code for Mimic OS is quite complicated. I cannot show you the full aspect of how we integrated with Sniper, but let's do one thing first. So we want to study let's give some sort of perspective to someone who wants to study minor page faults, right? So how would someone approach this? Does anyone have any idea? So let's say that you want to figure out how your simulator models minor page faults. How well does it do that? Like, what is the first step And how would you approach this basically? Like what sort of application would you run? Like what's a good application that you should run? Yeah, something with a large memory footprint, but like would you start by checking every application in the wild and seeing which one has a high memory footprint?
There would be class of workloads that sort of.
Sure, but let's say you're in the implementation phase. You don't want to search for workloads. Then what would you do?
You would write a bench.
Exactly, which is called a micro benchmark. Exactly. So the first thing we're gonna do is we wrote a micro benchmark basically. And what does this micro benchmark do? It does only one simple thing. It accesses memory at the page granularity. So it basically touches different pages. It touches 10,000 pages in this context. And we have already created the trace file for this micro benchmark that touches so many pages so that we can feed it to Sniper and figure out, okay, how well do we capture the minor page fault overheads? What does Sniper do with respect to the user, right? Because this micro benchmark consists mostly of minor page faults. It doesn't do anything else. So let's see how this works. Oh, it's done. Okay, cool. Then let's do the following. Let's first learn the baseline system, right? So the baseline system, essentially, we want to find out like what is the cycle count reported in the simulator by the baselines in the baseline system, so that we can then compare it to what like Mimic OS plus Sniper reports as latency to figure out like how close these two are, right? So let's run. Yeah, I'm also compiling because I. Yeah, let me check. Okay, also compiled. You also compiled, so we're in a good state. So what we're gonna do is run our baseline, basically. Figure out how many cycles they estimate that the program will run. So we run the program till completion. This is a key when you're doing this sort of like
fault-based or operating system overhead studies, you need to run as much of your application as possible, especially when you have the short-running workloads. It's very easy to run them till completion because they will not take like 3 months to run, right? So let's run the baseline system. You can also run the same thing. Yes.
One application like LM, where running to the first token, for example, is important. Wouldn't that be also a use case? But you don't need to run necessarily on the application, but you can run to the first token.
Potentially, you can extrapolate the overheads if you know the page fault rate of your application, or if you know that the page fault rate of your application is constant. So if you know that the amount of page faults per kilo instructions is constant throughout your application, then of course you could extrapolate and make it.
You may only be interested in the first one.
Then if you're interested in the first one from a tail latency point of view, then you could also isolate it clearly. But yeah, sure, that's possible. It depends on your type of study you want to do, right? If I want to measure throughput or I want to measure like end-to-end latency, maybe I want to run the full application. If I want to measure tail latency, then I wanna run some first iterations which are very cold, let's say. On granular application, we see that it's running extremely fast. Yeah, because it has a really small number of instructions, basically. That's why it's running very fast. We can find the results inside the baseline. So what do we see here? How many cycles do we spend? So we spend 600,000. And we have around 600,000 cycles spent by the baseline system to run this application end-to-end. So let's see right now a different sort of experiment. So in this experiment, we're going to see how much time does it take and is reported by Mimic OS running on top of Sniper. And in this context, we're taking the overheads of page faults into account when we simulate our application. We do this, we basically say, okay, I want to basically execute the Mimic OS executable. You can think of this as your boot process for the operating system. And I'm going to give it an argument, which is my workload. And my workload in this context is basically the minor fault micro benchmark shift trace. So I'm telling the simulator, okay, I'm going to boot you up with the Mimic OS. I'm going to give you one specific trace that you want to execute. And then I will be instrumenting and delivering information about the overheads of page faults and the page fault outcomes to the underlying simulator. So let's run this script together. The script will run okay, right? Okay. Oh, sorry, I have a mistake in the configuration. Okay, let's observe the following right now. Look at how many more instructions it's running in order to run this whole process. Imagine before we had 300,000 instructions. Look at how many instructions it's running right now to be able to simulate the full application. It's going beyond 2 million. Which is a sign that the previous simulation was not taking into account any sort of instructions that were causing the page faults, that were executing during the page faults.
Do you have a complicated page fault algorithm? Or
in this scenario, we have a complicated page for that algorithm.
Does this play a role, whether or not it's a complicated one? How
Yes.
close is the real?
It's a matter of software efficiency in this scenario.
I mean, the number of instructions per page fault, is it reminiscent to the actual linear system?
Yes, and we show this in the paper, but there is a linear relationship basically. The more you increase the instructions, the more time it takes, right? Which is the same is the case for linear. So our simulation finished after 2 million instructions almost. And let's see the results right now. Let me remind you, before we had 600,000 cycles for
This is an order of magnitude.
what?
This is an order of magnitude.
Yes, in this scenario, the application spent 21 million cycles to be executed, which is a very high amount compared to the baseline that did not take into account any page faults. Let me show you the exact number from the statistics. So yeah, in this context, it took 8 million cycles to execute the program. So instead of 600,000, we spent 8 million cycles to execute the program. Let's see the difference between like if I do not simulate page faults, I would not capture any of these overheads in this context.
These instructions would come from the way we model it, right?
Yes, but like
essentially how, yeah. Right.
Yes, so we need to be precise when it comes to that because we need to define what system we want to emulate. Exactly. If we want to emulate Linux with transparent huge pages,
yeah,
MimicOS should be designed so that
similar.
Yes, in a similar way. That's why we use multiple modules so that people can configure this, right?
Essentially imitating.
Yes. Exactly. Okay, so we see this difference, right? It's almost an order of magnitude more. An order, 2 orders. The one order of magnitude more. So let's see how to deal with this problem right now. We see that this workload is spending too much time on page faults, right? And let me show you right now one approach which we can take in order to alleviate this overheads in a way. Show my screen. So there are a bunch of works which have proposed offloading the page faults at the hardware level. And how do we do that? We basically, when the page table watcher finds out there is a fault, we do not trap to the OS. We have a designated module at the hardware level to handle these faults. And the simplest form of delegation is the following. The hardware unit can say, okay, give me some memory so that I can handle it on my own. So the main memory would look like this. Some of it would be hardware managed, some of it would be software managed. Does this remind you of anything? We can basically restrict the virtual address to physical address mapping, and as proposed by some previous work from the group, we can basically hash virtual addresses, map them into the physical address space, and we split the physical address space between a mapping which is hardware managed and a mapping which is software managed. You can employ the same idea as in Utopia for memory allocation instead of accelerating address translation. The simplest form of delegation, again, we want to allocate, we send a signal that we want to allocate, and what do we do? When we want to figure out whether a page is free or not, we calculate the set index inside the segment using hashing, And we store an array that keeps track of the tags, same way that caches do. So we have a tag array lookup FSM that simply checks whether the tags match or do not, or whether there is something free or not. If we find out that the tags match, then we serve directly the translation. Otherwise, we do the allocation. So you did git checkout to part 2, and then we make this clean make, and this works for everyone. And now we go to the demo time for the final part. See how we would change the MMU to support this. So basically, we want to do the following. We want to extend the memory management unit with a new class, a new handler called the hardware-based fault handler. Hardware-based fault handler. And what does this handler do? It does one thing. If we find out there's a fault, we will first try to go there and handle the hardware level. So how did we do this? The first thing we did was to basically define this hardware fault handler. It needs two things. It needs a start physical page number and the end physical page number. Why does it need these? Because we need to be able to manage the memory provided by the OS on our own. Why is that important? It's important to do this because otherwise you would need basically to synchronize with the operating system when it comes to allocation. And that's a very costly process. That's why simply getting a pool of pages and then making sure you handle them at the hardware level solely without involving the OS, this gives you the flexibility that you can do a lot of tricks to avoid the latencies coming with synchronization overheads between the hardware and the operating system, which is very, very tricky to handle. We also need to store the tag array. The tag array will tell us, oh, in this in this part of the memory, there's already a page, the tag does not match or matches with what you have, right? Yes, sure.
So if you bypass or sidestep synchronization, can you still provide guarantees? So this is what you will achieve with this, because your hardware might, let's say, start the OS, maybe access the action to the OS in terms of access to the memory.
That's why you usually predefine the segment, right? So you basically, the interface would be the following. You request something from the OS, and the OS decides if it's going to give it to you or not. Because, okay, yeah, sure, hardware could also reserve like 20 gigabytes out of my 32, but that doesn't work, right? Because I see that it's underutilized, or I see something similar. So it's a matter of QoS and different like profiles of the applications are running in the system, like how much an application or a process can allocate, how much, yeah, it depends on many factors like memory pressure, memory capacity pressure, and more. It's the same argument with respect to like, can a process malloc the whole memory? Yeah, it can. But probably if I try to malloc the whole memory and allocate it, then the OS is going to kill it.
Yeah.
And then we need two things as well. We need to be able to simulate the latency of accessing the tag array. So we need to store a pointer to the start physical page number of the tag array and the end physical page number of the tag array. So when there is a fault happening, then we need to do two things. First, we need to check if we can translate the address directly using this hardware fault handler. So how do we address? We find the physical page number by hashing the physical address using a mod operation. Here I'll use something very simple. And we find out the index in a direct mapped segment which we allocated for our own hardware fault purposes. So if the tag array at this specific index matches with the tag of the address shifted by the page size, then we return it immediately, which means we can resolve address translation immediately for this segment without doing more. Otherwise, we return -1. What does -1 mean in this case? It means that, like, okay, I cannot find this yet, but yeah, so I cannot find this, but I can allocate it. And what do we do here is, like, if this returns -1, then we go forward and allocate to the corresponding VPN if there's no aliasing problem. If there's an aliasing problem, then we basically say, okay, I cannot do anything more, so I will trap back to the operating system. Why? Because I returned -1, so my handle fault was a failure. I couldn't handle the fault using the hardware-based fault handler. Otherwise, I return the translation again because I allocated, and then the TLBs and the MMU is waiting for me to return the translation. And how do we integrate this in the MMU? So basically, what we did is that we instantiated the hardware fault handler. Yeah, these are details are not important right now. I delegate the memory size to have only 4,096 pages. Let me remind you, our application touches around 10,000 pages. And what we do is very simple. Based on the description I gave before about the MMU, so in case there is a fault, the first thing I do after I realize there's a fault, I check if the hardware fault handler can handle the fault. But this is not the only way to handle the fault. This is the fast way of handling the fault. If we fail, then we keep the cause the page fault is true because we will trap back to the Mimic OS. Else, we didn't cause a page fault. We got the result because it translated, it allocated the page for us, and the page size is 12. We made it allocate only at the 4 kilobyte granularity. So imagine I wrote inside the MMU 10 lines of code to be able to implement this, right? Which is very, very simple. Let's see how this performs compared to Mimic OS. The pure Mimic OS implementation, let me remind you, took around 8 million cycles to run. You can run this with me. Is that fine, Christine? Cool. Yeah, so the difference here is that I change the configuration only, right? I change the configuration so that my MMU uses the hardware-based page fault handler. Aha, so it ran a bit faster compared to the previous time, where we were spending more than 3 million instructions to run a simulator. Why? Because right now, that's the time. Exactly, we spend a lot less time in the operating system. So basically, if we see the amount of cycles we spend right now, we spend, sorry. Yes, so right now, instead of 8 million cycles, we spend 1.2 million cycles, basically.
which makes a huge difference. We spend more time than, of course, what the system without page faults would do, but it's almost an 8x decrease compared to handling the page faults solely at the software level. And yeah, this is to showcase the importance first of modeling these overheads, and second, to showcase what big of a benefit you can have with simple modules by offloading such noise routines at the hardware level. Thanks. Any questions? Stay. Yeah.
No, it's here. Yes, again. No. I don't think so.
No, we cannot.
You cannot?
Because I should be able to hear things from YouTube and I'm not.
You're not sure. I'm not sure if my computer microphone is okay.
Let's try. Can you see? Can you hear this now from the?
It is perfect.
You can hear me?
Yes. I
Okay, then let's
yes,
use
but-
that.
Wait. And do the.
Can you hear this? No.
This?
Yeah, hello. Come on. Okay.
Okay, so welcome back. So this is going to be the last part of the tutorial part of Virtuoso. And we will talk about how we can enable studies with different simulators in terms of integration and in terms of enabling some complicated schemes that involve the requirements of integrating with other simulators like Ramulator. And in particular, we will look at how we can enable swap space-based studies. Before we can start, for all the attendees here, you would want to check out to part 2.0. And you can make this clean and then make your make the simulator basically. So it's git checkout part 2.0. This might take a few, well, just one moment. In the root directory, essentially. So what is swap space? When you run an application in the virtual address space, each page is mapped to one physical memory page. However, if you keep doing this, your entire physical memory may be occupied. You may lose, you may be out of pages in the physical memory, and you may not be able to find a page to map the VPN, the virtual page number, to some PPN. And this is why you need swap space. Yeah, essentially memory is full and you want to kill some apps to free memory. And this is a big problem essentially, because you may not want to kill applications. What you can do is place some apps in some of the core pages in swap space. You have the apps in the virtual address space, which map to physical memory. And again, like we said, we have pages in the physical memory that you cannot map to. For example, this particular one, which maps to the third frame. What we can do is we have a swap space, which is in the storage. And you can evict 2 pages from the physical memory if they're cold through some policy and move them to the swap space. And which allows you now to map the page in the virtual address space to the physical memory from the vacant pages in the physical memory, that is. And this allows us to essentially save the day. We don't need to kill apps anymore. And for this, we have a small demo. Well, just some code that we've written to model the swap space through Mimic OS. And we can show you this from Visual Studio Code. So let's go to that very quickly. And Here we go. So here we have the swap space module, which is in the Mimic OS or stripped down Mimic OS, just for the purposes of this exercise. We consider swap cache essentially holds the data structure and provides an API to manage the swap cache. And it basically contains a swap cache map, which tries to map essentially your page ID, an app ID, a pair of page ID and map ID to essentially an end pointer, the pointer to the swap cache, essentially an index. For this particular example, we initialize some free pages and we assume that all pages are initially free, that you can essentially swap out to these pages. We provide a lookup method. So given a page ID and an app ID, you can find the location of a particular page ID, app ID pair in the swap cache map. And this returns to you whether you found a particular hit or not. If you found a hit, then you return a true and otherwise false. You also have two methods to swap out and swap in. Let's do swap in first. So when you want to swap in, essentially you want to move data from the RAM to the swap cache when you're out of physical memory. You choose cold pages and you invoke the swap in method. In this case, you look up the swap cache map to see if you can find a swap location. If you can find a swap location already, you erase this and you essentially swap in a page. On the other hand, for swap out, you look for free pages, essentially trying to swap out from the swap cache. And once you have a free page based on some way to find a free page, in this case, we just run a loop over all the free pages until you find a free page. And once you have a free page, you swap it out. And to do this, to find the location where you want to swap this out, you rely on the find free page. And this you insert into the swap cache map. And yes, and you update the statistics relevant to this. This is what the swap cache looks like. Going back to the tutorial, after learning what the swap cache looks like, and let me share. Okay, so we're back. So yeah, we've seen how the swap space can be implemented. What is important? An important question is what's the policy that we can use to perform swap outs? And for this, there exists various algorithms in the literature. One particular one is the clock algorithm and the clock pro. What clock says is that it's essentially a clock hand moves around a circular buffer, and you look at pages that have been touched in the past or not. If a page has been touched, you mark that as 1. If it has not been touched, it's marked as 0. If it has been touched and is marked 1, then you decrement it, giving it a second chance. For the pages that are already 0, you choose them for eviction. And for example, in this case, the page 1 marked 1 is not evicted, it's just given a second chance, and the page marked 0 is evicted. However, can we do something better? And to answer this, we come up with a scheme, a learning-based swap scheme, where you look at page table with various features that you can use to select candidates to swap out. In this particular case, let's say we found 2 victim candidates. And if you were to pass them through some learning model, in this particular case, we take a three-layer neural network model, then you can find the victim based on how this neural network was trained. The goal of this is to show that you can model such complicated schemes with ease using the MimicOS tool. And essentially, you model the side effects of swapping, which is essentially to do with the main memory and the storage. And to do the second part, which is to model the main memory and storage effects, we take as input a RAM-related trace, feed it into MimicOS. MimicOS models the page fault and the storage overheads, minor page fault and major page fault overheads, and dumps 2 traces. The first, a RAM-related trace that allows you to model the main memory impact of the virtual memory subsystem. And second, the impact of major page faults, in which you have swap-ins and swap-outs. And we use, in this case, MQSIM to show the impact of major page faults. This particular example shows how Virtuoso, MimicOS, and by extension Virtuoso, can be integrated with existing simulators to model various impacts. And for this example, the impact of the main memory and the storage subsystem. And this brings us to the main demo. Look at. All right, so this is the markdown that we have. And as we discussed, we will, this particular example probably will not work on the VM. So you can follow this and run this locally later because it relies on an a pin-based trace generator. And to model this, we again need to model 2 parts: the page fault overheads with the minor and major page faults. And lastly, the second part is the unified simulation that MimicOS MimicOS supports with RAM-related 2.0 and MQSIM. So the first part, to model the page fault and swap overheads, we take the original trace and model it through MimicOS to incorporate the storage, the main memory, and the storage accesses. And we do this through the magic instructions that Konstantinos discussed before this particular section. In the code section between the magic instructions, you can add the logic that you want to model. Let's say it's an allocation routine, a page fault routine, the swapping routine, for example. All of these can be modeled between this code section. And following this, we implement the swap space support by selecting some victim candidates and then predicting which one to evict. We can follow the code for this first. So let's look at this. For this, we have virtuoso.cpp, where we have the magic instructions here and here. Between this section, we go over all the lines in the trace, the input RAM-related trace that we just saw, and we check if this particular address of the memory instruction exists in the page table. We maintain a page table as a part of this app. And if we have a page fault, that is, we can't find this particular entry in the page table, then we enter the magic instruction area. First, we try to allocate. If allocation fails, then you may want to find a victim address to swap out. And to get the victim candidates, we essentially go over, we have a modified version of the clock algorithm where you select a k number of candidates, a k number of candidates that are suitable for eviction. And these are returned. These k candidates are returned. And we curate the set of features that will be passed to a neural network based evictor. And this comes from and here this basically shows that it's very easy to integrate and implement new techniques. It's extremely extensible for something that you may want to add, something like a neural network model to predict something. And in this case, you can predict which victim candidate you want to choose. This particular class basically models a 3-layer neural network. And we have a prediction class, which essentially outputs the index of the particular particular input, the candidate that you want to evict out.
You can capture this way the overheads of executing the neural network.
The neural network through the OS,
And
yes.
how do you figure out, like, if there's a fault, then what do you do? Like, whenever you need to access the disk.
Yes, sorry, go ahead.
Yeah, let's say that you find your victim candidate, then how do you proceed?
Once you find the set of victim candidates, you curate the features and pass them to the neural network to predict which victim index you have.
Let's say you found it.
Okay. Once you found the victim index, then first you go back and update the hand to go to the victim.
Sure.
Then you get the victim VPN. This is important because you want to swap out the victim address.
I see.
So you invoke the swap out method, which we just discussed with the swap cache implementation. Once you've swapped out the victim, you allocate the free page that the victim was pointing to the new address that you have. And you also modify the page table based on this new address.
And that's where you write the MQSIM.
Yes, this is where you write to the MQSIM, the trace. Similarly, you also have a swap in due to the migration from the SSD to the DRAM. So you also need to model the swap in request for the MQSIM. And this was captured here.
But you only swap out if the memory is full, right?
Yes.
Okay.
You swap out only when it's full.
Okay.
If you had a page table hit, then you essentially just modify. Well, if you had an allocate, if you were able to allocate, then you update the page table, and you add all the instructions that are incurred in allocating, which is already captured through the magic instructions. The rest is just boilerplate that we use to manage the files that we have in order to generate the Ramulator 2.0 trace and the MQSIM trace that will eventually help us model things. So running this, we provide instructions. So first you need to set up the environment variables. I can show this very quickly. I can run this here because this is not on one of the VMs. Just to quickly show people what this looks like. And we build. And this should build out of the box because this has been tried before. Hopefully, it works out of the box. And this build script builds the Mimic OS, builds Mimic OS, Ramulator 2.0, and MQSIM, all of them together. First, you need to go to Mimic OS, and run a trace that we provide that is slightly stripped to get to the interesting sections of the code. and it dumps to you the Ramulator 2 trace and the MQSIM trace. And if you may notice the output, you have ending PF and the number of instructions that were involved in handling this, and this is around 2000 right now. The number of instructions incurred in handling the page fault. As the physical memory is occupied due to mapping, you would run into major faults, which has not happened yet. Should happen soon. And now you see a much larger number of instructions being captured. And this keeps increasing because more and more pages are being occupied in the swap area. And because the find free page method is running a loop, this will keep increasing. I can show this as well again to be complete.
So the find free.
So the find free page, yes, sorry, go ahead.
It could be done with to avoid the linear search. We could do it with free lists, right?
Yes.
Okay, sure.
This particular one is just a for loop, so you keep seeing an increased number of instructions.
But like from a performance point of view, we want to do it with free lists.
Yes. And this runs for some instructions that the input trace has. We'll just let it finish. And we can discuss the next part, which is essentially running this dumped trace through Ramulator to get the latency that you would incur for all the minor page faults, inclusive of the regular memory accesses of the workload, and all the latency incurred for handling the major page faults through MQSIM. Let's just wait for the trace to complete. It seems to be taking longer than expected. Okay, so it has completed. And this generates two files on the left-hand side, if you may see. You have the final VTW25R2 trace, which is essentially a Ramulator 2 trace, and the MQSIM trace that we generate. We go ahead and run this with Ramulator and get the latency for the main memory accesses. And this is quite straightforward for Ramulator. You have cycles recorded core, which gives you the cycles that the core experiences to handle all the main memory accesses. Similarly, you can also go to MQSIM, and we have already populated an SSD configuration as well as a workload configuration. The workload configuration essentially points to the MQSIM trace that we just generated. And running this will give you the simulation time. And this is in nanoseconds, but this can be converted to get a result very quickly. And that's it. If you were to sum up the latencies, then you would get the total latency incurred by in running this workload. So that's it. Are there any questions? Okay. Okay, great. Thanks.
Okay, thanks everyone for staying so long. I guess it was a bit tiring with so much coding and running experiments and going through different concepts. You can find all these recorded on YouTube, which I think is going to be very helpful for people who want to either use Virtuoso or try to get a deeper understanding of how simulation works. Of course, get in touch with us if you want to contribute to the project, if you have questions, if you want to basically propose any workaround with existing issues. And I hope we have the second iteration of the workshop in Asplus. And I hope it's going to go even better. Thanks a lot, everyone. And I thank also my speakers, the speakers who joined, which I think they did a very good job gathering the audience, which was quite engaging. And I think we became a bit wiser today.